In a variety of subject areas, math models are developed to help in our understanding of the physical phenomena. The models often give us an equation that contains derivatives of some unknown function. An equation that contains a derivative of an unknown function is called a differential equation. Now, you've worked with a couple examples in the past. One example is free fall of a body. So let's say that we have an object that's being released from a certain height above the ground, and it's falling under the force of gravity. Now, the force of gravity is represented by G, and since it's pulling it downward, we use the minus to represent in the downward direction. So the total force acting on that object is minus m times g, where m is representing the mass of that object. Now recall that if h is the height of the object above the ground at any given time t, we called that a position function back in calculus. Its derivative with respect to t is the velocity. Its second derivative with respect to t was the acceleration of the object. Now, in these representations, h is the dependent variable, and t was the independent variable. Okay, so you see that in the derivative. You're taking the derivative of the dependent variable up here on the top, and the independent variable is the one that you're taking the derivative with respect to. Okay, so now, Newton's second law states that an object's mass times its acceleration has to be that total force. Well, so its acceleration is that second derivative. So we know mass times acceleration has to be the total force acting on it, which is the minus m times g. So this is a differential equation. Our unknown function is h of t, and that's what you're taking the derivative with respect to. The dependent variable, you're taking the derivative of h with respect to the independent variable t. So here's a differential equation. Our goal here is to find h of t, that unknown function. So now to solve this, you would first divide both sides by m, the mass, and you would have the second derivative of h with respect to t equal to minus g. Our independent variable is t, so integrate both sides with respect to t. Well, the antiderivative of the second derivative would just be the first derivative. And we're integrating minus g with respect to t, so it's going to be minus g times t plus some constant. Now, to find h, we're going to integrate again. The antiderivative of the derivative of h with respect to t would just be h. And again, it's a function of t, so I'm just using the function notation. And the integral of the right side will be minus g t squared over 2, since we're integrating with respect to t, plus c times t. Now I'm going to call that c1 because I'm fixing to have another constant since I'm integrating twice, plus c2. So this is the function. We now know the function that would satisfy this differential equation. Notice here, since this differential equation contains a second derivative, that you end up having to integrate twice, and you end up with two constants of integration. Okay, now another example that you've worked with in the past, probably in algebra and possibly in calculus as well, was the decay of a radioactive substance. So now the relationship between the rate of change of that decay, the rate of decay will be proportional to the amount of the radioactive substance present. So let's say that A is the amount of the radioactive substance present at time t, so we could call that A of t. K is the proportionality constant, and then it said the rate of decay is proportional to the amount present, so that means that dA dt is the constant of proportionality times the amount present, which is A. Now the minus here is because the rate of decay is going to be negative since the amount of the substance is actually decreasing. So again, we have a differential equation. Okay, this one only contains the first order derivative. If I were to solve, I'm looking for a of t in this equation. Okay, that has to satisfy that equation. So to find a of t, I'm going to separate my a's and t. So I'm going to do it this way. You did this back in probably Calculus 2. dA, and I'm going to have times 1 over a. I'm going to move my a to the left side by dividing both sides by it, or multiplying by 1 over a, equal to minus k times dt. Now again, my independent variable here is t. My dependent variable is a. Now I'm going to integrate both sides. Now the left side, I'm actually integrating with respect to a. So I'm going to have the natural log of a plus some constant. On the right side, I'm integrating with respect to t. So that's going to be minus k times t plus another constant. Now, one thing I want to point out here is that we just did two integrations. So we have two constants of integration that might be different, but they're both unknown constants. So what we can do is we can just subtract one of these from both sides and just be left with one constant to deal with. So I'm going to rewrite this as natural log of a is equal to minus k times t, and I'm going to combine those two constants and just call it a single c. So instead of having to represent that you've changed the previous constant, we're just going to keep calling it c, and when we actually solve for it later, the value will come out at that point. But we don't have to keep track of all the changes to that constant. Okay, so now I'm trying to solve for the a of t here. And to do that, I'm going to need to change the exponential notation. So remember that the log's base here is e. So this is equivalent to e to the minus kt plus c equal to the value you're taking the log of, the a here. Now some people like to say, okay, e to both sides, so that's e to the log of a equal to e to the minus kt plus c. So that's another way to actually get it, or just switch from the log notation to the exponential, which is base to the other side equal to the argument of the log. Okay, so we've got this equation now. We've just solved for a. So we now have a of t. So let me simplify this a little bit. I have a of t equal, now the left side here, I can break up. Remember that if you have a to the n times a to the m, that's the same thing as a to the n plus m. Well, if I start where I have a sum in the exponent, that's equivalent to e to the minus kt times e to the c. So I've just used this property backwards. Okay, and the reason to do that is that I've separated now so that this e to the c is just a constant, because c is a constant and e to that constant is just another constant. So again, you probably guessed it, I'm just going to call that constant c. So a of t here would be c times e to the minus kt. Now that c actually is representing how much is present at time 0, the initial amount present. But this is your function. That function satisfies this differential equation. So we found what the amount of that radioactive substance is at any given time t. So we found that unknown function. So notice here and in the previous problem, the solution that we found was a function. This is a function of t. It's not just a number like solutions were in the past when we were solving linear and quadratic equations. Here, the solution to a differential equation will be a function of an independent variable. So now, anytime your math model involves a rate of change of one variable with respect to another, you're going to end up with a differential equation. And you're measuring rates of change, which are things we can easily observe and record. So most of these math models that you've worked with in the past might come from observing some rate of change and measuring it, and you're using a math model then to describe, you know, in the solution to that differential equation would be the math model that you're getting. So differential equations come up in a lot of different applications. One more thing I want to point out here is, given this function, which was the solution to the differential equation, you can see A is your dependent variable. T here was your independent variable, just by looking at the function notation, and see how that corresponds to the derivative notation. What you were taking the derivative of in this on the top was the dependent variable, and what you were taking the derivative with respect to was your independent variable. Okay, now let's talk about some terminology. If you have an equation that has a derivative of one variable with respect to another, the former one is called the dependent variable, and the later is called the independent variable. So in the previous problem, we had dh dt. The h was what you were taking the derivative of. That was your dependent variable. And you were taking the derivative with respect to time. That was your independent variable. Okay? A differential equation that has only ordinary derivatives with respect to a single independent variable is called an ordinary differential equation. Now, we've been working with y being a function of x. So y equal to x squared plus 2x. So if you looked at the derivative of that, dy, so we're taking the derivative of y with respect to x. Y is dependent, x is independent. You would have 2x plus 2 for your differential equation. Because y was a function of a single independent variable, so you only had a derivative of the y with respect to that single independent variable in your equation. This was called an ordinary differential equation. In Calculus 3, you've studied functions of multiple variables. So you may have had z equal to some function of x and y. So maybe an expression like 4x squared plus 5xy. Z is a function of x and y. So when you took derivatives, because there were two independent variables, you had to isolate which you were looking at z changing with respect to. So you found the change in z with respect to x by holding the y constant, so the change in z with respect to x, and you had the change in the z with respect to y. Now the notation, instead of using dz dx, you used del z del x. So this notation using the del operator instead of the d was the way you represented that you were doing partial derivatives. Okay, so when you have a variable that's a function of more than one independent variable, you're going to have a differential equation then that's a partial differential equation. So it's pretty easy to tell. Are you dealing with the del when you're taking the derivatives of the independent variables, or are you going to have the d representing that it was a function of just the one independent variable? So in this problem, so if I were taking the derivative of z with respect to x, and if you haven't had Cal 3 yet, don't worry about it, but the answer here, you're holding the y as if it's a constant, would be 8x plus 5y. That was the partial derivative of z with respect to x. That's a partial differential equation because it has that partial derivative. Okay, so now the order of a differential equation, what do we mean by order? An order of a differential equation is talking about what is the highest order derivative that's present in that equation. We saw an example where you had a first order differential derivative in an equation, and we saw another example with a second order derivative. The order is the highest order of the derivative that's in the equation. So in the problem that we had where we were looking at the change in the height with respect to time, this was a second order derivative, so this would be a order 2 differential equation. Okay, so now the term linear, that's even a different concept. Think back to where you've heard linear in the past. In algebra, you had linear equations, 2x plus 3y equal to 7. Okay, we know the graph was a line. Linear actually was referring to something more than just the fact that the graph was a line. It was looking at the variable, the terms of the in the equation. Each variable was raised to the first power. In fact, if you had a term that had a product of 2, I mean, you didn't. When you were talking about linear equations, you couldn't have a term that had an x times a y, or it wouldn't be a linear equation. So this was linear because each term had a power of 1, or degree of 1, for the combination of the variables, and each one just had a single variable. So if you looked at the degree of the terms, each had degree 1. Now let's look at a quadratic equation. You later looked at things like 2x squared plus 5xy plus 7y squared plus, let's go and do 8y equal to 1. Okay, now this equation is not linear. This term has a degree of 2 on the x. The degree of the y here is 2. Now the degree of this 8y term is just 1. This term, because it has a combination of the two variables, is actually degree 2. You actually add the degrees of each of the two variables to get a degree of a term. So this was actually a second degree equation. Okay, second degree polynomial, which meant it was not linear. A linear equation has to be one where the degree of each of the terms is just 1. Now when you're talking about differential equations being linear, you're going to look at the dependent variable and its derivatives, and each term can only have first powers. So you can't have any terms that have a second degree. So notice in this first term, we can have expressions here that are multiplied by that nth order derivative, but we can't have any y's or other derivatives of y multiplied by that nth order derivative. So you can have the derivatives, notice all the derivative terms, but the only thing that can be multiplied by them will be either constants or functions of the independent variable. You will not have a y times a dy dx, because if you found the powers of each of those and added them together, this would be a power of 1, and this is a raised to the power of 1. That would actually be a second degree term. Okay, so you're just looking at the dependent variable and its derivatives, and add their powers for the terms. So notice every term here, and when I say term, I'm talking about the pieces separated by the plus and minus signs. You'll either have a derivative in them, or you'll have a y in them, but you will not have a product of both or a higher degree of any of them. You will not have a y squared. You will not have a derivative of y squared. Notice that's not the same as the second derivative of y. It's the first derivative squared. So all the dependent variables y and all of their derivatives will appear just to the first power in all of the terms. Okay, now notice on the right side, the term that doesn't have any of the dependent variable is just going to be an expression of the independent variable. Okay, so no y squareds, no dy dx's, no functions of the y. You can't have an e to the y. You can't have a sine of y. It's only the y. It has to match this form exactly, the y to the first power, or a derivative of it to the first power. Okay, so hopefully that's clear. We'll look at some examples in a minute. If an ordinary differential equation is not linear, we call it nonlinear. So that just means it's not linear. And we're only going to be classifying differential equations as linear or nonlinear if they're ordinary. So only if it's an ordinary differential equation do we worry about is it linear or nonlinear. Okay, so let's look at some examples. We want to see, is it ordinary or partial differential equation? Is it linear or nonlinear if it's an ordinary one? And what's the dependent and independent variables, and what's the order? So 4 things that we need to find. So let's start with what's the dependent variable and the independent variable. So our dependent variable in this first one, we're taking the derivative of x. So here we have the x, here we have a derivative of x, here's a second derivative of x. The dependent variable is equal to x. The independent variable is what you're taking the derivative with respect to, so it would be the t. The order, let's get that out of the way, the order is the highest order of the derivative that's present in the equation. Well, we have a first order derivative, but second order derivative, so this would be a second order differential equation. Okay. Ordinary or partial? Well, from this equation, it appears that the x only has the single independent variable t. At least that's all the derivatives that are present. And because they're using that dx dt instead of the del x dt, del t, then it's going to be an ordinary differential equation. Okay, so the last thing is it linear or nonlinear? Because it's ordinary, we can determine is it linear or is it nonlinear. Look at the dependent variable. Here's the x. Here's a derivative of x. Here's a second derivative of x. Each term containing one of those, the term itself with the dependent variable is only raised to the first power, and there's no functions of that multiplied by them. So this matches the form that was on the previous slide. So this is a linear ordinary differential equation of order 2. Okay, the next one. We can see first the dependent variable. What are we taking the derivative of? It would be the u. So the dependent variable is u. The independent variable in this case, it's what you're taking the derivative with respect to, which is x and y. So we have that u is a function of multiple variables, u of x, y. So we have partial derivatives, so it's a partial differential equation. What's the order? The order is the highest order of the derivative. We only see first order derivatives in this. They're both ones with respect to x and ones with respect to y, but we're only taking the first order derivatives. So the order is equal to 1. And since it's a partial differential equation, we don't classify that as linear or nonlinear. To the third one here. The dependent variable is y. The independent variable is x. We have a order 2, since we have a second order derivative. This is an ordinary differential equation. You can tell by the d instead of the del and the fact that we have the one independent variable. And we have, because this is an ordinary, let's classify as it linear or nonlinear. It's okay to have a second order derivative, but we cannot have this y cubed term. So this is a nonlinear ordinary differential equation of order 2. Okay. Next one, the dependent variable here is x. We're taking the derivative with respect to. The independent variable is t. Taking the derivative with respect to t, the derivative of x with respect to t. This is an order 1 differential equation because the highest order derivative is a first order derivative. There's no second derivatives here. This is a ordinary differential equation. You can tell by the dx dt. Okay, so it appears x is a function of one independent variable. And now we want to see, is it linear or nonlinear? Well, here's our first order derivative. I'm going to write it in the same format as the previous one. We've got a t cubed dx dt. A minus 1 times x equal to t cubed. So this looks like the previous form on that previous slide. This is that a sub 1 of x, of t. The t is the independent variable. Okay, x is the dependent, t is the independent. So this is that, a1 of t. This is the, I don't know if it was a1. Okay, it matches the order of the derivative. So a1 would be only in front of the first order. Well, that is. So this is your a1 of t. And this is your a0 of t. So a0 of t is the negative 1, which is just a function of t. And here is your, what was it, f of t? Capital F of t. So this matches the form of the linear differential equation. So this is a linear. Okay, and then the last one. The dependent variable is y. The independent variable is the x. This is an order 2, since we have a second order derivative in the problem. Always look at the highest order present. This is an ordinary differential equation because we were taking just ordinary derivatives of y with respect to x, one independent variable, and you have the d and not the del symbol. And so now let's see, is it linear? Look at the dependent variables. We have a y here, but we have a y times a dy dx, which this product makes it nonlinear. So we have a nonlinear ordinary differential equation. Now let's see, is there any other terms? This is the f of the independent variable, that's fine, and this is just a second order derivative. So it's just this one term that makes it nonlinear. Okay, let's review some of the concepts that we learned in the last section. An nth order ordinary differential equation will be an equality that relates the independent variable to the nth derivative, and usually lower level derivatives as well, of the dependent variable. So you're going to have the nth derivative of that dependent variable along with possibly lower order derivatives and the independent variable as expressions. So let's identify the order, the independent, and the dependent variable in each of these problems. Okay, in the first one, the independent variable. Look at the derivatives. We're taking the derivative with respect to x, since that's the variable in the bottom. So our independent variable is x. Our dependent variable, that's what we're taking the derivative of. So we're taking the derivative of y, right, with respect to x, and we're taking the second derivative of y with respect to x. So our dependent variable is y. And you notice you also have your y term here, and you also have expressions, coefficients, that are in terms of just that independent variable. So this one is one of those linear ordinary differential equations. Okay, the order. The order is the highest order of the derivative in that expression. So the highest order of derivative of the derivative of y with respect to x. And you can see that we have a second order derivative, so the order of this differential equation is 2. Okay, the second one. The independent variable, we're taking the derivatives with respect to t. So our independent variable is t. Our dependent variable, which is the function that we're taking derivatives of, we're taking second derivative of y. So our dependent variable is y, since that's what we're taking the derivative of. And you can see here that we also have another expression, another term that has just that dependent variable in it. Now notice this one would not be a linear differential equation because of this square root around this expression is equivalent to having that second derivative raised to a 1/2 power. And you still have the 1 in there also, but having it under the radical is equivalent to having a 1/2 power on that second order derivative. Okay, so the order of the derivative, what's the highest order derivative that we have? We have a second order derivative. So we've got a second derivative here. So the order is 2. Okay, and the third one here, our independent variable, what are we taking the derivative with respect to, would be t. Our dependent variable, what is it we're taking the derivative of? We're taking the fourth derivative of x with respect to t, so our dependent variable is actually x. Okay, so what order derivative do we have? Well, we have a fourth order derivative of x with respect to t, so our order of the differential equation is 4. Now notice on this one, our dependent variable is x, so we could rewrite this as that fourth order derivative of x with respect to t minus t times x equal to 0. This matches the form of a linear differential equation. We've got our highest order derivative. It's raised to the first power though, and it just has a coefficient of 1, which is a function of the t, the independent variable. Here's your just dependent variable x, and its coefficient is just a function of that t, that independent variable, and then 0 is just a function of t as well. So this is a linear differential equation, and the first one would have been as well. Okay, so now if you have an nth order equation, that means that your function is going to be relating x, which is the independent variable, y, which is the dependent variable, and derivatives of y with respect to x. So we could have a first order derivative, second order derivative, all the way up to an nth order derivative if it's an nth order differential equation. So you could write that, you know how we say that f is a function of x, or f is a function of y and x? So those are the notations we've used in the past. If you're talking about something being a function of x, y, a derivative of y, and multiple derivatives of y, you can just state what it's a function of. That just means it's going to be written as a relationship of those items in an equation. Okay, so now f is a function that depends on x, y, and the derivatives of y up to the order n, since we said it was an nth order equation. So we're going to assume that the equation holds for all x in some open interval. So when we have a differential equation and we're looking for a solution to it, we're looking for an interval, an open interval, where it's defined for all values in that open interval. So all values of that independent variable in the open interval. Okay. Now, in many cases, we're able to take that differential equation and actually solve it for that highest order derivative. And when you can do that, instead of writing it in this form here, which is that implicit form that you used back in calculus, you can write it this way, where you actually solve for the highest order derivative. And so if you have that term isolated, that means that what you have left is just going to be a function of x, y, and all the derivatives up to the nth, but not including the nth. Okay, so in this is actually called a normal form of a differential equation, when you can solve it for that highest order derivative and isolate it. So that'll be handy in some of the ways that we solve things. Okay, so definition. A function, remember, a function will be the solution to a differential equation. A function, and I'm just using phi of x, that when substituted in for y in the equation, and it can be either one of these two forms, either this one or this one, that satisfies the equation for all x in the interval, is called an explicit solution to the equation on that interval. So an explicit solution is just one where you have the y, or phi of x, solved for. Okay, so now let's look at some solutions and see if they really do satisfy the differential equations. So I want to show that phi of x equal to x squared minus x to the minus 1. So that's equivalent to x squared minus 1 over x. I want to show it's an explicit solution to this linear equation. So you should recognize that as a linear equation, and you should recognize this as a explicit solution. You just think of it as y equal the x squared minus the 1 over x, and you're just going to plug that in for the y into that differential equation. So now to plug this into the differential equation, we've got to find the second derivative of y. So let's find some derivatives. I'm going to use this form of it to find the derivative. So I know that y prime will be 2x plus 1. Remember, take the negative 1 times the negative 1 in front of the x, and then x to 1 less power. So the first derivative is 2x plus 1 x to the minus 2. The second derivative, now this is equivalent, since I'm taking the derivative with respect to the independent variable x, this is the second derivative of y with respect to x. So that will be 2 minus 2x to the minus 3. So I'll just use the power rule for each of the terms. So now let's make sure it actually satisfies it. I take the second derivative, I'm going to subtract 2 over x squared times the y. Well, the y for this was x squared minus x to the minus 1. And that should come out to be 0 if that is a solution. So let's look at it. I'm going to go ahead. I need to either put my x's in the denominator if they have negative exponent, or I need to just work with the negative exponents. Let's just work with the negative exponents. I'm going to write this as 2 minus 2x to the negative 3. I'm going to write this as minus 2x to the negative 2, and I'm going to distribute it through the parentheses. Okay, so when I distribute this through the parentheses, remember when you're multiplying, if you have x to a power times another x to the power, the rule is to add the exponents. Okay, so I'm going to have 2 minus 2x to the negative 3, and then minus 2 x to the negative 2 plus 2, which will be the 0 power, and then distribute it with the second term over here. I'm going to have plus 2x to the negative 2 plus negative 1. So I've got 2 minus 2x to the negative 3 minus 2x to the 0 plus 2x to the negative 3. Now you'll see these two terms actually cancel out. X to the 0 is 1, so that's minus 2, and here's a plus 2, so that actually all comes out to be 0. So that means that this phi of x is a solution, an explicit solution, since we have the y solved for, to this differential equation. Okay, now let's check this other function and see that it's not a solution. Okay, so now let's look at psi. Psi of x equal to x cubed. This is the Greek letter psi. So using that for our y in the equation, we have y equal to x cubed. So again, I need a second derivative. So y, the derivative of y with respect to x is 3x squared. And the second derivative of y with respect to x would be equal to 6x. Substituting into the equation, we're going to have 6x minus 2 over x squared times the y, which was x cubed. And we want to see if that comes out to be 0. So 6x minus x squared will cancel. We'll have 2x, which comes out to be 4x, which is not 0. So that means that psi of x is not a solution. To this differential equation. Okay, now let's show for any choice of constants C1 and C2 that this function is an explicit solution to this linear differential equation. Okay, so this is what we're going to use for the y in our differential equation. So we have y equal C1 e to the minus x plus C2 e to the 2x. So we need a second derivative and we need a first derivative. Y prime will be minus C1 e to the minus x. Remember, the derivative of e to the minus x is e to the minus x times negative 1. And then plus the derivative of e to the 2x is e to the 2x times 2. So we'll have plus 2 C2 e to the 2x. Second derivative will be positive C1 e to the minus x. And then plus 4 C2 e to the 2x. So now substituting into our differential equation, the second derivative, C1 e to the minus x plus 4 C2 e to the 2x, and then minus y prime, which is negative C1 e to the minus x plus 2 C2 e to the 2x, and then minus 2 times y. Y is C1 e to the minus x plus C2 e to the 2x, and that should come out to be 0 if this is really a solution. So removing parentheses, I've got C1 e to the minus x plus 4 C2 e to the 2x plus C1 e to the minus x. I'm distributing this minus through the parentheses, and then minus 2 C2 e to the 2x. Distribute the minus 2 here through the parentheses. Minus 2 C1 e to the minus x minus 2 C2 e to the 2x. Like the like terms, there's a e to the minus x's. We've got 1 C1, 2 C1, and minus 2 C1. So we have 0 e to the minus x's. Let's look at the e to the 2x's. And we'll have 0 e to the 2x, which gives us 0. So this indeed is a solution, an explicit solution to this differential equation. And notice it didn't make any difference what those constants are. Sometimes the constants have to have specific values, but to determine those values, we usually need to use an initial condition, and we'll get to that in a little bit. Okay, when we solve differential equations, we may not always be able to get an explicit solution, but we often can get an implicit solution, which is just as good. So let's show that the relation y squared minus x cubed plus 8 equal to 0. Notice that that's an implicit equation. We want to show that it implicitly defines a solution to the nonlinear equation dy dx equal to 3x squared over 2y. Now notice it would be nonlinear because if we multiplied both sides by 2y, you would have 2y dy dx equal to 3x squared, and to have a linear equation you can't have a function of y multiplied by a derivative of the y. So this is a nonlinear equation. Okay, so now to show that this relation defines a solution implicitly, we need to find what the derivative of the y is with respect to x. Now we have a couple ways to do that. This one's relatively easy to actually solve for the y, so let's do it that way. So take this, solve it for the y. We'd have y squared equal to x cubed minus 8. So that means you have two actual implicit equations that result from this relation. You have that y is equal to the positive square root of x cubed minus 8, and you have y equal to negative the square root of x cubed minus 8. So both of those would satisfy this equation. So let's just pick one of these and show that it actually is a solution to the differential equation here. So let's use the positive one here. Y equal to the square root of x cubed minus 8. So that's y equal to x cubed minus 8 to the 1/2 power. So dy dx would be 1/2 x cubed minus 8 to the negative 1/2 times the derivative of the inside, 3x squared. So that would be, I take this x cubed minus 8 to the denominator, that would be 3x squared in the top over 2 times the square root of x cubed minus 8. Okay, so now let's see if that actually satisfies this. I'm going to replace the left side with this. So I'm going to have 3x squared over 2 times the square root of x cubed minus 8. And I want to see if that's the same as 3x squared over 2y. So 3x squared over 2 times the y. Well, the y that we're using is this one right here, square root of x cubed minus 8. And you can see that those are the same. So this does define, this relation defines two different implicit solutions to this differential equation. And I'll leave it to you to go through and verify that it also works for the negative square root of x cubed minus 8. Okay, now notice also that both of these are defined on the open interval 2 to infinity. Notice that x cannot be 2 for this to exist. The derivative here would not exist if x was equal to 2 because you would have a denominator of 0. So we can define the solution then on the open interval from 2 to infinity since the 2 is not included. You could also use minus infinity to minus 2 for that interval as well. Okay, so definition. A relation is said to be an implicit solution on the interval I if it defines one or more explicit solutions. The previous example here, we had two explicit solutions that were defined by this one implicit relation. Okay, now let's show that this is an implicit solution to the nonlinear equation. Now notice again, this is nonlinear because of this y e to the xy term in a couple different places. Now this one will be much more difficult, but we can't solve it for y because of the two places that it's located. So let's just take the derivative of that and find dy dx by taking the derivative implicitly. So remember back in calculus 1, you took the derivative of both sides. Now our independent variable is x, our dependent variable is the y. So we're going to take the derivative with respect to x of both sides. So x plus y plus e to the xy equal the derivative with respect to x of the 0. On the left, we have a sum of terms, and the sum rule tells us that we would take the derivative of each one. So that would be the derivative of x with respect to x plus the derivative of y with respect to x plus the derivative of e to the xy with respect to x, and then the derivative of 0 on the right side is just simply 0. Well, the derivative of x with respect to x, since x is our independent variable, is just 1. The derivative of y with respect to x, remember y is a function of x, so we just leave that as dy dx. And now the derivative of this term with respect to x, the derivative of e to the xy is e to the xy times the derivative of that exponent. Let's take an extra step to do that. And so we're going to have 1 plus dy dx plus e to the xy times the derivative of xy. Since it's a product, we'll need the product rule. So it would be the x times the derivative of the y with respect to x plus the y times the derivative of the x with respect to x. Okay, so we've got 1 plus dy dx plus x e to the xy dy dx plus y times e to the xy, and notice that the derivative of x with respect to x is simply 1. Okay, so now I'm looking for dy dx to see if this actually, well, if you notice, if I just factor dy dx out of the two terms here that have it in common, I have dy dx, coefficient here is 1, plus x e to the xy, so that takes care of this term and this term, and then I have plus the 1 here at the beginning, and then plus y e to the xy. So the derivative is exactly this differential equation. So it clearly would satisfy that differential equation. So we've just shown that that is an implicit solution of that nonlinear equation. Now in this next example, I want to show that for every constant c, this relation will be an implicit solution. So here's my differential equation. To take the derivative of this, we can just do it implicitly. So the derivative of this will be 8x minus the derivative of y squared, which will be 2y times the derivative of y. Got to use the chain rule since y is the dependent variable, equal the derivative of the c, which is 0. I'm just taking the derivative of each of the terms in the equation. Now notice that if I just divide both sides through by -2, I'll have negative 4x plus y dy dx equal to 0, which is exactly this differential equation. So it clearly is an implicit solution, and it didn't matter what the c was. It was going to be a solution for any value of c. So now let's look at just a few values of the c. If c is equal to 0, this equation becomes 4x squared minus y squared equal to 0, which is equivalent to y squared equal to 4x squared, which is y equal the plus or minus square root of 4x squared. So that'll be the square root of 2x, well, square root of 4x squared, which will be 2x, and y would be equal to negative 2x. Okay, so we have these two implicit solutions. Now those are just lines going through the origin. So y equal 2x looks like something like that. Y equal minus 2x, like that. I'll show you a graph on the next slide. Okay, now let's look at c equal to 1. Or let's do c equal 4. If you use c equal 4 in this equation, you've got 4x squared minus y squared equal to 4. Okay, now if you recognize this form, when you have the x squared and the y squared and they have opposite signs, this is going to be a hyperbola. And to find the standard form, you want a 1 on the right side. So I'm going to divide everything through by 4. So I'm going to have x squared minus y squared over 4 equal to 1. Now this, because the x squared is the positive one, that means there's going to be x-intercepts. Okay? The the a squared is the number underneath that positive term. So the a here is equal to 1. Okay, a squared is 1, so the a would be 1. The b squared is the 4 here, so the b would be equal to 2. That tells you where to go to get the vertices and where to go to get the asymptotes. The asymptotes were the b over the a. So I know it's going to pass through like this. Now what I'd actually do is I would use the b to go up 2 and over 1. I'm doing the b over the a, and that gives me asymptotes, which look something like this. And that's going to allow me to actually use those to sketch that graph. Okay, so that's just approximation, and you can do the same thing with these other values. All of them are going to be hyperbolas. And so what we get would be this family of solutions. You can see the two intersecting lines in the middle. Those are two separate functions. But then you have hyperbolas for the other solutions. So you've got the ones coming this way. That was where that c was positive. When the c was negative, they're going to go in the opposite direction. Okay? And you've got the intersecting lines for when c was 0. So this is called a one-parameter family. One parameter because there was a single constant of integration, c, which resulted from having that one single-order derivative. Okay? If you remember before, when we had a second-order derivative, we had two constants of integration. So in general, when you solve nth-order differential equations, you're going to have n arbitrary constants. And if you want to find a specific solution, just like we did here, we had to find values for that parameter. Okay? So if you're going to have n different parameters, n different constants, you're going to have n different values to be able to resolve those n parameters in that general solution. But if you end up having n initial conditions, those will help you to resolve and find a unique solution in most cases. So next we're going to look at actually finding unique solutions to initial value problems when you're given those initial conditions for the differential equation. Okay, when they tell you you have an initial value problem, that just means that you have a differential equation and you have initial conditions. Okay, so an initial value problem for an nth order differential equation means that your differential equation is of this form. So it's going to be a function of the x, the independent variable, the y, which is the dependent variable, and derivatives up to the nth order derivative of y. Okay, now to solve the initial value problem, what they want you to do is to satisfy the n conditions at a certain point, an initial point, some x naught. So they're going to give you the y value for x naught. They're going to give you the derivative at x naught, all the way up to the n minus first order derivative at x naught, so that you'll have values to go along, you know, for each of those, the y value, the derivatives value, and so on, at a given x naught. So initial value problem means that you've got this unique x naught. Later they'll have boundary value problems where they won't have all the conditions for that same x value. So now, if it's an nth order differential equation, that means that you would have n of those parameters, the constants of integration. So you're going to need n different conditions to be able to resolve those in most cases. So this is an initial value problem. So this first example, I want to show that this phi of x equals sine of x minus cosine x is a solution to this initial value problem. So what is an initial value problem again? It's a differential equation, and because it's a second order, I need to have two conditions at that same initial point, and they're giving me the x value of x equals 0 for those initial conditions. So let's show that it's a solution. We just want to show that this is the y and that it actually satisfies that differential equation. So if y is equal to sine of x minus cosine of x, that means y prime will be cosine of x minus a negative sine of x, so plus sine of x. And again, we need the second derivative in this equation. So we'll have minus sine of x plus cosine of x. So now let's just substitute in to the differential equation. We want the second derivative here. So it's going to be minus sine of x plus cosine of x plus the y value, which is sine of x minus cosine of x. And it should equal to 0 if it satisfies it. And you'll see these sines cancel and the cosines cancel. So we do get 0 equals 0. So that proves that it is a solution. Now, is it a solution to the initial value problem? This says that the y value when x is equal to 0 needs to be negative 1. So y of 0, that just means to take this equation and plug in x equal to 0, will be sine of 0 minus cosine of 0. Well, sine of 0 is 0, minus cosine of 0 is 1, so we get negative 1. So that matches. And now the derivative, we want y prime of 0. So just take the derivative and plug in 0 for the x. So cosine of 0 plus sine of 0. Cosine of 0 again is 1. Sine of 0 is 0, and you get that it's 1. So it does satisfy those two initial conditions. Okay, we've got an example here that's a solution to a differential equation, second order linear differential equation, and it says it satisfies it. I think we checked this one a while ago. We showed that it satisfied it for any choice of the two constants. So now I want to find what would the specific solution, we've already shown this is a solution to this differential equation. I want to show what is the specific C1 and C2 that would make it satisfy these two conditions. So we have that y is equal to C1 e to the minus x plus C2 e to the 2x. And I know that when I plug in x equal to 0, the y should be 2. So that says that 2 is equal to C1 e to the 0 plus C2 e to the 0, or simply that 2 is equal to C1 plus C2, since e to the 0 is 1. Okay, now this says that if I took the derivative and plugged in 0 for x, I should get negative 3. So let's find y prime. So for this particular y, this is y prime is equal to minus c1 e to the minus x plus 2c2 e to the 2x. And so now plug in 0 for the x into the derivative, and the derivative should come out to be the negative 3. So I'll have negative 3. Let me go ahead and write the equation down. I have y prime equal negative c1 e to the minus x plus 2c2 e to the 2x. So the y prime is negative 3 when I plug in x equals 0. So I've got negative 3 equal to negative c1 plus 2c2. So what I've got now is I've got a system of equations. I need to find c1 and c2 so that both of these two equations are true. c1 plus c2 equal to 2, and negative c1 plus 2c2 is equal to negative 3. Now, it's already set up where you can just do elimination by adding the columns. So that the c1's cancel, we get 3c2 equal to negative 1. That means the c2 needs to be negative 1/3 for these two conditions to be satisfied. Okay, now let's find the c1. So if I just take either one of these two equations, I'll just take this one. c1 plus c2, which is negative 1/3, has to be 2. So that means c1 will be 2 plus 1/3, which 2 is 6/3, so that'll be 7/3. So the specific solution, the phi of x, that satisfies these two initial conditions as well as the differential equation would be 7/3 e to the minus x plus negative 1/3 e to the 2x. And so that's your specific solution to the initial value problem. Okay, now when we're solving differential equations, one thing that would be nice to know in advance is actually, does a solution exist? We'd like to know that a solution exists, and we'd like to know that it's a unique solution so that if we find one, we'll know that we have the only solution. So when we have an initial value problem given by dy dx equal f of xy and the initial condition is that y at x naught will be y naught. So if you have this initial value problem and this function, whatever this expression is on the other side of the equal sign from the dy dx, that's our function f. If that function as well as the partial derivative of that f with respect to y are both continuous functions in some rectangular region that contains x naught, y naught, so if we got some point x naught, y naught, we need a rectangular region. So from an x smaller than x naught to an x bigger than x naught, and then likewise from some y value above to a y value below. So if we have a rectangular region where the function f and its partial derivative are continuous, then the initial value problem will have a unique solution on some interval around that x naught. So for all the x's between the x naught, so if this is our x naught, go delta this way, so here's x naught minus delta to x naught plus delta. We know that for all x's in between there, that there will be a unique solution. Okay, so let's see how we can verify a unique solution exists. Okay, so does Theorem 1 tell us that there's going to be a unique solution for these initial value problems? So the first thing we want to do is we need to look at what the f of xy is. F of xy is the derivative. So solve for dy dx, and it's that f of xy. It'll be a function of x and y. And we're only looking at first order differential equations. So dy dx for this first one will be x squared minus x times y cubed over 3. Okay, now this derivative exists for all x and all y. So dy dx, which is that f, it's that f of xy, it exists and is continuous. It's just a polynomial, exists and is continuous in any interval around the point 1, 6. So all intervals containing x equal 1, and so it would be all rectangular regions containing 1, 6. So all intervals containing x equal 1 and all rectangular regions containing 1, 6. Okay, so now let's also look at the partial of f with respect to y. Okay, so here's our f. Take the partial derivative of that with respect to y. Now let me rewrite this to split that 3 up. This is x squared over 3 minus xy cubed over 3. So taking the derivative with respect to y, remember that the x then is just a constant. So the derivative of x squared over 3 is a constant, so it has a derivative of 0. The derivative of xy cubed over 3, we have x over 3 is a constant, and then the derivative of the y cubed is 3y squared. So that comes out to be just minus xy squared. And that partial derivative exists and is continuous for all rectangular regions in the xy plane as well. And obviously that contain the point 1, 6. Okay, so by Theorem 1 then, as long as f, this function was continuous for a rectangular region around 1, 6, and the partial of f with respect to y, which was this function, those are both continuous for all regions that contain 1, 6, then by Theorem 1, there is a unique solution, and it obviously exists then. So therefore, a unique solution exists to the differential equation, to the initial value problem. So it's not just a differential equation, but it also has to satisfy this initial value, passes through the point 1, 6. Okay, now the second one. first check f of xy. Well, in this case, f of xy is the 3y to the 2/3. And this exists for all y values. So this is continuous. For all regions containing the point 2, 0. Okay, now let's look at the partial of f with respect to y. That would be 3 times 2/3 y to the negative 1/3, which would come out to be 2 over the cubed root of y. Well, the partial derivative of f with respect to y does not exist when y is equal to 0. So since the point that we're interested in is the point 2, 0, and this partial derivative doesn't exist anytime y is equal to 0, which means any point along this x-axis, it does not exist, then that means that there is no region containing 2, 0 for which this partial derivative would exist. So there is no rectangular region containing 2, 0 for which or where the partial of f with respect to y exists. So that means that you're not guaranteed a unique solution. So no guarantee of a unique solution. Or any solution for that fact. Now it ends up that this one does have actually multiple solutions. So because of that condition, we're not going to have a unique solution, but we do end up with multiple ones in this case. Okay, so let's look at the next one. The same derivative, we now have changed the point. So we're still dealing with our function f of xy, which is 3y to the 2/3, which again exists and continuous for all rectangular regions containing 2, 0. The partial of f with respect to y, again, is 2 over the cubed root of y, which again is not continuous on the x-axis when y is equal to 0. So that means since it doesn't exist when y is 0, and we were looking at the point 2, 0, there couldn't have been a region around it. But now we're referring to the point 2, 1. So the point 2, 1 isn't on the x-axis. So there is a rectangular region containing that point for which that partial derivative and the function f would be continuous. So for that reason, there is a unique solution in some interval around x equal 2. You know, as long as that interval doesn't go down and touch the x-axis. Okay, so here in this case we do have a unique solution. In the last section, we looked at the existence and uniqueness theorem, and that told us when we had a solution and whether it was unique or not. Now that's nice to know, but sometimes we want to know more about the nature of the solution. Like, can we find a value of a solution at a certain point, or where the solution's increasing, or where it has its maximum values? Now, if we had the explicit solution, we would be able to get that information. But in most real-world problems, we're not going to be able to actually get a formula for the solution. But what we can do is we can find information about the solution from the differential equation. So one technique that's helpful in visualizing the solutions is to sketch the direction field for the equation. So take a first order differential equation that's in normal form, like this. Remember what dy dx tells us. Dy dx tells us the slope of the tangent line at each point. So what we can do if we have a differential equation in this form is we can get what the slope of the tangent line is for every point in the xy plane. So a plot of short line segments drawn at various points in the xy plane that show the slope of the solution curve is called a direction field for that differential equation. And we're going to use those direction fields to be able to visualize what the solution is going to look like. Okay, so now let's consider this differential equation in normal form. If I just pick some random points, let's say I'm going to pick the point 1, 0, then I know that the slope of the tangent line at that point, just by plugging in x equals 1, y equals 0, is going to be 1. Think about a slope of a tangent line. Remember, slope is rise over run. So for every 1 unit you go up, you're going over 1. So up 1 over 1, the slope of the tangent line would look like that. So at the point 1, 0 on the graph, I'm going to draw a little line segment that matches the direction that that solution curve is going to take. Let's say at the point 0, 1. Well, plug in x equals 0, y equals 1. You get that the slope of the tangent line at that point is -1. So rise over run is down 1 to the right 1. So the graph of the lines, the tangent line, will look like that. So the solution curve will be moving in that direction at that point. So at 0, 1, I would put a little line segment matching that slope. And you could continue that all day, and it would take you an infinite amount of time to do that. But notice as your x gets bigger, the slope's going to get bigger. And you can see how these tangent lines are getting to be steeper and steeper. Remember, the bigger the slope, so slope of 1 will be like that. Slope of 2 would be up 2 over 1. The steeper, the bigger in absolute value that slope gets, the steeper that tangent line will get. And you can see all those little mini tangent lines in that direction field. Okay, so now let's use that to actually sketch some solutions. Take a starting point. So let's just pick the point 0, 1. And I'm going to follow the flow that those tangent lines are giving me. So at this point, I need to be moving in that direction. I'm going to start kind of leveling off down here. This isn't going to be real smooth since I'm writing on this. But then it's going to be moving upward. I'm trying to match the flow. And the further to the right I go, I see that they're getting steeper and steeper. And I can move backward the other direction. So matching the slopes over here, it looks like it's moving something like that. Now, somewhere in here, it's kind of hard to tell for sure, but it could be going this way. So just depending on where you start, you're going to have, a sketch of what the solution curve looks like. And notice if I'd started down here, let's say I start at this point, I'm going to follow the flow. These are rising really steeply. And as I get up here, I'll start going up steeply as well. So you can get the graph or approximate graph of a solution curve just based on where the starting point is. Okay. Now this particular differential equation, if you check the existence and uniqueness theorem, there is, this was your f of xy, which is continuous for all points. And if you took the partial of that f with respect to y, it comes out to be -1, which is also continuous. That means that for any starting point, there will be a unique solution curve. Okay, so now let's look at a couple more. Let's say dy dx is equal to -2y. Again, the derivative is continuous for any point, and the partial of it with respect to y would be -2y, so it's also continuous. So we know that there will be a unique solution, and it exists, passing through any point. Okay, so a computer has created this direction field. It's a very tedious process, so we'll use the computer, graphs here. I want the solution curve as you pass through the point 0, 1, which would be right here. So just follow the flows. Now you could plot at 0, 1, you can see that the slope would be -2, so it's kind of going up steeply. As x gets bigger, notice in this one, there's no x in the differential equation. That means x is irrelevant. So if we plugged in y equals 0, we're going to have slopes that are 0. So every point here along the x-axis where y is 0 have a slope of 0. Every point where y is 1 will have a slope of -2. Notice all these little slopes are -2 along that same horizontal line. For every horizontal line, since that designates a specific y value, you're getting a unique slope. So the slope will be the same for every horizontal line that you have here. So if I were graphing the solution curve through the point 0, 1, I know that it's going to be going down. The slope's -2 at that point. It's going to keep going down, and notice as it gets closer to the x-axis, it's going to be leveling off. With a slope of 0 on the x-axis, that means if it hits the x-axis, it's just going to level off there. But this one actually has an asymptote as it gets closer to the x-axis. If you go back the other direction, it's just going to start rising. So as the x gets smaller, the x doesn't make any difference, but as the y is getting larger, that slope is getting larger, and it's in the negative direction, so it is decreasing from left to right. So that would be the graph of our solution curve. Now, we actually did this problem previously, and we found that this was the radioactive decay problem. The solution actually came out to be y equal to c e to the -2x, where the c depended on what that initial value was, where you were starting. So remember a graph of y equal e to the -x? If you remember that graph from algebra, it looks like this. So the -2x will affect the steepness a little bit, but it's going to pass through the point 0, 1, and all those solution curves will look very similar. Just depends on where they start. Okay, so now the next problem. dy dx equal to -y over x. Okay, let's look at the uniqueness first. This is your f of xy, and it will be continuous as long as x is not 0. Okay, so as long as our starting point doesn't have an x value of 0, we will have, well, let's go ahead and check the partial derivative of that. The partial of f with respect to y would be -1 over x, which again is continuous as long as x is not 0. So if x is not 0, we will have a unique solution, and we know it exists. Okay, so that means if x is 0, we don't necessarily have a unique solution or the existence of one. Okay, so now let's look at the solution curve through the point 1, 1. Okay, so we see it's going down at that point. Actually, slopes -1. And as we go further to the right, you can see it's starting to level off. Okay. As you go the other direction, as you get closer and closer to x being 0, this function, as x goes to 0, is actually approaching infinity. Okay, so you'll see that the graph will just start going up, and it will not cross over the line where x is equal to 0 since it doesn't exist there. Okay. Now, the solution to this equation is actually of the form y equals c over x. Okay, and you can see that as x gets closer to 0, the curve is blowing up over here, and over on this other side, it's going toward the line y equals 0. Okay, now notice though, if c is equal to 0, this just becomes y equal to 0. Okay, now if you look at this differential equation, if y is equal to 0, the slope is actually 0. So that means along the y-axis, or along the x-axis, the slopes of the tangent lines are all 0. So if we start there, we're going to stay on that axis. So the solution curve would be y equals 0. That's one possible solution curve. Okay, so if there's actually two solution curves if y equals 0, but we don't have uniqueness if the x is equal to 0. Okay, now okay, this is just a graph of the ones that we just did. So here's the solution curve of minus 2y. That was that exponential function that was going down. And then here was the one that was passing through 1, 1 you can see how it is blowing up as you get closer and closer to x equals 0, and it's going down toward the x-axis as you go further, as x goes toward infinity. Okay, so now let's look at another problem. Okay, so this direction field, we actually looked at this one earlier to see if there was a unique solution. This function f of xy is continuous, but when we took the partial of the f with respect to y, we got that it was 2 over the cubed root of y. Okay, so it would be 2y to the negative 1/3. Okay, which is not continuous when y is equal to 0. Okay, so the uniqueness theorem or existence theorem failed in that case. Well, it ends up that there's actually two solutions going through a single point. So as long as the y was not 0, we did have a unique solution. But we were specifically looking at curves going through the point 2, 0 where the y was 0. And because the y was 0, it failed the uniqueness. There's actually two solutions that go through that. One of them is just simply y equal to 0. And you can see what the slope would be here. If y was equal to 0, the slope of all the tangent lines is just along the x-axis. So if the graph y equals 0 just passes right through there. So there's one solution, y equal to 0. But another solution is a little harder to actually see through this this direction field. The other solution is y equal x minus 2 cubed. Okay? So now if you were looking at the point 2, 0 and trying to find a graph, a solution passing through that point, if you could get off of the x-axis, you would see that it would just start going up like this. Or if you went down below it, you would see that it would start going downward like that. The tricky part is if you were just going by the direction field, you could think that it would just come up and just kind of stop. You don't really know that it's going to go ahead and go upward without knowing what the solutions are in this case. So direction fields are nice. They help to kind of give us a nice little sketch, but they're not sufficient to know for sure where a unique value is, especially if there's going to be more than one value. So it could take some turns that we just don't anticipate because we're not able to possibly graph every single slope at every single point. Okay, so use them sparingly, but they're a nice way to visualize a graph. Okay, the logistic equation of the population P at time t of a species is given by this. Okay, that's telling us that the rate of change of the population over time is P times 2 minus P. Now, we want to use the direction field here to answer these questions. If the initial population is 3,000, notice in the graph that P is given in thousands. So for a population of 3,000, that means that P would be equal to 3 in the graph. Okay, so we're starting here. If we follow the slope, it's going to be decreasing still. And notice as it gets closer and closer to P equal 2, at P equal 2 here, the rate of change is 0. So if we can get down to that point, it won't be changing. It'll stay at 2. So at P equal 2, we've actually got an asymptote here. Okay, so the limit, the P values are approaching P equal 2 as t goes to infinity. So the limit of P of t is actually 2. Okay, which it represents 2,000 population. So now, can a population of 1,000 ever decline to 500? Now let's start at 1,000, which is where P is equal to 1 here. Okay, so what's happening at that point? It's going to be rising. this point it's still rising, but it's starting to flatten off, and it won't cross over p equal 2, but it's going to be rising, and p equal 2 is an asymptote again. Okay, so can a population of 1,000 ever get down to 500, which would be down here? And the answer would be no. So if the population starts below 2,000, it's going to rise until it gets to that point. Can a population of 1,000 ever increase to 3,000? So if it started at 1,000, it's not going to be able to get past that 2,000 point, because once it gets above 2,000, it's going to be decreasing by looking at those little line segments. So the answer to this one is no. Okay, so that limiting factor is actually p equal 2. That's what the limiting population. So whatever environment that you're at, it can only approach, it can only sustain 2,000 people. Now there's something interesting about this particular equation. Notice that there's no independent variable t on the right side. Okay, we also can see that when p is equal to 0 and p is equal to 2, we're going to have a rate of change of 0. Okay, so down here and here, we ended up with just horizontal line segments. Notice also that the t was irrelevant. Whatever the p-value was, like p equal 3, all of those little line segments along this horizontal line were the same. Likewise, p equal to 1, they're all the same. Okay, so this is a special kind of differential equation when the p, the dependent variable, is the only variable on the right side of it. And we'll talk about that in just a second. Okay, a differential equation is autonomous if the independent variable t does not appear explicitly. So in other words, while dy dt is a function of f of t and y, it's actually only a function of y. Okay, so now there's two features of this. One is the slopes of the direction field will all be identical along horizontal lines. Also, any new solution can be gotten from an older one by just replacing y of t with y of t minus t naught. In other words, there's just a shift. So whatever the graph is doing in one place, if you shift it to the right, it's going to do the same thing, because those slopes are identical across those, across the horizontal line. So the solution will be shifted depending on what the starting point is. Now those constant solutions, the places that cause this f of y to be 0, those are called equilibrium solutions. Okay, and they have a lot of interest in this autonomous equation. The equilibrium solutions, y equals c, it's called a stable equilibrium or a sink. Okay, and some textbooks will call this also attractors. So stable, attractors, or sinks. If the neighboring solutions attract to it as t goes to infinity. In other words, if it's an asymptote for those solutions. Okay? Equilibrium that repel neighboring solutions. So the y equals c is a stable or a sink or attractor if it attracts them. If it repels the neighboring solutions, those are called sources, or some textbooks call them repellers. Okay. Other equilibrium are the ones where it's either attracting on one side and repelling on the other, or vice versa. So the other equilibrium are called nodes, or some people call them semi-stable. Okay. So you've got your attractors, which are stable equilibriums. Okay. The sources and the nodes, people call, this textbook calls them unstable, but other textbooks will call both the sources and the nodes unstable. But be aware that nodes, where they're attracted on one side and repel on the other, are also called semi-stable in some textbooks. So nodes are the ones that are the semi-stable. Sources or repellers are the ones where everything's being repelled from it. And the stable ones are also called sinks. Okay, so let's look at a phase line, and this will be a lot clearer once we do that. A phase line looks at the zeros of that f of y up here. Okay, and it's going to look at the nature of the equilibrium solutions for that autonomous equation. So let's look at it for this previous problem that we did. Okay, so if I were drawing a phase line here, what I'm going to do is I'm going to first find those equilibrium solutions. The equilibrium solutions are p equals 0 and p equal 2. I'm going to put those on a vertical line. This is called a phase line. So I have 0 and I have 2. Now this particular problem, p can't be below 0. We can't have a negative population, so we wouldn't worry about anything below p equal 2. But if our population was between 0 and 2, what did we see happen? We saw that it was rising. Okay, and you can tell that by if you pick a number in here for p equal 1 and plug that into the differential equation, you're going to actually get a positive value, right? So in here, the dy dt, or dp dt, is positive. That means that it's rising. Okay? If you look at a value where p is bigger than 2, such as p equal 3, plug p equal 3 into the differential equation, you get that dp dt is actually negative. That means that it's falling. Okay, so this is a phase line. It's showing the behavior. It's falling or decreasing above p equal 2. It's rising or increasing above between p equals 0 and p equal 2. And that's exactly what those solutions are doing. Notice that they're rising. If you started anywhere in this region, they're going to be rising. Okay? If you start anywhere above 2, they're going to be falling. Okay? So what's happening at 2, this equilibrium point? It's an attractor. Everything's approaching it. Attractor, or it's also called that the sink. Or they just refer to it as stable also. So all those would be words that would be describing the equilibria at y equal 2, or p equal 2 in this case. Well, p equals 0 is a little unique because it doesn't have both directions, but you can see above p equals 0, it's actually being repelled. So we would call it a repeller. They would call it source, or even just a node if it's not doing the same thing on both sides. Okay, so we would call that either unstable or semi-stable because we don't really know what it's doing below that. So we'll look at another example where we'll be able to see both sides of it. Okay, so let's look at the phase line for this. First, find when the derivative is 0. So y prime is equal to 0 when y is equal to 1, 3, and 5. And this one will have values on all sides of those. Okay, so those are our three equilibrium. So now let's look at each one. If we want to see is it being repelled or attracted, we can do that by picking values in those intervals. So I'm going to pick first p equals 0. If I pick p equals 0 and plug it in, then y prime, so I would have negative 1, negative 3, and negative 5 squared, which comes out to be negative. Okay? That means that it's decreasing for values below 1. Now let's do the same thing for any value between 1 and 3. So p equal 2, or y equal 2. I'm back to my p's again. So these are y values, not p's. Okay, y equal 2, I would have minus 1, negative 1, negative 3 squared, which will be positive. That means it's increasing. So of any value between 1 and 3, it's going to be increasing. Okay, now between 3 and 5, let me just pick 4. Pick anything in that interval. When you put in 4, I'm going to have a negative 3 times 1 times negative 1 squared, which again is negative. Oops, y prime is negative. Okay, so that means it's decreasing. Okay, now let's look at p bigger or y bigger than 5. So let's pick y equals 6. So we'll have negative 5 times 3 times 1 squared, which will be negative. Okay, so that means it's decreasing. So now let's look at each of those equilibria. This particular y equal 5, notice that above it, it's coming toward it. So it's attracting it above, but then it's repelling it below. So this is one where we call it semi-stable, or we would just call it a node. On one side it's going toward it, the other side it's going away from it. Okay, at y equal 3. Now this textbook also calls this unstable. So if you had to pick between stable or unstable, you would say unstable here for this textbook, but other books call it semi-stable. Okay, y equal 3. Notice it's being approached from both sides. So this one we would call stable, or we might call it an attractor, or we would call it a sink. Okay, so all those terms are used to describe y equal 3, that equilibrium value solution. Okay, now let's look at y equal 1. Notice here they're both going away from it. So we would call this one unstable. We'd call it a repeller, or we would call it a source. Okay, so those are all just different ways that you might refer to it. Now let's look at what the solution curves would look like. So if you were looking in the xy plane, you would have horizontal lines at each of these values, because each one of these are where the slope is 0, so you're not going to have solutions crossing over these lines. So at y equal 1, y equal 3, and y equal 5. Okay, so now wherever your solutions start before that, we have a picture over here on this phase line. This phase line shows us the behavior. Okay, so if you started below y equal 1 here, it's going to be decreasing. So it's starting at y equal 1, but it's going to be going down, and we don't know how fast it's going down. Okay, if you start between 1 and 3, it's going to be rising. Okay, just looking at this behavior here. So it's going to start here, and it's going to be going up. Okay, so that tells you whether it's increasing or decreasing solutions in that band. Between y equal 3 and y equal 5, it's going down. So y equal 3 is an asymptote. It's approaching. And above y equal 5, you can see that it's going down again. So that's going to be what the graphs of these solutions. And now, depending on where you start, I mentioned before that when it's autonomous like this, that other solutions are just shifts of these. So while you might have one start here and end here, another one could start over here, but it's going to have the same behavior. So you've got that shifting going on horizontally along the t-axis. Okay, so this just gives you an idea about the behavior of the solutions, just based on when you have this autonomous differential equation. As you can see, if we were having to hand sketch a direction field, it would be very tedious. So fortunately, there are several software packages that are available to do that, so that's how you would normally do those. If you need to hand sketch something, though, there's a method of isoclines that helps to reduce the amount of work. Okay, so an isocline for a differential equation is the set of points in the xy plane where all the solutions have the same slope. Okay, so what it is it's essentially a level curve for that function. So now what we would do to actually graph it is we would pick some values of c for the level curve. So let's say we picked c equal to 0. And we want to find what are all the points that have a slope of 0. Well, for this particular differential equation, that means that x plus y would be equal to 0. Okay, so all those points will have a slope of 0. So now if I graphed this, this is just to graph the line y equal minus x. Okay, now let's pick another c value. C equal 1. Well, if we want the derivative to be 1, that means that x plus y is equal to 1. So that's just the line y equal minus x plus 1, which is just the line, it's parallel to this one, it's just passing through the line, the y-intercept of y equal 1. It's not easy to graph this. Okay, c equal 2. You want the slope to be 2. That's x plus y equal 2. All the points that satisfy this line will have a slope of 2. That's just every point on the line y equal minus x plus 2, which would be the line passing through, slope of negative 1 with the y-intercept of 2. And so on. You could do that, as often as you wanted to. Now let's actually put the slope on each of those lines. Okay, so the line y equal minus x, the slopes were all 0. That means every point on this line is going to have a slope of 0. So the direction field little line segment is going to be a horizontal line. Along y equal minus x plus 1, the slopes of all those are 1. And we know a line with slope 1 looks something like that. That's the slope of it. So we're going to draw that slope along all those lines, every point on that line. And this one, slope of 2. So we'll make it a little steeper. And just repeat that up and down that line. So you could do that to get a quick direction field, but you have to set constant values equal to the derivative and then graph the curves. They're not always going to be lines like that previous example, x squared minus y equal 1, x squared minus y equal 2. Those would have been parabolas that would have had that same slope along. So now let's look at the actual. So here's the graphs of all those isoclines. Each one of these, notice the slopes along each line will be identical. And then if you want to take that direction field, then you can graph some actual curves along, using that direction field. So that's just a way to get a quick and dirty direction field. So just find all the points that have a fixed slope and then just put those along that curve. Okay, now we're going to try to approximate the solution to differential equations using a method called Euler's method. Okay, so the idea behind Euler's method is to use tangent lines. We're given an initial value problem, which consists of a differential equation with an initial condition. So we have a starting point here, x naught, y naught. And this differential equation is giving us the slope. Remember that y prime is the slope of the tangent line. So the idea behind Euler's method is to take a starting point, calculate the slope at that point by plugging this point into the derivative function, using that slope then to draw the tangent line. So using this as a starting point and just projecting out the value of that slope. So we're just moving along that slope further to the left. We can now calculate the y value of the next x value. Okay, so we're going to first start by determining a step size. So we have our starting point, and we want to determine how far apart do we want to calculate those values. So we're going to have a step size, which we usually use h to represent that step size. So our first x value that we're going to actually get a calculation for, an approximation for, will be x1, which will just be the initial x plus that h value. And then once we get the y value there by using the tangent line's y value, we're going to repeat the process again by now using this as a starting point, calculating the slope at that point using the same function that we're given, the differential equation, and then we'll calculate the y value for that tangent line. So here's the tangent line starting at this point, and we'll approximate the y value, which will be the y value for that tangent line at this x. Now that x will just be the previous x plus that step size again. And then we'll just keep doing that. So we'll start with this as our starting point, calculate the slope using this differential equation, drawing the tangent line that would have that slope projected off to the right, and then we're going to calculate the y value for that tangent line corresponding to this x. So this will be our x3. The x3 is just the previous x2 plus the h value. And then we'll just get the tangent line's y value, and then we'll have the approximate y value for the solution. So it's a real simple process. So let's look at how we're going to get those y values. So we know how to get each of the x values just by taking our starting point and adding the step size h each time. Okay, to calculate the y value, we know that we have a starting point here. That's the point x naught, y naught, which is given by this initial condition. We know that the tangent line, so the line passing through that point with this slope, would be y minus the y0 equal to the slope times x minus x0. Now our slope here is the y prime, so it's just going to be the f at that initial point, using this function f over here. So if we're actually just trying to get the y value, the y will be the initial y value plus that slope at that initial point times our h, our step size. Our step size is just the difference in these two x values that we're going to determine those values. So that's just a step size that someone determines in advance. So here's our recursion. This is our formula to get the next y given the previous one. So if you wanted to keep doing that, so our first point here, we would find the y1. And that y1 we'll get by getting the previous y, which is the y0, plus the slope at the initial point times our step size. So now we have this point right here. We have the y value. We already know what the x value was. Then you repeat it again. I want the y2 starting at the point x1, y1. So the y2 will be the y1 plus the slope at that point at x1, y1 times that same step size, since we're always using the same distance apart on the x's. And then you would continue, so that if you're trying to find the nth y value, yn will be yn minus 1 plus the slope at that previous point, which is xn minus 1, yn minus 1 times the h. And so this is your recursion formula. You use this to calculate the x's, and then this is how you get the corresponding y's. And you just repeat that for each step size that you want to use. So let's look at an example. I want to use Euler's method with step size 0.1 to approximate the solution to this initial value problem. So this is our function. This is our f of xy that we use to represent the slope, because that is the derivative. Our starting point, this is your x naught, and here's your y naught. So our starting point, x naught, y naught, will be 1, 4. Okay, now we're asked to use the step size 0.1. So here we're looking at the x value of 1. The next one, we'll look at the x value of 1.1, and then we'll repeat that for x equal 1.2, 1.3, and 1.4. And finally, we get x equal 1.5. So this will take using the formula, 5 different times. We already know the value when x is 1. We're given that when x is 1, the y is 4. So now, using this formula, y of n is the y of n minus 1, the previous one, plus the slope at x of n minus 1, y of n minus 1, times the step size, the h, which in our case will be 0.1 each time. Okay, so this will change. It'll be the y value of the previous point each time, and then this will be the slope, the derivative, at that previous point. So first, our previous point is 1, 4, and that was when x was equal to 1. So let's just put that, here's our point, 1, 4. So our y of 0 is 4. Now let's look at x equal 1.1. We want to find the y corresponding to that. So the y will be equal to the previous y, which is 4, plus, now we want the slope at 1, 4, the previous point, times the point 1. So this will be 4 plus, now the slope, which is the derivative at 1, 4, we get by just plugging it into this. So we'll have 1 times the square root of 4, and then we have our times 0.1. So we have 4 plus, this will be 2 times 0.1, it'll be 0.2. That gives us a y value of 4.2. So now we have the point 1.1, 4.2. Okay, now we repeat using x equal 1.2. We want to find the y value when x is 1.2. So the y value will be the previous y value, 4.2, plus the slope at 1.1, 4.2, the previous point, and then times our step size, 0.1. So that's 4.2 plus, this will be 1.1. I'm using the derivative formula. I'm going to put that in green just to highlight it a little bit. 1.1 times the square root of 4.2, and then times our step size, 0.1. Okay, so that calculation, you'll need a calculator to determine that. That comes out to be 4.42543 if you carry it out 5 decimal places. X equal 1.3. So let me go ahead and record this over here. It's getting bigger. Okay, now the y for x equal 1.3 will be the previous y plus the slope at that previous point times the step size, which will be, we'll run out of room here. Okay, so that slope, we'll plug in that point into the derivative formula. 1.2 times the square root of 4.42543, and then times our step size. Okay, and that comes out to be 4.67787. 1.4, so we've got this point here now, 1.3, 4.67787. Now for x equal 1.4, find the y value. By using the previous y value, 4.67787, plus the slope at the previous point. I'm going to skip this step here and I'm going to go straight to using the formula up here. So I'm going to have 1.3 times the square root of 4.67787, and then times our step size of 0.1, and that comes out to be 4.4. Okay, now we're finally on the last one. We have x equal 1.5. We're going to use the previous point that we just calculated, which is 1.4, 4.95904 for the y value. And so the y for x equal 1.5 will be the previous y value plus the slope at that previous point, which will be 1.4 times the square root of 4.95904, and that's just by using this formula that we're given, the differential equation, which is the slope of tangent lines, and then times our step size, which is 0.1, and that comes out to be 5.270804. Okay, so that gives us an approximate value then for y, the function y, that's the unknown in this differential equation, at the value of 1.5 for x. Okay, now if you want to actually calculate out and see what the actual answer is, we'll be able to solve this differential equation when we get to chapter 2 in section 2.2. This is what's called a separable equation. Okay, and we'll see in chapter 2 that the solution, the actual solution to this, is x squared plus 7 squared over 16. Okay, so if you calculate what that function's value will be at each one of these x values, you can see how close our approximations are. So we have that on this next slide. This will have the values that we just calculated using Euler's formula, and it has the exact values using that function, the phi of x, which is the exact answer to this differential equation here with that initial condition. Okay, and so you can see that when we were at x equal 1.1, it was a very good approximation. Even at x equal 1.2, we had the first decimal point accuracy correct. But notice the further we get away from the 1, which was our initial condition, so we started here with the exact value, the further away we get, the farther away our answers in the approximation are. So they're still pretty good, but they're going to be further away from the exact answer than the ones that are closer to that initial value. And if you think about it, remember when you had a curve back in Calculus 1, if you took the tangent line at a point, really close values of x to this, where this point was located, will have very close to the exact function's value. See how that tangent line almost coincides with the values of the function near the x naught. But of course, the further the x value gets this way, the farther you would expect the function's value to be from that tangent line's value, which is what Euler's method's using. Okay, so it would work perfectly if it was actually a line, but if it's a curve, it's going to have a worse approximation farther away from that initial condition. Okay, let's look at one more example, at least the start of this example. We're going to use Euler's method to approximate the solution of this initial value problem. Now, this is a very common, the simplest form of differential equation. We want to know the function whose y value is the same as its derivative. And so if you recall, the function that has that derivative, that it's itself, is just e to the x. And you'll see here the initial condition, when x is 0, the y value is 1. So this satisfies the initial condition 0, 1. So we're going to use this also to check our answer, our approximation with the exact answer. So what I want to do here is we're going to start with the x value 1. That's what we want to approximate the differential equation at, the solution at. We want to know what is the e to the 1. Okay, so we already know what that is. It's 2.71828 and dot, dot, dot. So I want to do it by looking at various number of steps. So we're going to use one step to begin with. That means we're starting at the starting point 0, 1. There's our x naught and our y naught. And we want to find the y value at x equal 1 with just one step. So we'll call this n equal 1. Okay, so that means that we're going to go from x equals 0 to x equal 1, letting this be our h. So one step. So we're just going to get the initial point, and we're going to get a tangent line based on what the slope gives us, and we're just going to get the y value at that point. Okay, so remember the recursion formula that we're going to use. The recursion formula is y of n is the previous y value plus the slope at the previous point times the step size. So in this case, since we're doing it in just one step, and we're going from x equals 0 to x equal 1, our h value is just going to be 1. Okay? So our y value then, so y1, which will be the y value when x is 1, will be the previous y, which was 1. The slope, now this slope is the same thing as the y value itself. Okay, so that means that when we plug this point 0, 1 in, we're only plugging in the y value. So that will be just 1 times the step size, which is also 1. So our y value comes out to be 2. So if we use a step size of 1, then the x of 1, the y of 1, the x value is 1. So y of 1, for when the x is 1, will come out to be 2. Okay, so now let's look at using two steps. Okay, so what that means is that we're going to calculate it here and here. So we're going to have two steps. So our h then will be 0.5. So we're still at the same starting point, but now we're going to use n equal 2 steps. So that means our h value will be 0.5. Now you can get that by just taking the 1 minus 0 divided by the number of steps. Okay? Okay, so the y value then, we're going to find the y value first at 0.5. So y1 will be the previous y, which was 1, plus, again, the slope. This slope here is the y value of the previous point. So it'll be 1. And now our step size is 0.5. So this will be 1.5. But we need to find y2 because that will give us the y value when x is 1. So this was the y value when x was just 0.5. And now here's the y value when x is 1. So we'll take the previous point that we just calculated to be 0.5 was the x and 1.5 was the y. So that's our x1, y1. So y2 will be the previous y value plus the slope, which is the previous y value based on this differential equation. And then our step size is 0.5. So this will be 1.5 plus 0.75, which comes out to be 2.25. So when n was equal to 2, our y value when x was 1 came out to be 2.25. So that's a better approximation because remember, this function we know is the solution, and we know that y when x is equal to 1 will be e to the 1, which is approximating 2.71828. So that's our target. That's what we're trying to get close to. So now let's see what if we did it in more steps. So let's say that we started here and now we're going to use 4 steps. So we're going to split this into 4 even pieces. So our step size will be the 1 minus 0 over 4. So it'll be 0.25. Okay, so we're going to have to calculate. This is our x0 is still at 0. Our x1 is 0.25. Then we're going to calculate it for x equal 0.5, x equal 0.75, and then finally x equal 1. So our y value for x equal 0.25 is the previous y value, which was our initial condition. So 1 plus the slope, which was the previous y value. So this, we'll say the initial point, x naught, y naught, is equal to 0, 1. So the slope of the previous point, or at the previous point, which is the y value at that previous point, was 1. And our step size is 0.25 this time. So we'll have 1.25. That's just our approximate value at x equal 0.25. Now, let's use that. So this gave us the point. 0.25 was our x, and our y was 1.25. Now let's look at 0.5. The y is the previous y, plus the slope at the previous point, which is just the y value, so 1.25 times the step, okay, and that came out to be okay, so now our point here would be x equal 0.5, and the y is 1.5625. Now, we don't care about these intermediate values. We're just trying to get the y value at x equal 1 using 4 steps. So now, the next one will be the y is the previous y value plus the slope, which is the previous y value, times the step size, and that comes out to be 1.953125. So our point is 0.75, 1.953125. And now finally at x equal 1, our y value approximation will be the previous y plus the slope, which is the previous y just by this differential equation, times the step size, and that comes out to be 2.44141. So now we wanted the y value for x equal 1, and we did that with 4 step sizes, or 4 steps, and our y of 1 then came out to be 2.44141. And again, we're getting closer to this actual answer by using more steps. Now, I'm not going to go through the 8 and the 16. You can see it'd be really simple just to do this with the computer, which is what we'll do in the project notebook that will follow this. And that'll also help you to do your homework using the computer. So let's look at the table here that has these values. So you can see with 1 step, 2 step, 4 step, which is what we calculated, we got approximate values of 2, 2.25, and 2.44141. And you can see in the graph here that this was using the step sizes of 1/4 and 1/8. So the blue one is the actual answer. And by using the 0.25 step size, which was 4 steps, we got the one that's lower here. It wasn't quite as good approximation that as we would have gotten if we'd continued with using the 8 steps, which would have been the 1/8 step size, the h, for the h value. And that's the one right in between. So you see that the more steps we use, the closer we're getting to the actual answer of y equal e to the x. Okay, now let's start solving some differential equations. The first type we're going to solve is called a separable equation. A separable equation is one that when you have it in standard form, dy dx equal f of xy, you can express the right side as a function of only x times a function of only y. So you're able to actually separate out those x's and y's so that they're in expressions that are just multiplied together. Okay, so when you can do that, that equation is called separable. Okay, now to solve a separable equation, you'll write it in that form, or at least verify that you can write it in that form, and then you're going to group your x expression with your dx, and you're going to group your y's with the dy. So in this one, I would multiply both sides by dx, and then I would divide both sides by p of y. And so then you get something in this form. So notice, all the y's are with the dy, and all the x's are with the dx. Now that only works if the x and y expressions are multiplied together. They can be separated out into two factors like that. Okay, now when you do get it in this form, the next thing is just to integrate both sides. So when you integrate both sides, notice you'll get a constant of integration on both sides. So I'd have a plus c1 on the left and plus c2 on the right. But then we can always take those two constants and combine them and just put a single c. So we're going to do that. We're not going to tend to carry a constant of integration on both sides. Okay, so let's look at an example. dy dx is x minus 5 over y squared. Now if you look at this, first thing I want to do is, can I separate the variables? Well, I can think of this as x minus 5 times 1 over y squared. So yes, I can write this as a product of a function only of x times a function only of y. So now let's separate it. We're going to do that by multiplying and dividing. I'm going to put my y squared with my dy by multiplying both sides by y squared. And at the same time, I'm going to multiply both sides by dx. And so now I've separated my x's and my y's, hence the name separable equation. Next, integrate both sides. Okay? The antiderivative of y squared is y cubed over 3. And then I'd have a plus c1, but I'm going to combine it with my other c. And then we'll have x squared over 2 minus 5x, and then plus that c, which is the combined constant of integration on both sides. Now, most of the time we'd like to solve for y if we can to get it in that explicit form, but if you can't, you don't have to. This would actually be an implicit form for the solution, but if we want to get the explicit form, I would multiply through by 3. Now notice I would have a 3c. C, I don't even know what c is to begin with, so I don't need to put 3c. I can just put c to represent some unknown constant here. So we have y cubed is 3x squared over 2 minus 15x plus another c. It's not the same as the c previously. And then take the cubed root of both sides. And we can write that as to the 1/3 power or put it under a cubed root. Okay, so here's our explicit solution for this differential equation. Now, in the graph over here to the right, they have various graphs of this. They're using e for the constant of integration. But if you put in, c equal to -6, you're going to have this graph in here. They've just got various graphs just filling in different values for the c. So the c would be determined by an initial condition. So if you told me a specific point that it passed through, I could tell you exactly which of these graphs would have that point passing through. Okay, so let's look at another separable equation. I want to solve this initial value problem. So initial value just means we've got our differential equation and we have an initial condition. So we'll use that to determine the specific c in the next problem. So first, is this a separable equation? Well, yes, we could write this as y minus 1 times 1 over x plus 3, so the x and y's can be separated into separate functions that are multiplied here to be the dy dx. So separate them by multiplying both sides by dx, and dividing both sides by y minus 1. Okay, so now we have them separated. So now we're ready to integrate both sides. Okay, the left side would just be the log of y minus 1 plus a constant. The right side will be a log of x plus 3, and then we'll just put our constant here. Okay, now if we want to solve for y, we need to get that away from the log. So, You have several ways you can do that. You can take e to both sides. Let me just do that. Another way you can do it is to move the log to the left side, make both logs on the left, and combine them using properties of logarithms. But let me just do it this way. E to the natural log of y minus 1 equal, it's to the whole side. Don't do it each term. It's not equivalent. Okay, so e to both sides, since the two sides are equal. And now one of the rules for logs is that e to the natural log of x is just the x. Likewise, log of e to the x is also just x. Okay, so those are two properties of logarithms. So this left side becomes just the y minus 1. And the right side, I'm going to break the right side up first. This would be the equivalent to e to the log of x plus 3 times e to the c. Okay, remember the rule for powers. X to a power times x to another power. You add the exponents. So we can take a sum in the exponent and break it into a product this way. And that allows me to get this constant away from the rest, and I can just call this my c. So then this becomes the e to the natural log of x plus 3 is just the x plus 3, and then sometimes some constant. Okay, so now I want to solve for y. Okay, now this absolute value of y minus 1, we know that absolute value of y minus 1 will be either plus or minus the y minus 1. Likewise, the absolute value of x plus 3 is either positive or negative, whatever x plus 3 is. So we know there's going to be a possible negative sign. So I could say that y minus 1 is equal to plus or minus the c times the x minus x plus 3. There's only going to be a sign difference depending on whether those are a positive or negative of that value. So what we can do is we can just roll that plus or minus into the c and just call that a, you know, you can change letters if you want to. I just keep calling it c. Okay, so we really have this relationship, and it depends on whether those two terms come out to be positive or negative. So now that's going to be determined, though, and taken care of when we use the initial condition. So here's our standard form for the equation. And now solving it for the y, we have that y is equal to 1 plus some constant c times x plus 3. And now let's use our initial condition here to actually determine that c. So I'm going to have y equal I'm going to use the value x equal negative 1 and y equals 0. There's my x. So we'll have 0 equal to 1 plus c times negative 1 plus 3. So that's 2c plus 1 equal to 0. That means that 2c is negative 1, c is negative 1/2. Okay, so our equation that solves this initial value problem will be y equal 1 minus 1/2 times x plus 3. So if we take the derivative of that, we should get this. If you plug in negative 1 for the x, you should get 0, and we've solved the initial value problem. Well, one more step. I wouldn't leave it that way because you have a constant term here that can be combined. So let me go ahead and take y equal 1 minus 1/2 x minus 3/2. So that's just going to be y equal to minus 1/2 x minus 1/2. So you can leave it that way. I mean, all these are correct, but this is a more simplified form. Or you could write it as y equal negative 1/2 times x plus 1. So either one of those two, I would leave it in either one of these two forms. Okay, and let's look at one more solution. I want to solve this nonlinear equation. Is it separable? Well, we have a function of just x here divided by a function of just y. So it is separable. So the first thing we would do is to get the y's together. So I would have cosine of y plus e to the y dy equal 6x to the 5th minus 2x plus 1 times dx. So now we can integrate both sides. Now you're going to have to remember some of your integration techniques, so you might have to review those. The antiderivative of cosine is sine of y. e to the y is just e to the y. And then we'll have x to the 6th minus x squared plus x, and then plus some constant of integration. Now notice here that we're not going to be able to solve this for y, not with the y in the argument of both sine and e to the y. So there's times when you're just going to have to leave it in this implicit form. So that would be the best that we can do for this solution. Now one thing I want to point out here is when you're dealing with separable equations, because you're dividing by terms, remember that sometimes you can lose solutions. Remember back in algebra, when you had an equation like x times x minus 2 equal to 4 times x minus 2. If you divided by x minus 2, you got that x was just simply 4. But that's ignoring the fact that if x equaled 2, it would also satisfy the two equations. So this solution would have been lost by dividing by a variable expression x minus 2. So anytime you're dividing by things with the variable, just be careful. You might be losing a solution. So this method that we're using with the separability, where we're multiplying through by solutions and dividing by them, you could be losing a solution. So be careful. One thing in this problem here, look at the original problem and see, is there something that would cause the y expression, the y minus 1, to be 0? And y equal 1 with one such value. Now, y equal 1 was then we divided both sides by y minus 1. Okay? Which then it wouldn't have been a solution to this, because this y equal 1 was not valid here, because it would have been division by 0. So the solution we ended up getting actually did not include a solution to the differential equation. Y equal 1 was a valid solution, but it's not one of the solutions that we actually got. Well, now it looks like y equal 1 is a solution here if c was 0, but because we switched the c here, remember the c here had came about from the e to the c, which e to the c never would have been 0. So that meant that this c could never have been 0. Okay, so this actually would not ever include y equal 1 as one of the solutions to this equation, but it should have been as a possible solution, because let's say y equal 1. What would dy dx be? Dy dx would come out to be 0. Well, when y is equal to 1, dy dx would be 0. So we can see that this is a valid solution that was actually lost in the process because we divided by the y minus 1. So be careful when you do the separability equations, the separable equations. Check and see, is there any constant value that would make that f of y expression 0, because that gives you a constant solution that might be overlooked. Sometimes it's automatically built into the solution, like if this hadn't been the case where c couldn't be 0, you would have had y equal 1 as a solution for the c equal to 0. But there's other times, which this particular case, when that c could not have been 0, that y equal 1 is just a lost solution. So to keep from losing solutions, make sure you check to see if that expression containing the y could be 0 for a constant value, and keep that solution in mind, because that's an extra solution that might not come out with your general solution. Okay, now we're going to look at the linear first order differential equation and how to solve it. Okay, remember that a linear first order differential equation is an equation that can be put in this form. Notice that the y, which is the dependent variable, and all of its derivatives will have a power of 1, and they'll only have coefficients that are functions of the independent variable. And you can't have the dependent variable as an argument of a function like sine of y or e to the y either. So an equation in this form is a linear first order differential equation. So let's check a couple and make sure remember how to check that. Put it in this form. So I've got my dy dx term here, so I'm going to rewrite this as sine of x dy dx plus cosine of x times y equal x squared sine of x. In this form, it matches exactly the one up here, so that this is my a1 of x, this would be your a0 of x, and this would be the b of x. So this is a linear first order differential equation. The next one, I've got my dy dx, but it's multiplied by a y. So this keeps it from being linear. Likewise, this one, it can't have a y cubed. So both of these make this a nonlinear differential equation. It is first order, though, because it's only a single first order derivative. Okay, so now how do we solve the linear equations? The idea behind the linear equations is to make the form of one side be a product, the derivative of a product. So I'll show you how to do that. First thing you're going to do is you're going to take your linear differential equation, so your a1 of x dy dx plus your a2 times the y, a0 times y, equal to the b. Then you're going to divide through by this leading factor, the a1 of x. So we're going to have dy over dx plus a0 of x over a1 of x times the y equal to the b of x over the a1 of x. Okay. This is called standard form, when that first, the dy dx, has just a coefficient of 1. So this is our linear equation in standard form. Notice that the p of x here is just this a0 of x over a1 of x, and the q of x is just this b of x over a1 of x. So get the equation in standard form. Okay, so now the idea behind solving a linear equation is to find an integrating factor, so that when we multiply both sides of the equation by that integrating factor, and I'm going to call the integrating factor mu of x, so I'm going to multiply both sides by that. Mu of x times dy dx plus mu of x times p of x times y equal mu of x times q of x. Okay, we're going to be able to solve this by getting this left side now as the derivative of a product. So this is going to be the derivative of mu times y, if we're going to be able to solve it. So we want to find mu so that the left side is just the derivative of mu times the y. Well, when's that going to happen? What is the derivative of mu times y? The derivative of mu times y would be mu times the derivative of y plus the derivative of mu times y. Okay, so we know that that's true. When will that be equal to this? Well, the first term matches exactly. So the only time this is going to be equal is if mu prime of x times y is equal to this, which means that mu prime has to be mu times the p. Okay, now so let's look at that. How do we choose our mu so that mu prime is mu times p? Okay, now mu prime is the derivative of mu with respect to x. So what I'm going to do here is I'm going to separate out my variables. So this is going to be d mu over mu equal to p, it was p of x, times dx. And now I'm just going to integrate both sides. So this gives me natural log of mu equal whatever the integral of p of x dx is. So my mu, to solve for mu, I'm going to take e to both sides. And this is just equal to mu. So that's the integrating factor. Whatever the p of x is here that was in front of the y, we're going to take the integral of that and then take e to that power, and that's going to be the mu that we use. So our mu is equal to e to the integral of the p of x. Once you get your mu, multiply all the way through by it. So you're going to end up getting this. And now the left side, because of the way we chose our mu, the left side is just the derivative of mu times y. And now finally just integrate both sides. If you integrate the left side, you're just going to get mu times y. And so whatever that other side comes out to be. And then we'll be able to easily solve for the y. Okay, so that's the idea. linear differential equations, first order. Find the integrating factor, which is e to the integral of p of x, multiply through by it, then determine that the left side is the derivative of mu times y, and then you'll be able to solve for y. Okay, so here's an example. First, verify that it's linear. Is this linear? We've got a function of x times dy dx minus a function of x times our single y here equal a function of x. So this is indeed linear. So to solve it, put it in standard form, multiply through by x. I want to get rid of that leading function. So I'm going to have dy dx is equal to dy dx minus 2 over x times y, and I'm multiplying through by x, equal to x squared times cosine of x. Okay, so now, this is standard form. This is my p of x, and this is the q. Don't worry about the q of x. Really, the p of x is what you need, because that's what you're going to use to get the integrating factor. The integrating factor is mu of x is equal to e to the integral of the p of x. That's e to the integral of minus 2 over x dx, which the integral of minus 2 over x, remember the integral of 1 over x is just natural log of x, so this is e to the, I'm going to go and pull the minus 2 out just so you can see it. This is e to the minus 2 natural log of x, which to simplify this, remember that e to the natural log of x was just x, but we can't have but a 1 as the coefficient here for that to be true. So I need to move this back using properties of logs. Remember, log of x to the p is the same thing as p times log of x. So I'm going to move this negative 2 up as the exponent. So this is equal to e to the natural log of x to the minus 2, which now we can apply this property is equal to just x to the minus 2, or 1 over x squared. Okay, so that's our integrating factor. So now take the integrating factor and multiply through the equation in standard form. So multiplying through by the integrating factor. I'm going to have 1 over x squared dy dx minus 2 over x cubed times y equal just cosine of x. I'm multiplying all the way through by 1 over x squared. Okay, now I'm ready. This left side, because of the way I chose my integrating factor, is just the derivative of the mu, which is 1 over x squared times the y. It's always just the integrating factor times y. So now, to solve for y, I'm going to integrate both sides. The integral of the derivative of 1 over x squared y is just 1 over x squared y. Equal, the integral of cosine is just going to be equal to sine of x. Okay, and finally, now let's solve for y. We're going to multiply through by y squared, so y is equal to x squared, not y squared, times sine of x plus c times x squared. And that's your solution. Of course, it's a one-parameter family of solutions. So the c would be determined if we had an initial condition. So now if you picked various values for the c and graphed them, this is a picture of your solution curves. Okay, one more example. Okay, the rate of decay of a radioactive isotope is given by this function, where y is the mass of the isotope present at time t. So if you're told that initially y of 0 is 40, we want to find the mass y of t. So we're trying to find an expression for y of t. We want to solve that differential equation. So the first thing we want to do is identify it. Is it separable? Is it linear? Those are the only two we've talked about. So looking at it, if you change the form, this is dy dt plus 2y equal 50 e to the minus 10t. The dependent variable is y, and the independent is t. And so now we have it in a form that we can see that it is linear. It's linear, and it's already in standard form. Because that initial, the coefficient of the dy dt is just 1. Okay, so you need it in standard form because the next thing you're going to do is you're going to get the integrating factor. Okay, identify it as linear, put it in standard form, get the integrating factor. The integrating factor is mu equal e to the integral of the p of x, or in this case p of t. Okay, our p is just 2. So this is just going to be e to the 2t. Now we don't have to worry about a plus c when we're doing the integrating factor. We just need an integrating factor, just any integrating factor. So we're going to choose the one that's simplest with the c equal to 0. Okay, so once you get your integrating factor, multiply the entire standard form by that integrating factor. So we're going to have e to the 2t times dy dt plus e to the 2t times 2y equal e to the 2t times 50 e to the minus 10t. Now, you don't have to formally go through doing this every time because it's always going to be the same. This left side is the derivative with respect to t of the integrating factor times y. So then the next step would be just integrating, so you're going to get e to the 2t y. This will always be the integrating factor times y when you integrate. So all that's left to do then is to integrate the left side. Okay, so at this point, though, to make these two sides equal, I haven't integrated yet. So I'm going to have e to the 2t. Let me go ahead and simplify this. This would just be 50 e to the minus 8t because they have the same base. I can add the exponents. Okay, and now we're integrating both sides at this point. So we're going to have 50 times the antiderivative of e to the minus 8t would be e to the minus 8t divided by negative 8. So times negative 1/8. If you don't remember that one, go through U substitution and you'll get this. Okay, and so now the last thing to do is to solve for y. So the y will be just e to the 2t. Well, we're dividing by e to the 2t, or multiply through by e to the minus 2t. So let me do it that way. E to the minus 2t, because that gives you 1 on the right, the left side. Okay. So we have, let's see, 50, that'd be minus 25 over 4 e to the minus 10t plus c times e to the minus 2t. So there's your general solution. That's that one parameter family of solutions. But we also have that we have an initial condition. Y of 0 is 40. So let's plug that in. We'll plug t equal to 0, and the y should be equal to 40. So we'll have 40 equal negative 25 over 4 e to the 0 plus c times e to the 0. E to the 0 is 1. So we have that 40 plus 25 fourths is equal to c. So that's 160 fourths. So that's going to be 185 fourths equal to c. So fill that into our equation down here. And our solution, the specific solution to this initial value problem is negative 25 over 4 e to the minus 10t plus 185 over 4 e to the minus 2t. Okay, sometimes we're not going to be able to actually get a nice, pretty formula for our solution, but we might be able to find values at specific points for it. So we've got an initial value problem here. Y prime plus y equals the square root of 1 plus cosine squared of x at y of 1 equal to 4. We're trying to just find a specific value of the function at x equal 2. So first off, look at the equation and see how you can solve it. Is this a separable equation? Is it linear? Since those are the only two types we've actually learned to solve. Well, because of that plus y, move to the other side to be a minus y, you're not going to be able to write it as a separable. It's not a separable equation, but it is linear. This y prime is your dy dx. The coefficient's 1's already there, so it's already in standard form. And you have the a0 of x is also the 1. So it's in standard form, so this is a linear equation, and it's in standard form. Linear first order, because you see the highest derivative is first order. Okay, so once you know it's linear, you put it in standard form, which it already is. The next thing you do is find your integrating factor. Okay. The p of x in this case is just the 1. Okay. So our integrating factor will be mu equal e to the integral of the p of x, which is e to the integral of 1. So that's just going to be e to the x. So we've got our integrating factor. Okay. Once you have the integrating factor, multiply through by it. Both sides. And you get mu times y prime plus mu times y equal mu times the square root of 1 plus cosine squared of x, which our mu is e to the x. So it's going to be e to the x y prime plus e to the x y equal e to the x times the square root of 1 plus cosine squared. The left side, again, is just the derivative of the integrating factor times y. You can check it. Okay. Okay, now integrate both sides. Okay, when you integrate the left side, you're just going to get the e to the x times the y. And then this right side, now unfortunately this is not going to be something we're going to be able to integrate. So you don't always have functions that you can integrate. You have table of integrals to get some of them, but this is a pretty bad one. So what we'd probably do is we would just use an approximation technique. So you can use something like Simpson's rule to approximate that. What I'm going to do though is I'm just going to use the calculator. I'm not going to review Simpson's rule. That was back in Cal 2. So what I would do next, since all I care about here is finding the value of y of 2, I'm not just asked for the function y. I mean, you could get the function y. Y would just be this whole integral divided by e to the x or times e to the minus x. Don't try to take that e to the minus x inside the integral though. But we're just looking for a specific value of y, not an actual function. So what I'm going to do is I'm going to take both sides of this equation and I'm going to take the integral for them, the definite integral from 1 to 2. But let me back up to do that. I'm going to back up to this previous step up here, and I'm going to integrate from 1 to 2. Now, I chose 1 and 2 because 1 was where the initial condition was given, and 2 is the value that I'm trying to get the function at. So by integrating, making this a definite integral here, I know what the antiderivative is. It's e to the xy, and now I'm just going to evaluate that from 1 to 2. And then I'm just going to keep this as a definite integral. And so now the left side becomes e, we're evaluating, we're putting 1 and 2 in for the x. So it's going to be e to the 2 times y of 2. Now remember, y is a function of x. So y of 2 minus e to the 1 times y of 1. Okay, I know that e of 1 is 4, so I'm going to replace the e of 1 down, y of 1 with 4. So I think I said that wrong. E squared y of 2 minus e times 4 is equal to this integral. Now what I want you to do is to use your calculator to approximate this. Okay, just simplifying just a little bit. I'm trying to solve for y of 2. So this tells me then that y of 2 would be equal to 4 times e, taking the 4e to the other side, plus this integral, and then the whole thing divided by e squared, because I'm trying to solve for the y of 2. So I'm just going to multiply this whole thing by e to the minus 2. Okay, so I've got the calculator up. Let me show you how to use that to get this integral. You're going to enter the function e to the x square root of 1 plus cosine of x squared using the y equal button. Okay, so we're going to use the y equal button. We're going to enter e to the x, so second log, and enter the variable x, close the parentheses, and then times the square root 1 plus, now that cosine squared x is really cosine of x. I'm going to put it in parentheses, cosine of x, parentheses, squared. And then close my parentheses for the square root. So that should be my function. And now I want to find the definite integral from 1 to 2. So you use the calc button, which is the second trace, and option 7 is the definite integral. It'll graph the function. I'll make sure you also have it in radian mode, which I already have. It needs to be in radians for the cosine. The lower limit is 1. The upper limit is 2. And so the value of that integral is 4.841. Okay, finishing that, let's go ahead and add that to 4e. So let me clear that. Clear it. 4.841 plus e to the first, e to the first power, enter, whoops, entered a few times, times e to the minus 2. So that comes out to be 1.023. Okay, and before you say anything, I see that I didn't multiply by the 4. So let's go back. That is 4.841 plus 4 times e to the first, equal, and then times e raised to the negative 2. Let's see if that's a little better. Yes. So we have 2.127 if you want to approximate 3 decimal places. Okay, so all we did there was to find what y of 2 was. And we didn't even have to finish up the integration, but we were able to get a function's value just using numerical methods. Okay, now I just want to finish up with a theorem just showing us that just going through the process that we just did, the p of x and the q of x in this standard form for a linear equation will be continuous for at the whatever value that we're using here. So for that if the function and derivative exist at x naught, then the p of x and the q of x will be continuous, and that's going to guarantee us then that there will be a unique solution to this initial value problem. So we do have the linear equations because if the p and the q are both continuous on the interval, we will have a unique solution, and we won't have to worry about that existing or not. Okay, now we're going to look at a third type of differential equation called an exact equation. This one's one that's going to assume that we started with a function that was given in implicit form. So we have a function f of xy equal to some constant c. So now we're assuming here that the x is still the independent variable, and that y is the dependent variable, and that y is a function of x. Okay, now so let's take the derivative of both sides with respect to x. So I'd have the derivative of the function f of xy with respect to x is the derivative of the c with respect to x, which will just be 0. Okay, now how do you take the derivative of a function that has two variables? Okay, now think back to Calculus 3. If you had a function with two variables, you had to use a chain rule. And you got the chain rule that was specific to that function by looking at its independent variables. The function f has two variables, x and y. X is a function of itself. It's the independent variable. Y, on the other hand, is the dependent variable, and y is a function of x. And so to get the chain rule, you know that the derivative of the f is built by the derivatives with respect to x and the derivatives with respect to y. So you got the part that each of those contribute to the derivative of f by looking at the partial derivatives of each branch. The partial of f with respect to x, now because f had two variables, x and y, coming off of it, we have to do partial derivatives of the f to get the derivative with respect to x. And then the derivative of x, since there's only one variable that it's has it in terms of, that's just a regular derivative, dx dx. Likewise, the f has two variables, so the partial with respect to y, we have to use partial derivatives since there's two variables for f, and the derivative of y with respect to x, since y is just in terms of one variable, is dy dx. So now, the derivative of f with respect to x is built by taking the product of the derivatives along the branches. So you would have the partial of f with respect to x times dx dx. So this is the chain rule. The partial of f with respect to y, dy dx. Now dx dx is just 1, since the change in x relative itself is just 1. So this gives me the partial of f Now we also had that this derivative of f with respect to x was just 0. So we'll have that equal to 0. Okay, so now one thing I want to do, though, is we're going to be looking at these equations in the differential form. Now the differential form means we're not going to have the dy dx in that form in the equation. Instead, we're just going to have the differentials, the dx and the dy, separately. So let's take this equation and let's multiply both sides by dx. So I'm going to have the differential of the f is equal to the partial of f over the partial of x dx plus the partial of f with respect to y times dy equal to 0. That's the differential form of the equation, and that's what we're going to use to compare the differential equation we're given to see if it's an exact equation or not. So we're going to be given equations in this form. M of xy dx plus n of xy dy equal to 0. So notice you just have a function of x and y in front of the dx, a function of x and y in front of the dy. Okay, so if this is going to be an exact equation, what's in front of the dx has to be the partial of f with respect to x. So this would need to be the partial of the f with respect to x. Likewise, the n of xy has to be the partial of f with respect to y. Okay, so if that's true, then we have an exact equation. Okay, so now how are we going to test to see if there's some f that the m is the partial with respect to x and the n is the partial with respect to y? Okay, so that uses something else from Calculus 3. that said that if you had a function f of xy and took the partial of it with respect to x, and then took the partial of that with respect to y, that should be the same thing as if you took the partial of f with respect to y first, and then took the partial of that expression with respect to x. Okay, so these are your second derivatives from Calculus 3. And those should be the same if, well, as long as the f and the two derivatives were continuous, those will be the same. So the way we can test to see, is this the partial of some f with respect to x, and this is the same partial of the f with respect to y, is by taking the partial of the m with respect to y now, because the m's already the partial with respect to x. So now take the partial of the m with respect to y, and that should be the partial of the n with respect to x, if there's an f that makes that true. Okay, so this will be the test to see whether or not we have an exact equation. Okay, so there's two things going on here. You first need to look at the differential form, determine the m of xy, which is what's in front of the dx, determine the n of xy, which is what's in front of the dy, then check the m. If it's exact, that means that that m is already the partial of some f with respect to x. So check the m and see if you took the partial with respect to the y then, if that's going to be the same as the partial of the n with respect to x. If that's true, then that means there is an f that exists that has those two as the partial derivatives, and so our solution will be just the f of xy that has that true equal to c, and that will be the solution to our differential equation. Okay, so now I'm going to look at an example. I'm not going to show you how to get the f yet, but what I'm going to do is I'm going to show you how to look and determine if it's exact and look at the differential forms. So first thing you need to do is to look at differential forms. Well, actually the first thing I'm going to do is see, is it separable, because I'd much rather solve it by separability than to do it by exactness. So is it separable? Well, remember, to be separable, you have to be able to take this expression and write it as a product of just a function of x and just a function of y, and you're not going to be able to get that, not with the way the x's and the y's are multiplied together there. So it's definitely not separable. Is it linear? Well, to be linear, you would have to have a function of x times dy dx plus a function of x times the y, but you're not going to be able to get this y in that form. So you're not going to be able to get that x and the y squared separated. So it's definitely not linear either. Okay, so then the next thing you do, is it exact? Okay, so let's look at differential forms so that we can tell if it's going to be exact or not. Okay, so the first thing I'm going to do is I want to get 0 on one side. So I have that dy dx plus 2xy squared plus 1. Now notice this minus is in front of the whole fraction, so when I move it over, I just make the whole fraction positive. Okay, so that's moving everything to one side. Now the differential form is where we have just the dy and the dx separately. So let's multiply through by dx. You're going to have okay, that's one differential form, but let's be really careful here. The form that we're trying to match is m dx plus n dy equal to 0. We want to look at that form, so put the dx first, or at least be sure you pull the m from in front of the dx. So let me turn it around right now so I'm going to have 2xy squared plus 1, 2x squared y dx plus 1 dy equal to 0. Okay, so now we're in the same form. So comparing this one to this form, the m would be this, and the n would be this. Okay, so that's one possible differential form. Let's look at another possible differential form. Instead of leaving that big fraction in front of dx, let's multiply through by 2x squared y. So maybe 2xy squared plus 1, and notice that whole thing times dx, plus 2x squared y dy equal to 0. So there's another differential form. In this form, this would be the m, and here would be the n. Okay, one more differential form. What if we had a 1 in front of the dx? So we could have 1 dx. I'm dividing by 2xy squared plus 1. In this equation, this would be the m, and this would be the n. Okay, so we've got three different possible differential forms. Now we're looking for a function, f of xy, equal to c, so that the m is the partial with respect to x. And the n is a partial with respect to y. Okay? And we saw in the test for exactness that that's going to be true if the partial of the m with respect to y is equal to the partial of the n with respect to x. Okay? So let's check. Which of these three forms do you think the partial of the m with respect to y would be the same as the partial of the n with respect to x? Well, in the first one, the n is 1. So if we took the partial of n with respect to x, it's going to be 0. So the partial of this big thing with respect to y is not going to be the partial of this one with respect to x. Likewise, if you looked at the third equation, if you looked at the partial of this m with respect to y, it's 0. It's not going to be the partial of this one with respect to x. So the one that we have the best chance of working, being an exact form, would be this one. Okay, so in this case, our m would be the 2x y squared plus 1, and the n would be the 2x squared y. Let's check it for exactness. Take the partial of the m with respect to y. That means you're treating the x as if it's a constant. So we'd have 2x times the derivative of the y squared, which is 2y, plus the derivative of 1 with respect to y, which is 0, which comes out to be 4xy. And now let's look at the partial of the n with respect to x. In this case, you hold the y as if it's a constant, so we'll have the 2y as a constant, and now the derivative of the x squared is 2x. And they do come out to be the same. That tells me that there is an f, so that if you took the f equal to the constant, it would be the solution to this differential equation. Now I'm going to show you an f that appears to work. What if f of xy was equal to x squared y squared plus x, and then equal to some constant? So what if we took the partial of this function with respect to x? So the partial of the f with respect to x, remember the partial of f with respect to x should be the m. So the partial with respect to x, the y will be a constant, so y squared times the derivative of x squared plus 1. Now what about the partial of the f with respect to y? If this function really works, the partial of the f with respect to y should be the n. So the partial with respect to y, now x is a constant, so x squared times the derivative of y squared, which is 2y. And then the derivative of x is just 0 when y is a constant. So that'll be when y is the variable. So that's 2x squared y. And is that the n? The n is 2x squared y, and the m was 2xy squared plus 1. So that does work. So our solution to this equation, of this differential equation, would be x squared y squared plus x, that is your f, equal to the constant. You've got to write it in that form. Don't say y equal. It's got to be an implicit form. So this would be your solution to the differential equation. Okay, now let's look at a way to solve for the function f when we know we have an exact equation. So first thing we want to do is look for the form to make sure it's exact. So if it's exact, you'll have this form where the m should be the partial of the f with respect to x, and the n is the partial of the f with respect to y. So if you have an equation of that form, in the differential form, you can check it to be sure it's exact, and the way you do that is you check the partial of m with respect to y and see if that's equal to the partial of the n with respect to x. Okay, so that's the test for exactness. Okay, so now how are we going to determine what the function f is? Well, we're going to use the fact that we know that the m is the partial of f with respect to x, and that the n is the partial of the f with respect to y. If we know m is the partial with respect to x, then we can go backwards and find the f by integrating m with respect to x. Or we could start with the n if we want to, and integrate n with respect to y to find out what the f is. Now, you're going to end up with the constant of integration when you do that, and the constant of integration won't be a single constant. It actually could have a function of the variable that we're deeming as constant as well. So I'll get to that in just a minute. So they've got the steps here where you can find the f then by integrating the m with respect to x. And then just remember, when you integrate something with respect to x, you're assuming that the y is a constant. So that means any expression that you had in that had just y's in it, the derivative of that would have been 0. So when you integrate the m with respect to x, you're going to end up with some function of y, which is your constant of integration. So this will be your constant of integration if you're integrating, with respect to x, when it's a function of multiple variables. Okay, now once you do that, then we can take the derivative of both sides with respect to the y. So if we take the partial of the f that we get from that with respect to y, so you would be taking the partial of this with respect to y. It'll be an expression that has y's. You take the partial of that with respect to y, and then you would take the derivative of this with respect to y. And what you're going to get then is you're going to get the n. So that'll be the partial with respect to y of that integral. And then take the derivative of the g of y with respect to y, and you get g prime of y. Okay, so now once you set n equal to this whole thing, then some of the terms are going to cancel out. What's remaining will be the g prime of y. Once we get the g prime of y, once we get that, then we can go back and get the g of y by just integrating g with respect to the y. So we'll do that in multiple steps. So determine g of y, you take the partial derivative with respect to y of both sides, which is what they're saying here. Substitute that for n, and then you solve for g prime of y by integrating. So integrate g prime of y to get the g of y, and then substitute that back into this equation right here. Okay, just be sure that you put your answer in this form. Okay, so let's look at a couple examples. Okay, first thing you want to do is check what type of equation it is. Now, because this one's in the differential form, you could go ahead and just try the exact, method, but you could also rewrite it. If you get dy dx in there, you can look and see if it's going to be separable. Let's see, would it look like it'd be separable? Probably not with this x squared plus 2y. So even if you divided by dx, and you're not going to end up having it separable because of that x squared plus 2y. As far as linear, with that 2y times the dy dx that you're going to have if you divide by dx, it's not going to be linear either. So this one's not separable and it's not linear. So that's what I would check before I start working on exact. It's in the differential form, so that saves us a step. So what we're going to do next then is to identify what the m and the n would be. The m is is what's in front of the dx, so here's my m. The n is what's in front of the dy, and then we've got the equal to 0. So be sure it's in the right form, m dx plus n dy. Now check to see if it's actually exact. So the test for exactness, remember the m, if this is an exact equation, the m is a partial with respect to x. So I'm going to take the partial of m with respect to y, and I want to see if that's the partial of the n with respect to x. The partial of m with respect to y will be 2x, and then secant squared x doesn't have a y, so it would just be 0. The partial of the n with respect to x will also be just 2x. So these are equal to each other, so that means we have an exact equation. Okay, so now the goal is to find the f. Okay, so find the f. I know that the f of xy, because it's exact, I know that this m is the partial of the f with respect to x. So I'm going to use that and take the antiderivative, the integral of the m with respect to x. Okay, so you're just taking the partial of the m with respect to x. Okay, so now when I integrate that, I'm holding the y as a constant, the x is the variable, so I'm going to have 2y, x squared over 2, using the power rule. The antiderivative of secant squared is going to be tangent of x. Okay, now when you integrate, remember, you usually would have a constant because the derivative of any constant would be 0. But in this case, we've got a multivariable function. We're integrating with respect to just the x. So anything that had only y's in it or constants would have had a derivative of 0. So that's where this g of y is going to come from. It's that constant, because if you went back and took the derivative of this, you will get 2xy minus secant squared of x, because the derivative of g of y would just be 0. Okay, next, we're going to use the n. If this was exact, which we know it is, the n here should be the partial of the f with respect to y. So the next thing I'm going to do is I'm going to take the partial of f with respect to y. So integrate with respect to x first. So I'm integrating m with respect to x. Now I'm going to take the derivative, differentiate f with respect to y. So I'll have the partial of f with respect to y. Okay, so this first term is just x squared times y. The derivative with respect to y would just be x squared. The derivative of tangent of x with respect to y is 0. And then g of y, if we take the derivative with respect to y, see y is the variable in that, the independent variable, then the derivative will be g prime of y. But remember, partial of f with respect to y is n. So that means that x squared plus 2y should equal to x squared plus g prime of y. Well, that tells me then that g prime of y is 2y. I've just got one variable now, so integrate with respect to y. So that tells me that g of y is equal to y squared plus some constant. Okay. You really don't need the constant here because we're going to move it all to the other side in a minute. But remember, once you get the g of y, you will come back up to here and write down what your function f is. So the f of xy, let me cancel these 2's, will be the x squared times y minus the tangent of x plus the y squared plus some constant, but remember we're going to write the answer as equal to c, so I'm just putting the c on the other side. You don't really need that constant here. And that's the way you leave your answer. So the f of xy is the x squared y minus tangent x plus y squared. and you leave it as that equation equal to c. You wouldn't actually put this part of it in the answer blank. That is the f of xy. Okay, so let's just check it. If we were to take the partial with respect to x, we would have 2xy minus secant squared plus 0. That's the m. If you took the partial with respect to y, you would have x squared plus 2y, which is the n. Everything matches. So that's it. Okay, one more. Okay, looking at this, because of this x e to the xy term, it's not going to be separable. Linear, let's see, it could possibly, it will not be linear. Let's see, I'd have to divide everything through by dx. It actually might be linear, because if I divide everything through by dx, I'm going to have the 1 plus e to the xy, e to the xy plus x e to the xy plus dy dx equal to 0. I can factor out the y from these, so I'd have x e to the x plus 2 dy dx plus okay. It is linear. So you could use the linear. It might be kind of difficult though if you look at what your p would be, which is the e to the x plus x e to the x over x e to the x plus 2. Finding the integral of that would not be very pretty. So you're probably not going to want to use the linear method. So let's check the exactness here. It's in the form of the exact. This would be your m, whatever times the dx, and this would be your n. So let's just check. Is the partial of m, see it should, if it's exact, that is the partial of f with respect to x, and this should be the partial of f with respect to y. Okay, the partial of the m with respect to y would be e to the x, because the derivative of 1 would be 0, e to the xy, the derivative would be e to the x, and then plus x e to the x. Okay, so that's partial with respect to m. The partial of the n with respect to x, I'm going to have to use the product rule. X times the derivative of e to the x is e to the x, plus e to the x times derivative of x, which is 1, and the derivative 2 is 0. So these do equal. So that means it's exact. Okay, so once we know it's exact, we're going to come up and use the fact that m is this, or n is the other one. Either way, you can work with either one of them. Okay, so if I want to find f, I'm going to integrate the m with respect to x. Okay, integrate with respect to x, we'll have x plus the y is a constant, integral of e to the x, e to the x. This one's going to take integration by parts. So let's come over to the side. The y is just a constant, so I'm going to say y times whatever the integral of e to the x is here. Okay, so let's go over here to the side. The integral of x e to the x, integration by parts, I would let u be the x, the dv would be e to the x dx, the v then is just the e to the x, the du is just the dx. So this integral becomes uv, which is x e to the x, minus the integral of the v du, which is e to the x dx, which is just e to the x. So this becomes x e to the x minus e to the x. So that's the integral of this term right here. And now we're ready for our constant of integration, but we're integrating a multivariable function with respect to x. So anything that it had just y's in it could have been added to that as well. Okay, so now we're ready to use the fact that n is the partial of f with respect to y. So now I'm going to differentiate. So we integrated m with respect to x. Now I'm going to differentiate f with respect to y. Which we know has to be the n. Okay, now taking the derivative with respect to y, derivative of x is 0. The derivative of y e to the x is just e to the x. The next one, it's y times all that, so it's x e to the x minus e to the x. And then the derivative of g of y with respect to y is g prime of y. So now take this. The x e to the x cancels. Well, let's see, this e to the x cancels there. So we end up with just 2 g prime of y. Okay, so now find g by integrating with respect to y. So g of y is 2y, and we don't need to worry about the constant because we're just going to roll it over to the other constant on the other side anyway. Okay, so now let's come back here. I will replace the g of y here and get my solution. So my solution is x plus y e to the x plus y, I'm going to go ahead and distribute that, x e to the x minus y e to the x plus 2y equal to c. So here's my f. But let me go ahead and get rid of the terms here that are duplicate. This and this should have canceled. So I've got x plus xy e to the x. And there's your answer. Let's check it. The partial of that with respect to x should be the m. So we'll have 1 plus, the partial of this thing with respect to x would require the product rule. So we'll have 1 plus the x, well, the y is a constant, x times the derivative of e to the x is e to the x, plus the y times 1, which is the derivative of the x and e to the x, and then the derivative of 2y is 0. So that gives me the y e to the x plus xy e to the x. So there's your m. And the n should be the partial of this thing with respect to y, which will be the x e to the x plus the 2. And that matches that as well. So we've checked it. Okay, now let's look at another example. This one's already in differential form, and you can see because of this cosine of y dy that it's not going to be separable and it's not going to be linear. So let's check to see if it's exact. Well, by the form that it's in, we have the m dx plus n dy. This would have to be the m, and this would have to be the n. So let's check the part, if this is exact, remember this would need to be the partial of the f with respect to x, and this would have to be a partial of the f with respect to y. So to check to see if it's exact is the partial of the m with respect to y equal the partial of the n with respect to x. Well, the partial of the m with respect to y would be 3x cubed cosine of y. The partial of the n with respect to x would be cosine of y times 4x cubed. We see that they're not the same. They're very close, but they're not the same. Let's see if there's something we could do that might make it exact, because it's very close to being exact as it is right now. Let's take the original equation and let's multiply through by x to the minus 1. It's called an integrating factor if you multiply all the way through by something. So let's say multiply both sides by x to the minus 1, which is like dividing by x. So we're going to have 1 plus 3x squared sine of y dx plus x cubed cosine of y dy equal to 0. Okay, so now let's check and see if it's exact. For this equation, this would be my m, and this would be my n. So the partial of this m with respect to y would be 3x squared cosine of y, and the partial of the n with respect to x would be 3x squared cosine of y. Now we have an exact. So this one's an exact equation. The previous one was not. So multiplying both sides by x to the minus 1 created an exact equation. So this is called an integrating factor. And we'll look at how to get that in another section. Okay, so now let's just solve this equation. Okay, we know it's exact. That means that the m here is the partial of the f with respect to x. So let's integrate the m with respect to x. Okay, so we're going to have f is equal to the integral of 1 plus 3x squared sine of y with respect to x. Now, integrating with respect to x, I'll have x plus sine of y is a constant, and then times x cubed. But we could have had another function that had only y's in it. Oops. Prime is just g of y. So anything with just y's would have had a derivative of 0 and would have given us the same answer. Okay, now let's differentiate the f with respect to y. And remember, partial of f with respect to y will be the n here. Okay. Take the derivative of this side. You'll have 1 plus, we're integrating with respect to y, not x. Integrating x with respect to y will be xy. Integrating this with respect to y, the x cubed will be a constant. The derivative of sine of, I'm taking the derivative, not integral. Let me get back up here. The derivative of x with respect to y, I'm taking the derivative, will be just 0. The derivative of sine y x cubed with respect to y will be x cubed times cosine of y. And then the derivative of g of y with respect to y is g prime of y. That means that 0 is g prime, which if you integrate, that means g of y has to be just simply a constant. Okay, so let's go back up here and fill in our constant, which we can assume the constant 0 since we're going to put it equal to a constant anyway. So we'll have x plus x cubed sine of y plus constant equal to a constant, and that will be your solution. So this is our f of xy. So sometimes you don't have an exact equation, but if you're really close, you might be able to introduce an integrating factor that you can multiply through by and switch the equation to being an exact equation. We saw on the last example of the previous section that we had an equation that wasn't exact, but by multiplying through by x to the minus 1, it created an exact equation. So if we have an equation in this form, m dx plus n dy equals 0, that's not exact, but multiplying through by some factor, mu, and we get mu m dx plus mu n dy, if that creates an exact equation, then that mu is called an integrating factor. Now we used that back when we were dealing with linear equations as well. So what we want to do in this section is focus on how do you find that integrating factor that you might need. So we're going to start by looking at another example and verifying that what they give us is really an integrating factor. So we'll start off, we have a differential equation, differential form of a differential equation. I've got the m is 2y minus 6x, and the n, 3x minus 4x squared y to the minus 1 in the form that it's given us. So is it exact? So is the partial of m with respect to y equal the partial of the n with respect to x? So it's exact if that's true. So let's check. The partial of the m with respect to y will be 2. The partial of the n with respect to x will be 3 minus 8x y to the minus 1. Well, clearly those are not the same, so this one's not exact. Okay, so now let's use what they're giving us as the integrating factor. I'm going to multiply through by xy squared and get a new differential equation. So the new equation is going to have the form 2xy cubed minus 6x squared y squared, 3x squared y squared, minus 4x cubed y to the first equal to 0. Now let's check to see if that's exact. So that's multiplying through by the integrating factor. Okay, so let's check. The partial of the m, so now this is my m, and this is the n. The partial of the m with respect to y will be 6xy to the second minus 12x squared times y. And the partial of the n with respect to x would be 6xy squared minus 12x squared y. And those are equal, so this one is an exact equation. Okay, so the way we found is we knew that if it's of the form, it's an exact equation, we know the f of the xy has to be the integral of the m with respect to x, because we know that this will be just the partial of the f with respect to x, and we know the n will be the partial of the f with respect to y if it's an exact equation. So integrate 2xy cubed minus 6x squared y squared with respect to x, which gives me x squared y cubed minus 2x cubed y squared, and then we know that it could have some function with just y's. Okay, so now we're going to use the fact that the n is the partial of the f with respect to y. So we're going to differentiate f with respect to y, and we should get the n. And that should give me 3x squared y squared minus 4x cubed y. But let's go ahead and take the derivative of this with respect to y. So it's going to be 3x squared y squared minus 4x cubed y plus g prime. Well, what that gives me then is that 0 has to be the g prime of y, which means that the g is just going to be a constant. Okay, so go back up here. Our f of xy is x squared y cubed minus 2x cubed y squared plus the g is a constant, but we're going to set it equal to c, so we just move the constant over there. This is the general solution to this differential equation, where this is the f of xy. Okay, one thing to be careful of when you're introducing integrating factors is that you could be multiplying through by 0, which would wipe everything out. So look at the integrating factor. If mu is equal to 0 for some value, it could cause there to be extra roots, or you could lose roots. So we know x equals 0 and y equals 0 would satisfy, this equation. If you look at the original problem, if x is 0 or y is 0, you're not going to have 0. But if you look at this form, if I put in x equals 0, you're going to get 0 equals 0. If I put in y equals 0, you'll get 0 over 0 equal to 0. But you will not have those be solutions to the original problem. So x equals 0 and y equals 0 are solutions to the second equation, but not the first one. So these are called extraneous solutions. And you can see that they would satisfy that. but not of the original. And so sometimes you need to throw out, so exclude them from the solution set. Okay, so now let's look at how do we find the actual integrating factor. Okay, so we started with an equation of the form m dx plus n dy equal to 0. We multiplied through by some integrating factor, mu m dx plus mu n dy equal to 0. If it's exact, this new term here should be the partial with respect to x. But if it's going to be exact, we know that the partial of this with respect, this is our new m, so we know that the partial of this with respect to y should equal the partial of mu times n with respect to x. Okay, that's just the test to see if it's exact. Okay, so now what is the partial of mu m with respect to y? Okay, we're going to need the product rule. This would be mu times the partial of m with respect to y plus m times the partial of mu with respect to y. And that has to equal to mu times the partial of the n with respect to x plus n times the partial of mu with respect to x. Okay, I'm going to collect the terms that have the mu on the right side, and I'll put the others on the left. So I'm going to have m times the partial of mu with respect to y minus n times the partial of mu with respect to x equal partial of n with respect to x minus the partial of m with respect to y. Okay, now solving this for mu isn't going to be easy. We're not going to be able to do it. But there's two special cases that we're going to look at. What if mu was only a function of x? Then that means the partial of mu with respect to y would be 0. So this term would be 0. So then we would have minus n times the partial of mu with respect to x equal okay, so what I would do next is I'm going to say that this is the partial. I'm going to multiply through by the mu x, and I'm going to have the partial of, I'm separating them essentially, the partial of mu with respect, or divided by mu, is equal to okay, so I just grouped my mu's together. I have the partial of mu over mu equal to this whole thing. Now, if you integrate both sides, we're going to end up with the natural log of mu on the left side equal to just the integral of this thing on the other side. Okay, now changing this to solve for mu, the mu then, we're just going to take e to both sides. Mu is going to equal to e to the integral of, and I'm going to take that minus sign down here and distribute it through the top and so turn them around. So that'll be the partial of m with respect to y minus the partial of n with respect to x all over n. Okay, that would be our integrating factor, and that looks horrible. But if, when you compute this, if it only is a function of x, this is your integrating factor. If you compute this, and it's only a function of y, then this will be your integrating factor. Okay, so that's a way to get the integrating factor. Okay, so this is just telling you how to get the integrating factor. So the steps for doing this, if you have an equation that's not separable or linear and not exact, then if it's not exact, look at this. If that's a function of just x, then your integrating factor is going to be up here. If this is a function of just y, then your integrating factor will be up here. So let's look at an example that does that. Okay, so let's look at this. First off, you can see that it's not going to be separable because of this x squared y minus x term. You can see it's not going to be linear because of that x squared y times the dy. If you changed it to the linear form, you're going to have that y times the dy. And so let's check to see if it's exact. So to be exact, the partial of the m with respect to y has to be the partial of the n with respect to x. So here's the m. The partial with respect to y is 1. The partial of the n with respect to x would be 2xy minus 1. So they're not equal. So let's see now, is there an integrating factor? It's close to being exact. So we're going to look at the partial of m with respect to y minus the partial of n with respect to x over just the n. Or we're going to look at the partial of n with respect to x minus the partial of m with respect to y, just turning them around because of the negative sign, over the m. If this is a function of x, I mean, only y on this one or only x on this one, then we'll know what our integrating factor is going to be. Okay, so it's just going to be e to the integral of that expression. So let's look. The partial of the m with respect to y was just 1. So we had 1 minus the partial of the n with respect to x was over the n. So that's going to end up being 2 minus 2xy over, let's see if that will actually factor. We can take 2 out of the top, 1 minus xy. We can take x out of the bottom. That's going to give me xy minus 1, which they're just the negative of each other. So if I multiply through by negative 1 and factor it out, I'll have negative 2 over x. So that is just a function of x. So it looks like this could be what I use, how I get my integrating factor. So mu then would be equal to e to the integral of minus 2 over x. So we don't need to check the other one out. Okay, so let's use that integrating factor. Okay, so that comes out to be e to the integral, actually negative 2, 1 over x dx, which is just log of x. So that's e to the minus 2 log of x, which take the minus 2 back up is the exponent. That's e to the log of x to the negative 2, which becomes just x to the minus 2. So we're going to multiply through by x to the minus 2. So our new equation then will be 2 plus x to the minus 2 times y minus x to the minus 1. Okay, now let's check. Is this one exact? The partial of the m, here's our m now. Okay, the partial of the m with respect to y would just be x to the minus 2. And the partial of the n with respect to x would be positive 1 x to the negative 2, which those are the same. So this is an exact equation. Okay, so now to solve it, we're going to take this equation. We know that the m has to be the partial of some f with respect to x, and we know that n is some partial of the f with respect to y. So we're going to find f by integrating the m with respect to x. And that comes out to be 2x plus the y is a constant, so that's x to the minus 1 over negative. So negative x to the minus 1 times y plus some function that could just have y's in it. So now, so we integrate with respect to, integrate m with respect to x. Now we're going to differentiate f with respect to y. Okay, which should be the n, so we better be this n, so it needs to be y minus x to the minus 1, and now let's go ahead and take the derivative of this. So with respect to y is 0 plus, I have negative x to the negative 1 plus g prime of y, and so I get that g prime of y is equal to just simply y. Okay, so now once I get that, then I know that g of y, I just integrate both sides with respect to y, is y squared over 2. Okay, plus constant, we don't need the constant since we're going to roll it in. Come back up to this form right here and fill in the y squared over 2 for the g of y. So we're going to get that the f of x is 2x minus x to the minus 1y plus y squared over 2 equal to c. This is the f of xy equals c, and so that's in that format. So I'm just taking this right here, filling in the x squared, the y squared over 2. And so that's your solution. Okay, we've learned how to solve separable equations, linear equations, and exact equations. Okay, those are still your three main go-tos for solving differential equations. The next thing we want to do is, if none of those work, is there another method? And the way these will work, there's 4 different methods in this section, and they're going to work by doing a substitution that will transform the equation into either a separable or a linear equation. So let's look at the process here. First thing we want to do is identify the type of the equation. So we need to find out what type equation you're going to have to determine what the appropriate substitution or transformation is going to be. Then you're going to rewrite the equation in those new variables. Then you're going to solve the transformed equation. It should either be separable or linear. Then you're going to go back to the original variables that you used. Okay, so it should be simple enough. Okay, the first type of equation we're going to look at is called a homogeneous equation. If the right side of an equation, you have dy dx equal to f of xy, so you have it in that normal form. If the right side can be expressed as a function of y over x alone, so everything involving the variable could be written as y over x, then we call the equation homogeneous. Okay, so now let's check that definition and see if these are homogeneous. The first thing I want to do is solve for dy dx. So this first one, I'm dividing everything through by dx, so I'm going to have x minus y plus x dy dx equal to 0. So moving the x minus y to the other side, I have dy dx equal y minus x, and then I'll divide by x. Okay, to see if it's the rate, it can be written in terms of y over x, everywhere there's a y, I want to create a y over x, and I can do that by taking the y that's here and dividing it by x. So to do that, I need to divide everything in the numerator and everything in the denominator by x. So I'm going to have y over x minus x over x over x over x. Okay, which leaves me with y over x minus 1 all over 1. Okay, so what we've got here is we've got dy dx written so that it's a function of y over x. That means that we could take the y over x out and put another variable. So if we change this to, let's say that v was equal to the y over x, then this dy dx is equal to just some v minus 1. So we would call this a function of just the function v. So g of the v, which was really just the y over x, is v minus 1. So it makes it a little simpler equation. Okay, so this one is homogeneous because we could write dy dx in terms of just the single variable, thinking of the variable as y over x. Okay, the second one here. Let's solve for dy dx. We're going to have dy dx. I would move the x minus 2y plus 1 to the other side, so that would be 2y minus x minus 1. I'm just skipping a few steps here, over the x minus y. Okay, so I see a lot of x's and a lot of y's in there. Let's see if we can write this just in terms of the ratio y over x. So wherever the y's are, which I have a 2y on top and y on the bottom, I want a y over x in those places. So I'm going to divide every term in the numerator and the denominator by x again. So this is going to be 2 times y over x minus x over x minus 1 over x over x minus y over x. So we've got 2 times y over x minus 1 over x, 1 minus y over x. So can this be written as just a function of the y over x? Could we change the y over x's to just a single variable and it'll be a function of just that variable? And the answer here is no, because of this 1 over x. We can't change that to v and get an equation with just v's at this point. So this one would not be homogeneous. Now there's another equivalent definition for being homogeneous, and the way they state that is if the function, when you replace the x with tx and the y with ty, if you get the same thing as f of xy, then it's homogeneous. So some books use that as the definition of homogeneity. So let's see how that would work with this first one. I've already got, so let's say I'm looking at the equation in this form. If I replace all my x's with tx and all my y's with ty, I would have dy dt equal ty minus tx over tx. Factor out a t, and you get y over x, which is the same, y over x, y minus x over x, which is the same thing as dy dx. So we get the exact same thing that we started with over here. So this is what they're calling the f of xy, not dy dx. Okay? So those are the same. So you would have that it's homogeneous by that other definition as well. Another way that I usually use to look at is if I look at my coefficients of the dx and look at the coefficients of the dy, if they all the terms have the same degree, so x and y and then the x all have degree 1, the power on them is 1. So if they all have the same degree, that's going to have the same effect as these other two definitions. So if you had something like an x squared plus an xy, then again, both these terms are degree 2 because if they're multiplied, you add the degrees. This would be degree 2. So all those would be degree 2. So if I replace the x's with tx and the y's with ty, you would end up getting the same equation that you started with, or get it as a function of just the y over x. So that's another way to check to see if it's homogeneous. Okay, so let's look at an example. When you know that it can be written just as a function of y over x, we're going to make a substitution. We're going to change that y over x to a single variable v. Now, because the original equation had x's and y's and a dy dx, we need to be able to change what is dy dx. So if you take this substitution and rewrite this as y equal to v times x, we've got to figure out what do I replace dy dx with, because we're going to have a dy dx in this equation. So if y is vx, then take the derivative of both sides with respect to x. So we get dy dx, and I need the product rule for v times x. So it's going to be v times the derivative of x plus the x times the derivative of the v. dx dx is 1. So this is just v plus x dv dx. Okay, so this is the substitution you're going to use for dy dx if you let v be y over x. Okay, so now let's solve the problem. The first thing you would need to do is to verify that it's not separable. With that x squared plus y squared, you're not going to be able to separate that. Is it linear? Well, not with that y squared term. Is it exact? Well, this would be the m, and this would be the n. The partial of the n with respect to x would be 2x, and the partial of the m with respect to y is going to be more than the 2x, so it's not exact either. So now we go to trying to find a substitution that's going to work. So we look at the expression, and we want to see, is it homogeneous? Can we rewrite it so that it can be written in terms of y over x, or put in a tx and ty for all the x's and y's and see if your equation's the same, or you can look at the degrees, and looking at the degrees, I can see that they're all second degree, and that's the sign that it's going to work. So let me go ahead and let's change it so that it's in terms of the y over x, just so you can see how that works. So if I were to solve this for dy dx, I'm going to end up with minus the x squared minus the y squared minus the xy all over the minus x squared. So dividing through by that, I'm going to go ahead and split it up into individual terms. Minus x squared over x squared minus the y squared over the minus x squared minus the xy over the minus x squared. And so you see that it's going to be just 1 plus y squared over x squared, which I can write as y over x squared, which is equal to, or minus, or plus actually, the y over the x. So we see that it is just it can be written just in terms of the y over x for the variable. So we can change all those y over x's to just v. Okay, so now that we've already got that, let's just go ahead and start with that. I'm going to replace the y over x with v. And I'm going to replace the dy dx with v plus x dv dx. Okay, simplifying a little further. See, at this point, we should come up with a separable equation, so we may have to clean it up a little bit. Subtract v from both sides. I've got the 1 plus v squared, so v squared plus 1. So I can separate it. I'm going to go ahead and move the x's to the left side. So let's see, dv dx. Okay, so if I want to think of it as cross multiplying or multiplying through by x dx, I'm going to end up with x. I'm not going to end up with x. Okay, I'm multiplying both sides by dx, and I'm dividing both sides by v squared plus 1 to separate the variables. So I'm going to have dv over v squared plus 1 equal dx over x. And we do have a separable equation. So we started off with the homogeneous equation, and it turned it into a separable equation. Okay, integrate both sides. If you recall, the integral of dv, or 1 over v squared plus 1 dv, is just the inverse tangent of v. And the integral of 1 over x dx would just be natural log of x. And we're just going to put one constant. Okay, if we're trying to solve for v, we're going to do it by taking the tangent of both sides. So then we'll have v equal to tangent of go back to your original variable now, which is y over x. So that means our y is equal to x times tangent of natural log of x plus c. And there's we actually got an explicit solution to the differential equation. Now notice with that substitution we have to worry about x, and x equals 0 is a solution here, so we'd also have a solution x equals 0. Okay, so we've already looked at solving separable equations, linear equations, exact equations, and then homogeneous equations that have that special substitution, v equal to y over x. The next type of equation that we're going to look at is one that's of the form dy dx equal to a function of some variable combination. So we're going to be looking for multiples of x plus multiples of y that repeat themselves in that expression. And then if we can replace all of them with that same variable z, whatever z is that variable combination, and have just a function of z remaining, then we're going to be able to use this type substitution. So let's look at the differential equation and see if we can see some repeated sum of multiples of x and multiples of y. So in this problem, you see a y minus x and you see an x minus y. Now, you do not want to take a constant with it, just multiples of x and multiples of y that are added or subtracted. So those aren't the same, but we could rewrite this as dy dx equal minus x minus y, and then minus our 1 plus x minus y plus 2 to the negative 1. So all I did was I changed that first y minus x to negative x minus y to get the duplicate, combination of x's and y's. So now we're going to use the substitution z equal x minus y. So that'll be replaced by z, and this will be replaced by z. So the only thing to do now is to figure out, well, what is an equivalent for dy dx in terms of the z. So take the derivative of both sides. We have dz dx equal 1 minus dy dx, which means then that dy dx is 1 minus dz dx. Okay, so now let's see if we can make the variable change. 1 minus dz dx minus z minus 1 . Okay, now let's subtract 1 from both sides. I'm trying to solve for dz dx. So subtract 1 from both sides. Now multiply through by negative 1. Okay, so now we have a separable equation. We want to get it in, group the z's and group the x's together. Notice there's no x's, but we will have just 1 left on the other side. So rewrite this. I'm going to multiply both sides by dx and divide both sides by z plus 2 minus z plus 2 to the minus 1. Okay. Now let's simplify that a little bit more. We've got z plus 2 to the minus 1 in the denominator. So let's rewrite that. Okay, now just to simplify things a little bit more, I'm going to multiply. I don't want to have that fraction in the denominator, so I'm going to multiply by z plus 2 over itself on the left. So we'll have z plus 2 times dz minus 1. Okay, we have a separable equation. Now it's a matter of just integrating both sides. Okay, now the left side we can integrate pretty easily just using a u substitution. So if I let u equal to z plus 2, And actually, I'm going to let the u be the entire denominator because we have that repeated factor on the top. So z plus 2 squared minus 1, if you take the derivative of that using the power rule, it's 2 times z plus 2 to the first power times 1, the derivative of the inside, and then plus 0. So it's just 2 times z plus 2 dz. Well, that means then that the z plus 2 dz is just equal to 1/2. Let me move this out of the way. So we're just replacing the z plus 2 dz with 1/2 du. And the whole denominator is just the u. Okay, so we have 1/2 of 1 over u du. Now disintegrate. 1/2 natural log of the u equal x plus the c. Go back to your original, we made 2 substitutions here. Go back to what u was equal to. And now let's go back to our z is x minus y. Okay, and I'm going to change the form of this. I'm going to go ahead and multiply both sides by 2. I'll have natural log of x minus y plus 2 squared minus 1 equal to 2x. And I could say plus 2c, but we don't know what c is to begin with, so we're just going to call it c. And now let's get the y away from that natural log by just taking both sides to the e power. So we're going to say e to the natural log equal to e to this whole side. So then the left side becomes just x minus y plus 2 squared minus the 1 equal e to the 2x. Now remember, e to the 2x plus c is the same thing as e to the 2x times e to the c, which could be just a constant c. So we'll just make this c. And then we'll have that plus 1 that we'll move over. So x minus y plus 2 squared is equal to c e to the 2x and then plus the 1. And so that's an implicit solution to the differential equation. We could take the square root and solve for y, but then it's just going to get pretty messy. So there's our solution. So look for this type of variable combination and make the substitution z, and then you should get a separable equation when you do. Okay, the next kind of equation we're going to look at is called a Bernoulli equation. We'll have a first-order differential equation that can be written in this form. It looks a whole lot like the linear equations. Remember, linear first order was an equation that could be written like this. This was the standard form. The only difference is the Bernoulli equation has this extra factor over here, a y to the nth, multiplied by that q of x. So when you have it in this form, it's a Bernoulli equation. The substitution that's going to work will be letting v be y to the 1 minus n. So determine the n from the power up here, and then let v be y to the 1 minus n. And that substitution is going to change it to a linear equation. Okay, so now look at the form. dy dx plus p of x y equal q of x. That's the linear, but if it has an extra y to a power, then we know it's Bernoulli. And you can see here that the p of x would be the minus 5, the q of x would be minus 5 halves x, and the y to the nth is y to the third. So in our problem, it's n equal to 3. So that means we're going to use the substitution v equal y to the 1 minus the n. So v will be y to the negative 2 power. Okay, we're going to need to also change the dy dx out to something with v's. So let's take the derivative of both sides. We have here that dv dx is equal to, I'm going to use the chain rule, the power rule, minus 2 y to the negative 3rd power times the derivative of the inside, because we're assuming that y is a function of x. So times dy dx. Okay, so now that tells me then that y to the minus 3 dy dx is equal to negative 1/2 dv dx. And I'm going to use this to make the substitution. Before I do that, I'm going to take the original equation and I'm going to divide through by the y to the 3rd, which is the same thing as multiplying both sides by y to the negative 3. That's just going to help me to set up the substitution a little bit better. Okay, so now multiplying through by that, I'm going to have y to the negative 3 dy dx minus 5y to the negative 2 equal negative 5/2 times x. Okay, so now making my substitutions. The y to the minus 2 becomes the v. The y to the minus 3 dy dx becomes the negative 1/2 dv dx. And then we'll just have minus 5/2 x. So now we see that it is linear. So to solve this, let's make the coefficient of the dv dx 1. So I'll multiply through by negative 2, both sides. So I'm going to have dv dx plus 10v equal 5x. Okay, so we definitely have a linear equation where v is the variable, the dependent variable. And so let's get our integrating factor. Our integrating factor here is going to be e to the integral of the p of x, which p is what's in front of the v. So we'll have e to the integral of 10 dx, which is equal to just e to the 10x. Multiply through by e to the 10x. This left side then should just be the derivative of the integrating factor times the dependent variable, which is v. Okay, now we're ready to integrate both sides. The integral of the left side will just be the e to the 10x v. The integral of the right side, because of that e to the 10x times the x, we're going to need to do an integration by parts. So let's go over here to the side and integrate 5x e to the 10x by integration by parts. Okay, so I'm going to let u be that algebraic term, the 5x. My dv is going to be e to the 10x dx. The du then is going to be just 5 dx, and the v will just be 1/10 e to the 10x. So this is my u dv. And integration by parts says it's uv minus the integral of v du. So we're going to have uv, which will be 1/2 x e to the 10x minus the integral of the v du. So I'll have 1/10 e to the 10x times 5 dx. So we have 1/2 x e to the 10x minus a 1/2, but then I have the integral of e to the 10x, which is 1/10. So let me just put the 20 here, e to the 10x. So that should be this integral right here. So we'll have 1/2 x e to the 10x minus 1/20 e to the 10x. Well, plus c. Don't forget the plus c here. Okay, so now if we were solving this for v, we would have that v, I'm going to divide everything through by e to the 10x, which is the same thing as multiplying everything through by e to the minus 10x. It's important that you have that c because that's going to be where that's going to be remaining. Okay, so we have that v is equal to 1/2 x minus 1/20 plus c e to the minus 10x. And now we go back to our original variable. Remember that the v was just the y to the negative 2 up here. So v is y to the negative 2. I'll write this as x over 2. So you could leave it that way, or we could write that as 1 over the y squared. You know, I would probably leave it that way. If you needed to solve it for y, I would rewrite this as 1 over y squared equal to this whole thing. One little trick I'll show you here is if you have 1 over something, take the reciprocal of both sides. So the reciprocal of the left is just y squared. The reciprocal of the right is just 1 over all this. Okay, then you could take the square root of both sides, but I wouldn't go so far. I would just leave it here unless they really wanted you to have it in a different form. But there's a lot of ways you could simplify and change the looks of that. Now we want to look at modeling growth or decay. Okay, so the specific example we'll look at first is population. So let's say that the growth rate is proportional to the population present. So if we're looking at the change in the population over time, which is a derivative, the rate of change of the population, proportional means that it's some constant times what it's proportional to, which is the population. So this is the model that we would use just based on the fact that we know that, or we're told that the growth rate's proportional to the population present. And so this is our constant proportionality. Okay, so one thing we'll need to find is based on population at a certain time, we'll be able to find out what that constant proportionality is and how quickly it really is growing. Okay, so this particular model is called the Malthusian model. So when you see homework where it says to use assume the Malthusian model for growth, population growth, it's also called the exponential growth law growth. So this is the model you'd use. The population at time 0, which is p of 0. So here's t equal to 0. The population is p naught. So this will be the typical population for this Malthusian model. Okay, so now if the k, the constant proportionality is positive, then we know it's a growth rate. If the k is negative, we know that it's a decay. Okay, so now let's look at a specific example. We're told that in 1790, the population of the United States was 3.93 million. So now instead of using 1790, let's just use that as our starting point. So we'll say that t is equal to 0 in the year 1790. So then every other year will be relative to that. So t equal to 0, the population in that year is 3.93, and we'll assume million. Okay, then we're told that in 1890, the population was 62.98. Okay, so using the Malthusian model, so we know that that says that the rate of change of the population over time is proportional to the amount of population at that time. Okay, and we've got our initial condition, p of 0 is 3.93. So solving this differential equation, we see that it's separable. So we would rewrite it as dp times 1 over p equal to k times dt. Okay, so then to solve for p, which will be a function of t, okay, so the dependent variable is p, the independent's t, so we're just going to integrate both sides. Okay, so we have natural log of p, that's absolute value, but we're assuming the population is positive, equal to k times t plus some constant c. Okay, so now solving for p, we're going to take e to both sides, so e to the natural log of p, which will just be p, will be e to the kt plus c. And we can break that up into, using the base, the exponential base will be e to the kt times e to the c, just using one of the rules for exponents, and that's going to be our p. Now, e to the c was just an arbitrary constant. We didn't know what it was to begin with. E to the c is also a constant, so I'm just going to replace the e to the c with just a constant c. It's different from the one previously, but we'll find that when we actually solve the initial value problem. Okay, so now we're told that the population at time 0 is 3.93. So we can use that to determine the constant of proportionality. So we know that the population, which is 3.93, we're letting t equal to 0. So that tells us the c is the 3.93, which is the initial condition. Okay, so the c here in this model is the initial value. So if you just want to get the general solution for this is p of t will be the p naught, it's always going to be the c there, times e to the kt. So that will be the solution to this differential equation, where you're also told that p of 0 is p naught. So we could have just gone straight to that, but we needed to practice solving it. Okay, so for our particular problem then, we know that p of t is 3.93 e to the kt. Okay, so now this is where we're going to use the other piece of data, the fact that in 1890 the population was 62.98. So we know then that p of 100, because if t equal to 0 is 1790, then letting t be the number of years, t equal 100 will be 1890. Okay, so using this data, we're going to be able to solve for that k. So we have 62.98 equals 3.93 times e to the 100k take the log of both sides, and we get 100k. The natural log of both sides. Natural log of e to a power is just the power. And so our constant of proportionality then will be 1 over 100 times natural log of 62.98 over 3.93. Okay, so just using your calculator, that comes out to be approximately 0.027742. Okay, so that means our equation then, the p of t, just going back right here, and I'm going to fill in the k value. And there's our formula for the population at time t. So we can use that to approximate the population at any time using t equal 0 in the year 1790. Now, the Malthusian model didn't take into consideration the death. All they considered was death by natural causes, and not death based on things like premature death, because of malnutrition or not having enough medical supplies, different kinds of diseases, violent crimes, and things like that. So a more realistic model is called the logistic model. Okay, now the logistic model starts with the fact that the rate of change of the population is proportional to the current population. Okay, And in that case, let's use a K1 for that constant proportionality. And then we're going to subtract off, and we're going to assume that the death rate is proportional to the number of two-party interactions. Well, if you have a population of size P, the number of two-party interactions will actually be P times P minus 1 divided by 2. So that's the number of different ways, that population could be split into groups of 2. Okay, so we're going to assume that the death rate is proportional to that. So we're going to use another constant, and we'll just call it K3. Okay, so this is the being proportional to the current population, which is what the Malthusian used, and then this is taking into account a death rate, which is that two-party interaction. Okay, so if you take this and just multiply it all out and rearrange it, you get something of this form right here, which is called the logistic model. Okay, so if you multiply this out, you end up getting that the A that's down here just ends up being the K3 divided by 2, and then what they use for the P1 is 2K1 over K3 plus 1. So you'd get that if you just calculated this and tried to put it in this other form. Okay, so let's just start with this form being the logistic model. Now, in this, if you remember, this is a normal form, and you can see that there's equilibrium points here. This derivative will be 0 when P is 0 or when P is P1. Okay, so those are equilibrium solutions for this derivative. Okay, so what that means is those are the places where you're going to have horizontal tangent lines. That's where the derivative is 0. So that's where your solution curve is going to be flattening out, having a slope, a tangent line of slope 0. So if you drew a graph with P equal to 0 here and P equal to P1 here, then the solution curve, if the value, the initial condition, is between the P and the 0 and the P1, which let's assume that this P naught is someplace in between P equals 0 and P equal 1, then a solution curve is going to look like this. Okay, as the population gets closer to that P1, it's going to start flattening out. Okay, so that's called a limiting factor. So based on some environment, based on how much food's available or predators or whatever, you're going to tend to have a limited number of size population that could grow based on those conditions. Okay, if the initial condition actually started off higher than that, then it's going to end up settling down, coming back down to that P1. So if it gets higher, it's going to start, having a larger decrease in population until it gets back down to that P1. So that P1 is that equilibrium solution that is really your maximum population over time as time goes on. Okay, so now if you were solving this differential equation, okay, this is separable. I would rewrite this as 1 over P times P minus P1. And again, keep in mind this P1 is that limiting factor. So what the population would approach as time goes on. And equal to minus, so we've got this dP equal to minus A times dt. So all I did was I just separated the equation. Integrate both sides. Okay, now to be able to integrate this, you're going to need partial fraction decomposition. So let's just look at, if we were to rewrite 1 over P times P minus P1 as the sum of two fractions, one with the denominator of P and the other one with P minus P1, okay? Remember partial fraction decomposition, this is the same thing. I'm multiplying through by the common denominator. So A times P minus P1 plus B times P would equal to 1. Okay, so now just pick a couple values of P. I'm going to pick the easy ones. P equal to 0 would tell me then that 1 was equal to minus A P1. That tells me that the A is minus 1 over P1, and the P equal to P1 would give me that 1 was equal to B times P1. So that tells me that the B is 1 over P1. Okay, so now this integrating this leads us to the integral of, I've got the a on top, so that's minus 1 over p1 over p plus the integral of 1 over p1 over p minus p1, and that's just going to be minus a times the integral of dt. Okay, so that's going to give me minus 1 over p1, natural log of p, we're assuming the population's positive, plus 1 over p1 times natural log of p minus p1. Okay, combining the left side, I'm going to rewrite this as 1 over p1 times natural log of p minus p1 minus natural log of p. Okay, combining the logarithms, I'm going to go ahead and get rid of this p1. I'm going to multiply both sides by it. So I'm going to have log of p minus p1 over p. That's just using the difference rule, the quotient rule for logarithms. That'll be minus a p1 times t plus some constant. Okay, raising, taking e to both sides. We're going to have e to the left side, which gives me p minus p1 over p. Now, if I simplify that, I can break it into two fractions. That's 1 minus p1 over p. And then the right side will be e to that power. So e to this whole thing. And I'm just going to break it into two parts. So that's just going to be e to the minus ap1t times e to the c, which again, this is just a constant. So this will just be c e to the minus ap1t equal to 1 minus p1 over p. Okay, so now I'm going to go ahead and solve this for p, and I'll do that by moving this term to the right side and this one over here. So I'm going to have 1 minus c e to the minus a p1t equal p1 over p. Now I'm going to flip both sides. So I'm going to have p over p1. So p is going to be 1 over this I had that p over p1 on the right. I'm going to go ahead and multiply this side by p1. Okay, so that gives me the population, p at t. Okay, now notice it depends on the p1 value, the a value, whatever of course we didn't have specific numbers in here for the original problem. Whatever the p1 is, whatever the a is, and then we just need to figure out what the c is. So let's determine the c using the initial condition. So if we know that p of 0 is p naught, then I'm going to plug in t equal to 0. So I'm going to have p1 over 1 minus c e to the 0 equal to p naught. So solving for the c, I've got p1 over p equal to 1 minus c. I'm just multiplying both sides by 1 minus c because the denominator is 1 minus c, and then dividing both sides by the p naught. Okay, so that tells me then that the c is equal to 1 minus p1 over p naught, or getting a common denominator, p0 minus p1 over p0. So that's the constant. So let me rewrite this equation then. I have that p of t is the p1 over 1 minus p0 minus p1 over p0 times e to the minus a p1t. And now if I multiply both sides, the left side by p0 over p0, just to clear the fraction out of the denominator, I get that p of t is equal to p0 p1 over p0 minus p0 minus p1 e to the minus a P1T. And one more thing, if I go ahead and distribute through or take a negative out of this second parentheses here, I can turn that around and make this sign a plus in front. So just a simple little algebra. I'm going to have P of T is P0, P1 over P0 plus, I'm just turning that second one around by taking a negative 1 out of that parentheses. I'm just trying to match the formula the book uses. So, okay, that's the population. Okay. And again, P1 is that limiting factor. So it'd be the limit as T went to infinity. Okay, so now let's look at an example that would use this formula, this logistic formula. Okay, now that's going to be the results. We're going to come over here and actually look at the problem first. Okay, we're going to take 1790 to have the population of 3.93 million again. That's the initial population. And now we're going to have two values. In 1840, the population is 1707. And in the year, this is the year 1890, the population is 62.98. So what they've given me is they've given me 2 points here. So I'm going to know that when T is equal to 50, because remember we let T equal 0 be 1790, so this will be T equal to 50. P of 50 will be 17.07, and P of 100 will be 62.98. Okay, so now if we take that formula that we just derived, okay, and plug in these for the T value and for the P value, we get these two equations. Okay, our initial population was 3.93, so we're using that for P0. Plug in the 50. Okay, and the second one would give us 62.98 is equal to 3.93. Okay, we get a really ugly system of equations. These aren't linear. To solve them, you'd need to do it numerically, except because the years end up being 50 and then twice that. The book goes through a formula in problem 12 where you can actually solve what these are going to be without having to use some sort of numerical solver. So just giving you the answers here, I just really want you to see the values here. We find that P1, so solving this system, you would get that P1 was approximately 251.78, and P2, or the A, which was the other unknown, so P1 and A were the two unknowns in this equation. The A came out to be 0.0001210, so that your logistic equation came out to be this: 989.5 over 3.93 plus 247.85. Okay, so that would be the function. So now if you wanted to look at some of the values at different times, you could calculate the population at those times. Now what I want to look at though is I want you to see the table of values here and see how those compare to using the Malthusian model. So this is the Malthusian model right here, which was that first example, and then this is using the logistic model. So notice at 1790 they both had 3.93 because we set them up to have that initial value. In 1840, the Malthusian model gave us a population of 15.73, versus the logistic gave us 17.07. Okay, in 1890, the population, we fixed it to have that same value. So we determined our values for A and P1 so that it would have those values the same. So the starting value and that value after T equal to 100. So now look at the U.S. Census here and actually see what the population, so what we're doing is we're looking at values, at data that was collected to see what model best fits the population growth, and then you use that to model other situations. So notice the population by the census was 1707. Now, the logistic model, of course, we actually used that value also to pin it down there. So we used that as a condition so that it actually made sure it was accurate at that point in time as well. So it gives us more information to try to get the model to be more accurate if we can use more than one value. So we used this value when we were actually getting our population model. But notice the other values, the ones that weren't part of our, fixing the equation. In 1810, 7.24 is definitely closer to that logistic model than the Malthusian. 9.64 here, the logistic model was much closer. And the 12.87, the 12.82 or 3, whatever that is a closer approximation. So notice that the Malthusian model each time is a better approximation to what the actual census gave us at those years. So just that extra bit of information where you're using more data points to, correct it, makes that logistic model a better approximation for population in the United States. It depends, a lot of it depends on the population size. The larger the populations, you need a little more correction too. Okay, so previously we used Euler's method to approximate a solution to a differential equation. What we want to do now is find a way to adjust that to make it, a better approximation. So this is called the improved Euler's method. Remember, Euler's method said that we started with the point x naught, y naught, and we used the function. We had that the slope y prime was equal to some function f of xy. Okay, so this gave us the slope of the tangent line. Okay, so we used that slope at the point x naught, y naught to get this tangent line, and then we looked at the next x value, which was some distance h away from the initial point, and we used this formula to find the y value on the tangent line for that x. So we found that the y1 was equal to the previous y value plus the slope. So we found the slope at the previous point times that h value. Okay, and that was just using the tangent line. That's just the equation of the tangent line passing through the point x naught, y naught with the slope f of xy. Okay, so that's how we got that. And then you can see for this particular curve that that y value is not that great of an approximation. So what we want to do is find a way to adjust it and correct it before we just use that for the y value for the approximation for that curve. So what we're going to do is not just use that. We're going to first calculate what that y value would be using the tangent line. So now we have this point x1 y star at x1, so y1 star. So that's going to be that initial point on that tangent line. But what we're going to do, instead of using that for the y, we're now going to make an adjustment to finding the y by looking at the slope at that new point. So if we could find the slope at this point right here, by plugging it into this equation, we're going to get some new slope. So let's say that this was the slope determined by that differential equation at the point x1, y1 star. Well, you can see that's different from the initial slope of that tangent line that we used to get it. So what if we average those two slopes? So instead of saying that this is the slope or that this is the slope, we're going to take the average of the two. So what this value is here is the average of those two slopes. We're taking the slope at that initial point, which was the f of xn, yn, and then we're going to get the slope at that new point, which is the f of xn plus 1, y star n plus 1, average it, divide by 2, and then we're going to multiply by the h and add the y, and we're back to using this formula. All we're doing is we're adjusting what we're using for that slope by averaging two slopes, the slope at the initial point and what the slope of that projected point would be, and using that as the slope that we're going to use then from this initial point. And then once we use that slope, which is the average slope of those two, we're going to get the point on that tangent line at this x value. And you can see in this picture that that y value, which is the y value on that tangent, that new tangent line, is a much closer approximation to the y value on that curve at that point. So that's the idea behind the improved Euler's method. You're using what's called a predictor corrector method. So you're predicting it using Euler's method, and then you're correcting it using the new information, the slope at that new point, combined with the slope at the previous point. So let's see what that might look like. Okay, so I want to use improved Euler's method to get an approximation for y of 1.5. So we're going to let the x equal to 1.5. That's what we're trying to calculate. And our initial value has x equal 1, the y is 1. So this is our differential equation. So this is going to give me the slope of the tangent lines at each point. So what I want to do is build a little table. I'm going to look at the x value, and we're starting at 1. We're going to look at a predicted value each time, and then we're going to get what the real value is going to be by using the corrector. Okay, so we know that for the first point that the y value is 1. So now the next x, we're going to use x equal 1.1. We're going to use a step size of 0.1 as they indicate up here. Okay, and then we'll go to 1.2. I'll go through pretty quickly because this isn't just kind of tedious to go through all this. So first, use Euler's method to find the y value at the point x equal 1.1 using the initial point 1, 1. So we know that we have this formula for Euler's method. So we'll do this. We'll say this is n and this one's n minus 1. Okay, and that'll be times 0.1 each time. Okay, so using that formula, our y1 predicted value will be the previous y, which is 1, plus the slope. Now I'm just going to use this 2xy. It's 2 times the previous points x and y, which is 1 and 1. Okay, and then times our h, which is the 0.1. So again, this is our slope calculated from this. Okay, so that's going to be 1.2. That's our predicted value. We're not going to use that. We're going to now find the average of the two slopes. So we're going to now use this formula. So this is for the star. Plus, we're going to look at f of xn yn star, and then times our h. Okay, let's go back to here. So then our y1 will actually be the previous y. Now we're going to look at two slopes. We're going to look at the slope at the original point 1, 1. And now we're going to look at the slope at the projected point 1.1, 1.2. And each time I'm using this formula for the slope. Okay, so when you find that value, it comes out to be 1.232. Okay, so that's what we'll actually use for the y value. So now we can ignore this y star for that point. Okay, now we're going to y2 star. use the previous point, the y value. I need the slope at that point. That gives me the slope times the h. That gives me 1.50304. And we're just going to use that to get the real y, or not the real one, the estimated y value. So now our y2 will be, again, the previous y, and now take the two slopes, 2, 1.1, 1.232, plus 2 times 1.2, 1.50304, that's the estimated value, divided by 2, and then times the 0.1. And that comes out to be 1.5479. So now that's what we're going to use, and we're going to ignore this one. Now the y3 star. Use the previous y value, the slope at that point, using Euler's method here to get the predicted value. Oops, not dividing. And then times the 0.1, and that comes out to be the 1.9194. Now we're going to use the adjusted value. So again, the previous value, average the two slopes, now we're going to use the 0.13 and 1.9194 times the 0.1, and that comes out to be 1.9832. Okay, now predict the fourth one using just Euler's method. The slope, and here's our h value. That comes out to be 2.4988. Okay, now use that to adjust 1 point previous value. Let's average the two slopes. .4, and then the projected y value. Oops, 8 times the 0.1, and that comes out to be 2.5908. Last one, y5 star, previous y value, plus the slope, times the h, so we get 3.3162. Okay, and now our y5, which will be the estimated y value for x equal 1.5. Two times the 1.5 and the estimated y value. And that one comes out to be 3.4509. Okay, so that's our estimated y at x equal 1.5. And if you look at the table over here, you'll see the values using the improved Euler's method. I just did the step size h equal 0.1. You could do it with a smaller step size and expect to get a greater accuracy. But here was the y values that we just predicted. This is the actual values. If you solve this, it is a separable equation, so you could solve that and get the exact equation now, get exact solution. And you can see that the error is very small. This is a 1% error to what the value was at x equal 1.5. So improved Euler's method, I don't have the values here for just Euler's method, but you saw them, we calculated them originally, and they were quite a bit off from the improved Euler's method. And there's other methods that use this same idea of averaging out those slopes. You could average the slopes of several points along the way if you wanted to. And we'll look at other methods that do that, even do weighted averages. And you can set those to any way you want to weight them. So improved Euler's method, and then you'll have some homework and have another notebook to help you with that. Okay, so now let's look at some of the higher order numerical methods. So we're going to start with Taylor, and then the next lab will get to the Runge-Kutta method. Okay, so we want to obtain a numerical approximation for the solution to this initial value problem. Okay, we're going to assume, using the Taylor methods, that phi sub n is the exact solution. Okay, so if that's the exact solution, then I can plug it in for the y values up here. So we're going to get this then is our new initial value problem. Okay, so now what I want to look at is I want to look at the Taylor series. Recall the Taylor series says that if you have a function f where the series converges, that f of x would be equal to the f evaluated at some x naught, some initial condition. I'm going to use x sub n as that point that it's evaluated at, plus the f prime of x sub n, and then times x minus x sub n, plus f double prime of the x sub n over 2 factorial times the x minus x sub n squared, and you continue so that you've got the nth order derivative at that x sub n over n factorial times x minus x sub n to the nth power. So there's your Taylor series. So if we plug in the phi then for the f, we're going to have the phi sub n at x sub n. We have the phi prime of x sub n here. Now the x minus the x naught is going to be our h. Okay, so we've just got an h, and we've got our phi double prime of sub n x sub n over 2 factorial, and then here's our h squared. Okay, and then so on. Okay, so that's going to give us our Taylor series about the point x sub n. Okay, so if we're looking for our recursion formula then, if we know that phi sub n at that x sub n is the y sub n, then we can just replace this then with the y sub n. So this is going to be our series, gives us our recursion formula. Notice I'm replacing the phi prime. Phi prime was just the f evaluated at that x sub n. So we've got this. And then at each step then, we're just taking a derivative. So phi prime, double prime of the n then would be the derivative of the f. Okay, so all I'm doing then, and they're just going to leave it this. So we actually need to do a little more to get that derivative, because that's a function with 2 variables. So we're just going to leave it for now with this phi double prime. Now notice if we drop the last terms and just took that first order term, all we've got is we've got the Euler method. So using the Taylor method, we're just going to get more accuracy by adding more terms, getting a larger polynomial than just a linear, that tangent line to approximate it. So what I want to find then is, what is this phi double prime? Okay, we know that phi prime sub n is the f of x phi sub n, but how do you take the derivative of that? How do we get that the phi double prime? So now keep in mind that this f here, that's a multivariable function. So if you recall from Calculus 3, the ones of you that have had it, we've got a function f that has 2 variables. Okay? So let's say that it's some, I'm just going to use the 2 variables x and y right now. So let's say it's some f of xy. Okay? So we'll just call this our phi prime. Okay, so each of these, though, we know x is a function of x and the y is a function of x. So if we're trying to take the derivative of this multivariable function with respect to the variable x, and we know y is a function of x, then using the chain rule in Calculus 3, this will be the partial of the f with respect to x times dx. Remember, take this branch, its derivative, Since f has two variables, you have to do partial derivatives here and over here. And then this will just be, since there's just one variable, that's the derivative of x with respect to x, and the derivative of y with respect to x. So we have partial, taking this branch here, times this branch, plus, now I'm going this branch times this branch. Okay, so that's given me the derivative of this f, which will be the phi double prime. So we're taking the derivative of this function with respect to x. Okay, it'd actually be a partial one. Okay, so this is the form that we're going to use to get the derivative of that multivariable function that we were given with the y prime. Okay, so what that means is then that we have to take the partial of the f with respect to x, just times 1, plus the partial of the f with respect to y times dy dx. Okay, and that's assuming that we're given this function y prime or phi prime equal to f of xy. So that's how we're going to get phi double prime. Okay, so we're going to use that in an example. Okay, so we want to find the recursion formula for the Taylor polynomial of order 2. Okay, so we know that that's just going to be I'm just going to use a single x instead of worrying about the x sub n. Okay, so I'm just writing the recursion formula for finding the next value of phi. Okay, so we're looking at specific values xn, yn at each point to get the next value. Okay, so, and we just also found that to find the phi sub n double prime, we're going to take the partial with respect to x, and then we're going to evaluate that at x sub n, y sub n, and then plus the partial of f with respect to y, again evaluated at xn, yn, times dy dx. And we know dy dx, we're given dy dx. Okay, so let's go ahead and find, for this particular function, we need to apply the chain rule. Okay, so this is our f of xy, and we know that the partial of the f with respect to x, okay, will be cosine of xy times the derivative of the xy, it's a composition, so we use the chain rule. The derivative of xy with respect to x will be y, and then we know that the partial of the f with respect to y will now be cosine of xy times the derivative of the xy with respect to y, which will be x. Okay, so this then replaces this part. So we need to evaluate x and y in, and this replaces this part. So we still have this product over here of the dy dx, which is just the sine of xy. So let's put it all together and get our conversion, our recursion formula. Which is just our y sub n plus 1. Okay, this f of x sub n, y sub n will just be the sine of x sub n, y sub n. Okay, so that's the h sub n, x sub n, y sub n, plus the h squared over 2. So I'm following this formula right here. Here's my y sub n. Here's my h times the f of x sub n, y sub n. And then the h squared over 2 times the phi double prime sub n of x sub n, which is the big one. Okay. So this whole thing then, the partial of f with respect to x, which is y times cosine of xy, this right here is this, plus the partial with respect to y, which is this, and then times the dy dx, which is this. Okay. Now we could simplify this. If you notice, we have sine times a cosine of the same angle, and if you remember your formulas from trig, sine of a double angle is equal to 2 sine of x cosine of x. So all we've got is we've got xy in place of the x's here, so that's just going to be sine of 2xy would be 2 sine of xy cosine of xy, just plugging in xy into the identity. And so that means that if I want to solve for this, it's just going to be half sine of 2xy. Okay, so I'm just going to change this out to 1/2 sine of 2xy. And that's not necessary. That's just the way the book had done it, so I'm simplifying it like that. So we're going to have x over 2 sine of 2xy. Okay, now this is supposed to be evaluated at x sub n, y sub n, so I will do that right here. Okay, so there's your recursion formula, and we also know that x sub n plus 1 at each step will just be the x sub n plus the h. So this is one of the recursion formula. And one last little bit is, don't forget the initial condition. So we're going to start with x sub 0, y sub 0 equal to 0 pi. And then you can find the next values from there. Okay, now we're going to look at a mass spring oscillator. A damped mass spring oscillator consists of a mass M attached to a spring that's attached to one end. Okay, we want to come up with the differential equation that governs the motion of the oscillator. We're going to take into account the different forces that act on it due to spring elasticity, a damping friction, and then other external influences. Now, when that mass is still and the spring has not been stretched or compressed, we call this equilibrium position. Okay, that's where the displacement of the mass is 0. Okay, now if they stretch it and move the spring, the mass outward a distance y, then that movement, that stretching of the spring, is going to be opposing the spring. Okay, so we're going to look at Newton's second law that's going to give us that differential equation. Now, the most commonly encountered differential equation is from Newton's second law, which says that force equals to mass times acceleration. Now, if y gives us the position function, then remember that the second derivative of y is the acceleration. Okay, So we have acceleration is the second derivative of y with respect to t. So what we're going to have then is we're going to have a second order differential equation. Force equal mass times acceleration will be mass times the second derivative of y. Okay? So that's the force exerted from this spring. Okay, so now, like I mentioned, if the spring is unstretched and the initial mass m is still, we call the position in equilibrium. Okay, so the system is in equilibrium at that point. So the coordinate y will be the displacement from equilibrium position. Now, so if this is equilibrium and you move the y, you're stretching the spring out to the right so that this is a distance y. We're gonna just have the convention that this is going to be a positive displacement. Now, when you release the mass, and it's going to cause it to oscillate back this way, a distance this direction is going to be negative. Okay, so you just have to accept some convention to start with, and we're going to choose to the right positive and to the left negative. Okay, so now when the mass is displaced from equilibrium, the spring will be stretched or compressed at that point, and it's going to exert that force that's resisting the displacement. Okay, now most springs, this force will be proportional to the displacement y. Now remember, proportional means that it's some multiple times that value y. So Hooke's law tells us that the force of the spring will be equal to negative k times y. So this is the proportion. K is that constant of proportionality. It's called the spring constant, or the stiffness of the spring. And then y, of course, is that displacement. So that force is a multiple of, or directly proportional to, that displacement y. Now the negative here is reflecting the opposing nature of that spring. Okay? Now Hooke's law is only going to be valid when there's small displacements. If you really stretch that spring out or really compressed it hard, you won't have that same proportion. Now look at a couple examples down here. This is just a regular sinusoidal oscillation. If you have a stiffer spring, you're going to have a greater frequency of oscillation, as demonstrated in this picture. If you end up with a heavier mass, the motion's going to have less frequency, as demonstrated in this graph. Okay, so now, the next thing, we've looked at the spring constant. The next thing we want to look at is friction. Okay, so for vibrational motion, okay, this force usually is modeled by looking at a term that's proportional to the velocity. Remember, if y is a position function, then the derivative of y is the velocity. Okay, so the force that's exerted from the friction then will be a multiple of the velocity. Okay, so the b here is that damping coefficient. Okay, that's that multiple of velocity. Again, the negative sign is reflecting that opposing nature of the force. Okay, so we have friction now, and we also have the spring constant. Okay, so now the other forces that occur, that act on this oscillator, are usually external to the system. Okay, it could be something having to do with gravity, magnetic fields, electrical fields. So most of those have something to do with shaking the supports that are holding the system. Okay, so right now we're just going to lump them all together and have a single known function, the force related to those external systems, those external factors. Okay, so what Newton's law tells us then is that in this mass spring oscillator, the mass times acceleration will be equal to all of these forces. So the spring constant times y, so that's that multiple of the spring constant, of the position function. We've got the multiple of the velocity, which is the friction. Okay, here's the spring constant. And then we've got our external forces. Okay, so this is the equation that we're going to use to model the spring oscillator. Okay, notice it's a second order linear differential equation. Now we're going to learn how to solve these in chapter 4, but right now I just want to verify what some of the solutions might look like to this differential equation. Okay, so I want to verify that if b is equal to 0, okay, so that's that damping factor, and the external forces are 0, the equation that we were looking at, which was the mass times the second derivative plus the damping times the first derivative times the velocity plus the spring constant times the position equal to the external forces. This becomes the mass times y double prime plus just k times y equal to 0, since we're assuming that b is equal to 0 and the external forces is equal to 0. Okay, so this is my differential equation. And I want to show that y equal cosine of omega t is the solution to that. Now, omega here is called the angular frequency. Okay, and that gives you how many radians per second occur in this oscillation. Okay, so we want to show that that will increase when k increases and it decreases as m increases. Okay, so looking at y equal to cosine of omega t is the solution. I need to fill in the y here and the second derivative here. So y prime will be omega, negative omega times sine of omega t, it's taking its derivative, and y double prime is minus omega squared times cosine of omega t. Okay, so now plugging those into this differential equation, we'll have the mass times minus omega squared cosine of omega t plus k times cosine of omega t equal to 0. Okay, to pull out the cosine of omega t, we'll have minus m times omega squared plus k equal to 0. Okay, so notice that this will be 0 when this expression is 0. So minus m omega squared plus k will be 0 when omega squared is equal to k over, we'll have negative k divided by negative m, so it's going to be k over m. So that means that omega will be the square root of k over m. Okay, now notice that when k is larger, omega is going to be larger. So if k increases, omega will increase. And notice if m increases, that means the denominator here is going to get bigger. That means that omega will decrease. Okay? So as the spring constant gets larger, omega, the number, that frequency of the oscillation will get more and more, as we showed in that last picture over here. Where'd it go? Okay, so this was the picture where the spring constant is greater, meaning it's stiffer spring. You have a much more frequent oscillation. And when the mass gets heavier, you have a less frequent. So that meant the omega was getting smaller. So the frequency is less. Okay, so that's you know, the same thing that's shown in that picture over there. Okay, so now let's look at damping. So most of the time, you know, when damping is present, you're going to have the oscillations die out. So here's one situation where there's a low damping involved, and it might be something like a tuning fork or a crystal oscillator where it's going to maybe slow down the frequency of the oscillations, but they still are there, you know, and they just dampen out over time. Now, another situation that you'll have when you have a very large dampening is something like our car suspension systems. We don't want the oscillating, so we want that dampened, you know, pretty quickly. So you're going to have this type of situation demonstrated here where the oscillation stops quickly. Okay, so that would be a very high damping. Okay, so let's look at some examples with some dampening. Okay, so I want to verify that this exponentially damped sinusoidal system given by this is a solution when you have no external forces, you have the mass of 1, you have the spring constant of 25, and you have a damping factor of 6. Okay, so our differential equation then will be mass times second derivative plus the um, damping times the velocity plus the spring constant times the position equal to the external forces. Okay, so we have mass of 1, we have a damping of 6, and we have a spring constant of 25. Okay, so I just want to show that this solution satisfies this differential equation. So let's look at the derivative of this. Okay, so I need y prime. Now I'm going to need the product rule since both of these are functions of t. So I'm going to have the derivative of e to the minus 3t times the cosine of 4t, and then plus e to the minus 3t times the derivative of cosine of 4t. So negative 4 times sine of 4t. So just cleaning this up a little bit. Okay, now I need a second derivative. Okay, now I have to take derivative using the product rule for each of these two terms. So I'm going to have the derivative of minus 3 e to the minus 3t will be 9 e to the minus 3t times the cosine of 4t. Okay, then minus 3 times e to the minus 3t times the derivative of the cosine of 4t, which will be another negative 4 sine of 4t. Then I'll have plus 12 e to the minus 3t, that's the derivative of the first term, times sine of 4t. And then I'll have plus negative 4 e to the minus 3t times the derivative of sine of 4t. Okay, so cleaning that up a little bit. Okay, and it looks like we can combine some like terms here and here. So we're going to have and here and here. Okay, so now let's show that they satisfy this differential equation. We're going to replace y double prime with what we just found. Plus 6 times y prime and then plus 25 times y. Okay, so let's collect like terms here. We have a cosine of 4t. We're going to have a minus, so we have minus 7, we have minus 18, and we have 25. Looks like 0. Okay, so 0 cosine of 4t's. Then we have 24e to the minus 3t times sine, and this 6 times this minus 4 is going to give us a minus 24 sine of 4t times the e to the minus 3t. So we have 0 equals 0, which shows that it is a solution to that system. Okay, so now let's look at one more example. We want to verify that the simple exponential function is a solution of equation 3 with these constants. So m is 1, b is 10, 25 is k. Okay. So now looking at this, we have y prime equal to minus 5e to the minus 5t, y double prime, 25e to the minus 5t. Plugging those in, oh, I need to erase it. Okay, so we're going to have 25e to the minus 5t for y double prime, plus 10 times y prime, and then 25 times the y. Okay, so you have 25e to the minus 5t minus 50 plus 25, all e to the minus 5t, and you get 0 equals 0. So that does, we have just a simple exponential function. Now if you want to look at the motion defined by that, remember the exponential function is just going to die out like that. So our solution here, when we have a strong spring constant and a big damping, is just going to look like that. Okay, in this first example up here, if we were to graph this exponentially damped sine, the external function, that's going to be one where you're going to have an oscillation. It's going to be similar to that picture in the previous problem, where you have an oscillation, starts an oscillation, but it's going to end up dampening out and kind of going, flattening out because of the exponential function. Okay. Now there's situations where when you have an external force that's sinusoidal, that it can actually cause the system to be somewhat erratic. So notice here in this problem how it's kind of erratic at first, but then it kind of settles down to a certain motion and gets in sync with the motion, the oscillation. Okay, so there's certain times when you have that sinusoidal type of force that's interacting with it. Things to do with sound systems, or if you're bicycling over a railroad track, amplifier type circuits, ocean tides, things like that. So engineers have to be careful though, because sometimes when you have those type of systems that have a certain frequency and it kind of gets in sync with the motion of the spring, it can actually bring down a bridge. It's called resonance. So that structural engineers have to be very careful that when they have a product that it doesn't resonate with the vibrations that might be external to that environment. So so just be aware that there are situations where you have to be careful about that external force. Okay, now let's look at second order constant coefficient differential equations. Okay, the form of a second order constant coefficient differential equation will be this. You'll have a constant times the second derivative of y plus a constant times the first derivative of y plus the constant times y equal to some function of t. Okay, now for it to be a second order equation, the a can't be 0. Otherwise we'd have just a first order differential equation. Okay, we're going to, before we study that general second order constant coefficient form, we're going to look at what's called the homogeneous second order constant coefficient differential equation. Now homogeneous just means that we're going to assume that the f of t is equal to 0 in that form. So we're looking at this special case where the f of t is 0. Okay, it ends up that there is a relationship between solutions of this homogeneous equation and the non-homogeneous equation. So when we're solving these second order constant coefficient equations, we're going to first find the solutions to the homogeneous second order differential equation by setting that f of t equal to 0. Once we get those solutions, then we'll be able to build a general solution of the homogeneous system and homogeneous equation, and then we're going to be able to take the f of t and find a solution to the non-homogeneous equation. Okay, so it ends up that when you have this homogeneous second order constant coefficient, this number 2 here, that a solution will look like this. It's going to be e to a power where the power is some constant r times t. So what I want to look at is, let's assume that y was equal to e to the rt, and plug that in. If it's a solution, then we should get an identity when we plug e to the rt in for the y. So we'll need to have y prime, which we know is e to the rt times r, so r e to the rt. And then we need to know y double prime, which is constant r, e to the rt times another r, so it'll be r squared e to the rt. Okay, so now plugging these values into this form, we're going to have a times e r squared e to the rt plus b times r e to the rt plus c times e to the rt equal to 0. Okay, so now that becomes ar squared e to the rt plus br e to the rt plus c e to the rt equal to 0. Now notice all the terms have an e to the rt, so we'll factor that out. Ar squared plus br plus c equal to 0. Now the only way that this product can be 0 is if either e to the rt is equal to 0 or ar squared plus br plus c equal to 0. Now the only problem with this is there's no solutions. If you recall the function of y equal e to the x, or minus e to the x, depending on whether the r is positive or negative, you're going to have a graph that looks like this. And notice it never crosses the x-axis where the y value would be 0. So that means that this has no solutions to it. So the only way that this will be a solution is if the ar squared plus br plus c is equal to 0. So if we find the r's that make this true, then we'll know that the solutions to this second order equation will be y equal e to the rt. Now notice also that because this is a quadratic equation, that there could be up to 2 solutions. And when we have a second order equation like this, there could be up to 2 unique solutions, and we'll get to that in a little bit, 2 what's called linearly independent solutions. So this equation is going to be real important, this ar squared plus br plus c equal to 0. It's called the auxiliary equation or characteristic equation that's associated with that homogeneous equation right here. So we're going to get that auxiliary equation to determine our r values, and then from that we'll plug them into this to figure out what the linearly independent solutions will be. Okay, so let's find a pair of solutions to this. Now I'm not going to just memorize that auxiliary equation form. I'm just going to know that I've got a second order constant coefficient. So we've got 1 in front of the y double prime, a 5, and then a minus 6. So constant coefficient. So this is important. You've got to identify what type of equation you have. Second order constant coefficient, and it is homogeneous because the 0 for the r of t. So we're only working with the homogeneous equation. Okay, I know that the solutions to this are of the form y equal e to the rt. So if that's a solution, let's plug it in and see what we get. Okay, so if y is equal to e to the rt, then we know that y prime is r e to the rt, and we know y double prime is r squared e to the rt. So plugging those in, we're going to have 1 times r squared e to the rt plus 5 times r e to the rt minus 6 times e to the rt equal to 0. Take out the e to the rt, we get r squared plus 5r minus 6 equal to 0. We know this is never 0, so our auxiliary equation is r squared plus 5r minus 6 equal to 0. So that looks like it might factor. Let's say r plus 6 and r minus 1. That's correct. And so our two values of r will be negative 6 and r equal 1. Okay, so what that tells me is I've got the two solutions that are of this form will be y equal e to the minus 6t and y equal e to the 1t. Just filling in the r values into the form that we know the solution takes. Okay, so we found two solutions to this differential equation. We can find additional solutions by multiplying either one of those by constants. We can also find additional solutions by taking a linear combination. That means to multiply each of these by a constant, as in C1 e to the minus 6t and C2 e to the t, and then summing them together. So if we have two solutions, we'll call this one y1 and y2, then a general solution will be of the form y equal some constant times the y1 plus some constant times the y2. That actually will end up giving us all the solutions. So this is the general solution. And we call this a two-parameter solution because we've got the two parameters, C1 and C2. Now those are also called degrees of freedom because each one, we have two different ways that we can vary the values to get new solutions. Okay, so now if we want to find a unique solution, a very specific one, see this is general because any number you plug in for C1 and C2 would give you another solution. If you want a specific value for C1 and C2, you're going to need two initial conditions because we have the two parameters in our solution. Okay, so now let me just show you that if y1 and y2, so we're going to assume y1 and y2 are solutions. Okay, so that means that we're looking at a second order homogeneous differential equation. So that means then that a y1 double prime plus b y1 prime plus c y1 has to be 0, and that a y2 double prime plus b y2 prime plus c y prime, c2, got the prime in the wrong place, plus cy2 is equal to 0. We know these are true if y1 and y2 are solutions. So let's see if this linear combination, meaning a multiple of each of those y1 and y2 summed together, would give us a solution as well. So I want to see, is this a solution? So to find that out, I'm going to plug it into this form, the a y double prime plus the b y prime plus the c y equal to 0. So that's our second order equation that we're trying to solve. So if this is my y prime is equal to c1 y1 prime plus c2 y2 prime. And my second derivative would be c1 y1 double prime plus c2 y2 double prime. Okay, now plugging into this equation, we'll have a times c1 y double prime plus c2 y2 double prime, I'll left the 1 off, plus b times c1 y1 prime plus c2 y2 prime plus c times the y, which is c1 y1 plus c2 y2, and we want to see if that is equal to 0. Well, distributing, we have a c1 y1 double prime. I'm going to group everything with the y1s. So I've got this one, I'm going to have this term over here plus b c1 y1 prime. And then I need this term plus c c1 y1. And now I'm going to get all my terms with the y2. So a c2 y2 double prime, this term, plus b c3 y, oops, that's a 2, little numbers here, y2 prime, that's this term, plus c2 y2, and we need that to be equal to 0. So now let's group these together. I've noticed that I can take out a c1, and I'll have a y1 double prime plus b y1 prime plus c y1, and in the second set of terms, I'm going to take a c2 out. I'll have a y2 double prime plus b y2 prime plus c y2. But look up here. We knew that y1 was a solution, so that meant that this term is 0. And since y2 was a solution, we know that this is 0. And so this does come out to be a true statement. So what this tells us is if we can find two solutions, y1 and y2, like we did up here, then we can get a general solution, that's all possible solutions, by taking linear combinations, take a constant times each one of these and add them together. So that will be the general solution of the second order constant coefficient differential equation. Okay, so let's solve this initial value problem. That's going to allow us to actually find the C1 and the C2 values. So again, I'm going to look at this and identify it as a second order constant coefficient differential equation. So that tells me that the solution is going to be of the form y equal e to the RT. So let's find it. Y prime would be r e to the RT. Y double prime is r squared e to the RT. So we're going to have r squared e to the RT plus 2r e to the RT minus e to the RT equal to 0. Take out the e to the RT, which we know can never be 0, so we could actually divide both sides by it. Now, we end up with our auxiliary equation, which is r squared plus 2r minus 1 equal to 0. Solving that for the r's will give us the two values that lead to our two solutions. Now, notice one thing, though. Instead of having to go through this all the time, we know what the solution is, know what that form is. I want to make sure you realize that is a solution if we've identified the equation as this type. But notice that what this auxiliary equation looks like and its relationship to the original differential equation. Notice all we did was we took the y double prime out and replaced it with the r squared. We're using these same coefficients in our auxiliary equation for the quadratic in r. So 1r squared plus 2r minus 1. So we can skip all these steps and just go straight to that auxiliary equation. Now to solve it, this one's not going to factor, so I'm going to use the quadratic formula. Remember, our quadratic formula is if you have something of the form, I'll use r's, ar squared plus br plus c equal to 0. The solution is r equal minus b plus or minus the square root of b squared minus 4ac, the whole thing over 2a. So that's the quadratic formula. Okay, so let's solve this using the quadratic formula. R is equal to minus 2, so our a is 1, our b is 2, and our c is negative 1. Minus 2 plus or minus the square root of b squared is 4 minus 4 times the 1 times the negative 1, and the whole thing over 2 times the 1. So that's 4 plus 4 is 8. Now we can simplify that radical. That's 2 times, since square root of 8 is square root of 4 times 2, that's the same thing as just 2 times the square root of 2 over 2. factor a 2 out of the top. Don't just try to cancel a 2 somewhere. You've got to factor it out of the top, and then you can cancel it. So we have our two solutions, -1 plus the square root of 2 and -1 minus the square root of 2. So those are our values for r. Okay, so our two solutions to this initial value problem, this differential equation, would be y equal e -1 plus the square root of 2t, and y equal, so I'll say that's y1, y2 is e to the -1 minus the square root of 2t. So our general solution is y equal c1 times e to the -1 plus the square root of 2t plus c2 times e to the -1 minus the square root of 2t. So that's our general solution. But now we have some initial conditions, so let's solve for the c1 and the c2 and find those. Okay, so y of 0 is equal to 0. Put in 0 for t, and our y should come out to be 0. So we'll have 0 equal c1 e to the 0 plus c2 e to the 0. That just says that c1 plus c2 is 0. The second initial condition, y prime of 0 is -1. So I need to take that equation and find y prime. So y prime is c1. Now, to take the derivative of this term, it's e to the same power times the derivative of the exponent. So it's going to be c1 times -1 plus the square root of 2 times e to the -1 plus the square root of 2t plus c2 times -1 minus the square root of 2 times e to that same power. Okay, so that's the y prime. So we know y prime of 0 is -1. So that means we should have -1 equal, I'm putting 0 for the t and the y prime is -1. c1 -1 plus the square root of 2 e to the 0 This is that -1 is equal to minus c1 plus c1 square root of 2 plus minus c2 minus c2 times the square root of 2. Okay, I think I'm going to get rid of this last statement. I don't want to actually distribute that out because it's going to be simpler to solve this if I recognize here that C1 is the same thing as negative C2, and let's just substitute that in. So we know the E0 to the 0 power is just 1 here. So I'm going to use the equation -1. I'm just going to change the ink here so we can identify this. -1 equal, and I'm replacing the C1 with negative C2. And I'll have C2 over here. Okay, so now to solve this for C2, let's factor it out of the right side. So I'm going to multiply this -1 through, so I'll have 1 minus the square root of 2 plus -1 minus the square root of 2 equal to a -1. So the -1 and 1 cancel on the right. We end up with minus 2 times the square root of 2 times C2 equal to -1. So that tells me that C2 is 1 over 2 times the square root of 2. And so that means that the C1 is -1 over 2 times the square root of 2. And if we want to change this by rationalizing it, multiply by square root of 2 over 2, square root of 2, you would end up with negative the square root of 2 over 4. So that's the C1. And then our C2 would just end up being the square root of 2 over 4. So our solution then, we'll go back up here to what that form was of our general solution. and just fill in what the C1 and the C2 values were. So we'll have that y is equal to negative the square root of 2 over 4, e to the negative 1 plus square root of 2t plus the square root of 2 over 4 okay, and there's our specific solution to the original initial value problem up here. Okay, we're going to state this next theorem without proof. For any real numbers, a, b, c, t naught, y naught, and y1, there will be a unique solution to this initial value problem. Okay, so we have a second order constant coefficient homogeneous differential equation with two initial conditions. So we'll know that there is a solution and that it's going to be a unique solution. Now, because we know the solutions of this are of the form e to the rt, or a solution will be of that form, then we know that the solution will be valid for all t in the interval minus infinity to infinity, since this function does exist for all t that are real numbers. So now, we need to understand another concept. It's called the concept of linearly independence. That's when you have two functions. How do we know that those two functions, when used to form a general solution, will give us all possible solutions? Well, it's important to know that the two functions that we find must be linearly independent for that to be the case. So two functions will be linearly independent on an interval if neither of them is a constant multiple of the other. Okay, so we would say that y equal e to the 5t and y equal 3 e to the 5t are not linearly independent, because they're just constant multiples of each other. Okay, so if two functions are just a constant multiple of the other one, we could say that they're linearly dependent. Okay, so we're going to look for the two solutions to this second order homogeneous equation, and we need to make sure that the two that we come up with are linearly independent, because once they are, then we'll be able to get that general solution by forming linear combinations of those two solutions. Okay, so now, if y1 and y2 are solutions to the differential equation above here that are linearly independent on an interval, then unique constants can always be found so that this will solve and satisfy that initial value problem up here. Okay, so let's just figure out, how do we find two linearly independent solutions? Okay, so now to determine if two functions are linearly independent, there's something called a Runge-Kutta. Now, to find that, so let's look at, we had a previous problem where we had y equal e to the minus 6t and y equal e to the t for solutions. Okay, I contend that those are linearly independent solutions. You can see that one of them is not a multiple of the other one. Okay, so by the definition of what linearly independent was on the previous slide, those are linearly independent. But if you really want to check the functions out, besides just saying one's not a multiple of the other, the Runge-Kutta you form by taking a determinant. So I'm finding the Runge-Kutta here of the two functions, e to the minus 6t and e to the t. The Runge-Kutta can be evaluated by taking this determinant. Now, I'm going to put each function on the first row, so e to the minus 6t and e to the t, and then I'm going to put the derivatives on the next row. So that's going to be negative 6 e to the minus 6t and just e to the t. Now you just go until you get to one less than the number of terms there are. So it has to be a square matrix. Okay, so now remember how to evaluate a 2 by 2. You multiply down the main diagonal and then minus up the back diagonal. So this determinant evaluates to be e to the minus 6t times e to the t minus 6e to the minus 6t times e to the t, which comes out to be e to the minus 5t. You add the exponents when the bases are the same, and then I have plus 6e to the minus 5t, so that comes out to be 7e to the minus 5t. Now, that's the Wronskian. The next theorem says that the set of solutions, we've got some solutions here to a second order homogeneous equation. The set of solutions will be linearly independent if the Wronskian is not 0 for every x. So we're not using x, we're using t. So is this ever going to be 0? We know that the Wronskian is not ever going to be 0 for all t values in the interval minus infinity to infinity, because we know the exponential function is never going to be 0. So that means then that we can conclude from this theorem that e to the minus 6t and e to the t are indeed linearly independent. And once we have that that's true, then we know that the general solution, y equals c1 e to the minus 6t plus c2 e to the t, is the general solution. Okay, so it's the idea of not just finding two solutions, because I could have had e to the t and 3e to the t. Those would be two solutions. I just can't take a linear combination of those and say I have all solutions, because those two functions, e to the t and e to the 3t, were not linearly independent. So we have to be sure that they come out to be linearly independent. So a simple test for that when we're dealing with these exponential functions is that one of them's not a multiple of the other, like in this case. Okay, so we won't have to worry about it. I just want you to understand that that was an important concept, that they would be linearly independent. Okay, when we were looking for the solutions to the auxiliary equation before, r squared, ar squared plus br plus c equal to 0, we had unique solutions in the examples that we did. Okay, but we know that when we're solving a quadratic equation, there's not always going to be two unique solutions. If this discriminant, b squared minus 4ac, is 0, there's going to only be one unique solution. And if the b squared minus 4ac is negative, there's not any real solutions. They would only be imaginary. So now let's look at the case where we have one unique solution. So that means it's a repeated root to this auxiliary equation. Okay, so if the auxiliary equation has distinct roots, r1 and r2, then that means that y equal to e to the rt and y equal e to the r1t and y equal e to the r2t are both going to be solutions. They're going to be linearly independent, and this will be our general solution. Just take a linear combination of those two solutions. But if we have one unique solution to this auxiliary equation, then we only have the one solution, y1 equal to e to the rt, since r was a repeated root, and the second solution that we need to form that general solution is going to be of the form t times e to the rt. So the exponent will be the same, but you'll multiply that e to the rt by the value of the function t. So this will give us two solutions that will demonstrate that they are going to be linearly independent, and this will be the general solution. So just take linear combinations of those two. Okay, so let's first verify that t e to the rt will be a solution if the r is a repeated root to this. Okay, so y prime, now to find y prime of this, I'm going to need to use the product rule. So it's going to be t times r e to the rt plus e to the rt times 1. y double prime. Again, I'm going to need the product rule to take the derivative of this. It'll be r times t r e to the rt plus e to the rt times 1 plus r e to the rt. So now let's show that there are solutions to this. So we're going to have a times, this distributed through would be r squared t e to the rt plus r e to the rt plus r e to the rt. So I could have written that as 2r e to the rt plus b times y prime will be rt e to the rt plus e to the rt plus c times the y, which is t e to the rt. And that should come out to be 0. So distributing the a through, I'm going to go ahead and combine these. So that's going to be plus 2a r e to the rt Okay, let's take out a bunch of e to the rt's out of this. We know they can't ever be 0, so we can factor it out and essentially divide both sides by it. So we have ar squared t plus 2ar plus brt plus b plus ct equal to 0. Okay, let's look at ar squared t plus brt plus ct. So if you take the t out of those, that's going to be t times ar squared plus br plus c. And then we still got this 2ar plus b. Now remember that we found a solution to this auxiliary equation, so r satisfied that, which means that this term is 0. So this is t times 0. So is this true? Let's go back up to this. If r is a repeated root, then that means that b squared minus 4ac is 0, which means that your solution would be r equal minus b over 2a. So let's come back down here and let's put in minus b over 2a, because that's the case if r is a repeated root. And that comes out to be 0 equals 0. So that does indeed show that this will be a solution if e to the rt was a solution and the r was a repeated root. So now we have two solutions. We have y equal e to the rt, and we have y equal t e to the rt, or the two solutions to our second order differential equation with constant coefficients. So now, are they linearly independent? Let's check. Let's check the Wronskian. The Wronskian of e to the rt and t e to the rt will be e to the rt, t e to the rt. The derivative of e to the rt is r e to the rt. The derivative of the second one here, we need the product rule. We already have it over here. Will be rt e to the rt plus e to the rt. And now let's find that determinant. Multiply this. Okay, I'm going to distribute this through. Now I know e to the rt can't ever be 0. So we have rt e to the, now add the two exponents here. This is 0. We end up with e to the 2rt which we know is never equal to 0, so the Wronskian could never be 0, which means that e to the RT and t e to the RT are indeed linearly independent. So that means that our solution, C1 e to the RT plus C2 t e to the RT, is the general solution. That's when you have one repeated root, R, to the auxiliary equation. Okay, so let's look at an example. I want to find a solution to this initial value problem. First off, let's get the auxiliary equation. The auxiliary equation, just take the coefficients. 1 is the coefficient of the y double prime. It'll be the coefficient of the r squared. So 1r squared plus 4r plus 4 equal to 0, and solve that quadratic. So that's just r squared plus 4r plus 4 is r plus 2 squared. That means that we have one root, r equal negative 2. Well, that means we have the two solutions, y equal e to the minus 2t, and we have that y equal t e to the minus 2t is the second solution. So we'll call this solution 1 and solution 2. That means our general solution is y equal c1 e to the minus 2t plus c2 t e to the minus 2t. Okay, so now let's check use the initial conditions. If y of 0 equal to 1, we know that 1 is equal to c1 e to the 0 plus c2 t, t is 0, times e to the 0. So that means that c1 is equal to 1. Okay, use the other initial condition. Okay, so let's find y prime. Negative 2 c1 e to the minus 2t. We need the product rule here. T times negative 2 e to the minus 2t plus e to the minus 2t. Okay, so this is negative 3, is the y prime, is equal to minus 2 c1 e to the 0 minus 2 c2 times 0, the t, plus c2 e to the 0. Okay, so this one cleans up to be negative 3 equal to minus 2c1, that's 0, plus c2. We already know that c1 is 1. So that's minus 3 equal to negative 2 times 1 plus c2. That means our c2 is simply equal to negative 1. I just noticed I had a typo up here. I better correct before we get this answer so I don't get a bunch of responses. This was an equal sign, not a negative 3. So this should have been equal to 3, which would have meant that this is 3. I'm just going to make a little slight change to this, which means then that our solution here ends up being 5. Okay, so our solutions are, well, we already have our general solution over here. So all we need to do is get our specific solution for this initial value problem, which will be y equal 1 e to the minus 2t plus 5t e to the minus 2t. Okay, and I do want to point out too that these two were linearly independent. We checked that on the previous slide. When they're in this form, they will be linearly independent solutions, which then leads us to this unique solution. Okay, now let's extend this to nth order constant coefficient homogeneous equations. So we're going to be looking at equations of this form. So a sub n, the nth order derivative of y plus a n minus 1, the n minus first order derivative of y and still have a 0 for that f of t. So when you have an equation, an nth order constant coefficient differential equation that's homogeneous, the general solution will look like this. We need to find those n solutions to that. We'll end up getting an auxiliary equation of nth order. So we get the y1, y2 up to yn, which will be unique linearly independent solutions, and then just form the linear combination of those to get the general solution. So it's the same idea, you're just extending it to having a higher order differential equation. Okay, I want to find the general solution to this. This is a third order constant coefficient. That's important because we'll get to non-constant coefficients later. And homogeneous. So be sure you recognize those characteristics. Okay, let's get the auxiliary equation. We know the solution is going to be of the form y equal e to the RT. Okay, we know that if we plug that into this, we're going to get the auxiliary equation 1r cubed plus 3r squared minus r to the first minus 3 equal to 0. That will be the auxiliary equation. So just use the coefficients for the coefficients of the r. And now let's solve it. Let's see, it looks like this one might actually factor by grouping. I'm going to take r squared out of the first two terms, and I'm going to take a negative 1 out of the second two terms. Take out the r plus 3. This factors to, we have three unique solutions to this auxiliary equation, negative 3, negative 1, and 1. Our three solutions that are linearly independent, and we can check using the Wronskian to show that they are, but all these exponentials of this form are going to be. So we have the solutions y equal e to the minus 3t, that's y1, y2 is e to the minus t, and y3 is e to the t. Those are our three unique solutions that are linearly independent, and our general solution will be y equal c1 e to the minus 3t plus c2 e to the minus t plus c3 e to the t. And if we have three initial conditions, we can get a unique solution to this nth order, third order differential equation with constant coefficients. Okay, now we're going to look at those auxiliary equations that led to complex roots. Okay, so first off, we've looked at the harmonic equation, the simple harmonic equation, which is of this form. Okay, we got this when we were looking at springs and setting up equations that were involving the springs. The solutions to this equation are of the form cosine of t and sine of t. Okay, so let's just verify that those really are solutions to y double prime plus y equal to 0. So if y1 is equal to cosine of t, that means that y prime is equal to negative sine of t, and y double prime is equal to negative cosine of t. So substituting into this equation, we'll have negative cosine of t plus y, which is cosine of t, equal to 0, which is an identity. Okay, now let's look at y2. If y2 is sine of t, that means y2 prime is cosine of t, and that means y2 double prime would be negative sine of t. So again, substituting into this equation, we would get negative sine of t plus y, which is sine of t, which again comes out to be 0. So this verifies that these are both solutions to this particular harmonic equation. Okay, which is just one of our second order constant coefficient differential equations. Okay, so let's look at the auxiliary equation that we get from that. Well, the auxiliary equation is just going to be r squared plus 1 equal to 0. When we solve for this, we could use the quadratic formula. It does not factor. Quadratic formula would lead us to r equal the square root of -1. Okay, you can use quadratic formula. The b would be 0, so r would be equal to 0 plus or minus the square root of b squared is 0 minus 4 times 1 times 1, so minus 4 all over 2. So we'd end up with the plus or minus the square root of -4 over 2. Square root of 4 is 2, square root of -1 is I, so that's plus or minus 2I over 2. So that's plus or minus I. And that's exactly, I didn't put the plus or minus here. So I was just solving r squared is -1, so r is plus or minus the square root of -1, which is plus or minus I. Okay, so that leads us to our two complex roots. Okay? Okay, so now let's look at the auxiliary equation a little closer. The auxiliary equation was of the form AR squared plus BR plus C equal to 0. And when we solved for R, we got that R was minus B plus or minus the square root of B squared minus 4AC all over 2A. Now, you'll have complex roots when the discriminant, the B squared minus 4AC under the radical there, comes out to be negative. Okay, so now, looking at the roots, we know they're going to be complex numbers. So depending on the various values for A, B, and C, we're going to get roots of this form. Alpha plus beta times I and alpha minus beta times I. This plus or minus in the middle forces us to end up with these conjugate roots. So that means that all the two are going to look alike, except the sign of the I term will be positive or negative. Okay, so if you look at these the two solutions that you get here, you could split this up into two parts. Minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. Okay, and so if this does indeed come out to be a negative number, we know that that's going to be an imaginary part. Okay, so the two parts, the alpha will be the minus b over 2a, and the beta will be this term. Now, if this b squared minus 4ac is negative, that means that 4ac minus b squared, just take a -1 out of it, is going to be positive. And so we'll end up with that times the square root of -1, which is just going to be your I term. So this will be the beta. It's the real part of, well, it's the complex part. It's the coefficient, which will be a real number of the I term in these two roots. Okay, so we're going to have these two solutions, and we know that when we have this second order constant coefficient differential equation, the roots are going to have the form, the solutions will have the form of e to the alpha plus beta I and e to the alpha minus beta I. Those will be the solutions, your y1 and your y2. So that's true even if they're complex. Okay, so now to try to simplify that, let's look at one of them. I'm just going to look at the e to the alpha plus beta I to start with. If you look at that root, we can simplify that by breaking up the exponent to alpha t plus beta it. Okay, so this is e to the alpha t plus beta ti. I'm just distributing the t through both of those terms, which is the same thing as e to the alpha t times e to the beta I times t. Okay? Well, it ends up that this e to the beta it, or I probably should put that I at the end. Can be simplified. There's a formula called Euler's formula. And I'm not going to go through the derivation of it, but it uses Maclaurin series. It's not a bad proof. It's pretty easy proof. And the book does have the proof of it in there. E to the I theta. So if you have some angle times I, that's equal to cosine of theta plus I sine of theta. Okay? So using this on e to the beta ti, I'm just going to, the theta is the beta t, And so this term just becomes cosine of beta t plus I times sine of beta t. And then we still have this e to the alpha t in the front. So that would be one of our solutions. That would be the y1. Okay? And if we changed and looked at the y2 up here, the only difference is going to be the sign right here. Okay? Okay, so now let's solve this initial value problem. We first want to recognize the type. This is a second order constant coefficient. 1, 2, and 2 are the coefficients. Differential equation. We know that the form of the solution will be y equal e to the RT, and we know that our auxiliary equation will be r squared plus 2r plus 2 equal to 0. Solving does not factor. R equals to minus 2 plus or minus 4 minus 8 all over 2. Square root of negative 4 is 2i. So that comes out to be negative 1 plus or minus I. So get factor 2 out of the numerator and then cancel. So we have two roots. R is negative 1 plus I, and R2 would be negative 1 minus I. So our two solutions would be y equal e to the negative 1 plus I t, and y2 would be e to the negative 1 minus I t. Okay, let's look at the form that we switched to in the previous slide. We had that when you have e to the alpha plus beta t, that was equivalent to e to the alpha times cosine of beta t plus sine of beta t times I. Okay, so these can be rewritten then as e to the negative 1 and the beta here is just 1, so we'll just have cosine of t plus I sine of t. And I don't need to put minus 1t, it's just a minus t, this first term. Okay, the alpha here is negative 1, and the beta is positive 1. Because alpha plus beta I is the form that we're looking at here. Okay, so that's one of my solutions. My second solution is e to the minus t cosine of t minus I sine of t. Okay, so our general solution then is y equal c1 e to the minus t cosine t plus I sine t plus c2 e to the minus t cosine t minus I sine t. Okay, now let's use our initial conditions. We know that y of 0 is 0. So that means 0 equal c1 e to the 0 is 1. And then we'll have cosine of 0 plus I sine of 0 plus c2 e to the 0, which is 1, cosine of 0 minus I sine of 0. Now sine of 0 is just 0. Cosine of 0 is 1. So this ends up being 0 equal to c1 plus c2. Okay, the second condition is that y prime of 0 is 2. So we need to find y prime. Okay, using this general solution, y prime we're going to need the product rule because we have a t here and a t over here. So we're going to have c1 e to the minus t times the derivative of what's in parentheses, which is negative sine of t plus I times cosine of t, plus the second term times the derivative of c1 e to the minus t, which will be c1 negative 1 e to the minus t. Okay, that's just the derivative of the first term, plus c2 e to the minus t times the derivatives of minus sine t minus I cosine of t plus cosine of t minus I sine of t, second term, times the derivative of the first. c2 times negative 1 e to the minus t. So there's our first derivative. Let's go ahead and plug in 0 for the t's, and y prime is 2. So we'll have 2 equal c1 e to the 0 is 1. We'll have minus sine of 0 plus I cosine of 0 plus cosine of 0 plus I sine of 0 times c1 times negative 1 e to the 0 is 1 plus c2 times 1 minus sine of 0 minus I cosine of 0 plus cosine of 0 minus I sine of 0 times negative c2 times e to the 0. Okay, so let's see what that comes out to be. Sine of 0 is 0, so this is 0, this is 0, 0, and 0. Cosine of 0 is 1. Okay, we get 2 equal c1 times I plus negative c1 minus c2 times I from this one, and then minus c2. So let's group the terms together. That says 2 is equal to negative c1 minus c2 plus I times c1 minus c2. All I'm doing is I'm grouping the i's and the real parts and the imaginary parts. For this to equal to 2, which is only a real part, that means that the 2 has to be this term, and this term has to be 0. Okay, let's back up here a little bit. I don't want to look at it this way. I want to go back and group it as a C1 and C2. I already have one equation with C1 and C2. I need to just focus on the C1 and C2 down here. So when I get it to this form, actually I could have left it in the one above it. I'm going to group my C1s. I want to get an equation with C1 and C2. So I've got the C1 here. So I've got C1 times I minus 1. And then I've got minus C2. Or let's just keep that as plus C2. And then a minus I minus 1. Okay, now let's use this other fact that we have here and say that that means that C1 has to be negative C2. So I'm just going to swap this in. So I'm going to have 2 equal negative C2 so that's minus C2I plus C2 minus C2I minus C2. Let the C2's cancel. We get minus 2 C2I equal to, we're looking for C2. C2 then is equal to 2 over negative 2I, which is equal to negative 1 over I. If you remember how to simplify when you have imaginary numbers in the denominator, You don't want to leave the imaginary in the denominator. So let's multiply by the conjugate of the denominator, which is just changing the sign of the I term, minus I over minus I. That gives me a positive I on the top and a minus I squared on the bottom. I squared, remember, is equal to negative 1. So minus I squared is going to be positive 1. So this is just simply positive 1. And so C2 then comes out to be simply I, which means then that since C1 is just negative C2, C1 is equal to minus I. Okay, so now let's see if we can write our actual solution down. We have, these are our two values for C1 and C2, and where did our general solution go? Our general solution was right up here, but it's kind of covered up now with the, it's right here. Now we want to fill in the I and the negative I for C1 and C2. So we'll have, we move that over there, and then I can move it up. All I'm doing is I'm copying this equation and filling in C2 and C1. And then we're going to simplify this. Write it neat enough. Okay, if you distribute this minus I e to the minus t through, this and this cancel. So we get, here's that minus I squared again, which is just equal to 1. These are just 1. So we end up getting e to the minus t times sine of t plus e to the minus t times sine of t, which is equal to 2 e to the minus t sine of t. Notice that we don't have any imaginary numbers left in this solution. So that's our specific solution for this initial value problem. Okay, now when we're using the method of undetermined coefficients for this particular differential equation, we have 5 as the f of t on the right side. So our best guess, using the methods that we used previously, was that the particular solution was going to be of the form y equal a constant. Okay, since there's no powers of t. Now look what happens when we actually plug that in. If y is a, that means that y prime is 0 and y double prime is 0. So that would give us 0 plus 0 equal to 5, which is not a true statement. So there is no solution for a there. Now, what if we assume that we could just multiply by another power of t? So let me consider a particular solution, y equal to a times t. Well, then y prime would be equal to 4. Y double prime would be equal to 0. So then plugging in, we would have 0 plus 4, oops, 4a equals 5, and that would mean that the a was 5/4. So that would actually give us a particular solution of y equal 5/4 times t. Now, why did we have to modify our original plan? Previously, if we had a power of t over here, which in this case would have been t to the 0, we'd only use terms up to that power. We didn't go higher powers. The problem comes from what the solution to the homogeneous equation would be. If you consider the homogeneous equation, y double prime plus y prime equal to 0, we're looking for solutions that would cause a 0 to the left side. So the way we found the solution to this was we used we knew that the form of the solution was going to be y equal e to the RT, and we formed the auxiliary equation. So we ended up with r squared plus r equal to 0. Well, when you solve that for r, you get r times r plus 1 is 0. That gives me two values for r, 0 and -1, which tells me that the solutions to the homogeneous equation were y equal e to the 0, which is just 1, and y equal e to the minus t. The problem with using just a up here was that it overlapped the value that we got here. This tells me that y equal to 1 was a solution of the homogeneous equation, which told me that I was going to get 0 on the right side when I plugged that function into the left. And remember that if you have one solution of the homogeneous equation, any multiple of it would also be a solution. So our general solution to the homogeneous equation was y equal C1 times 1. I'll just put the 1 there so you notice it, plus C2 times e to the minus t. Any value of the C1 or C2 will give you a solution that will come up with 0 on the right side. So that means any just constant term here is going to end up resulting in a 0 on the right. So we can't use those for our solution to get for the form of the function that's going to give us the particular solution with a 5 on the right. So we have to modify what we choose for our form of the particular solution. So when this overlaps what the solution is to the homogeneous equation, we have to multiply by another power of t, just to make it a unique solution. Remember we did that back when we were finding solutions when we had repeated roots? So had our auxiliary equation been r minus 1 squared, we ended up with two roots, r equal 1. The solutions in that case were going to be e to the 1t, and then to give us a second solution, we found that t e to the t was also a solution. So that multiplying by an extra power of t helped to give us that second solution in that case. That same idea works here as well. So when you look at this equation and think, oh, I need something of this form, if you've already checked to see that the homogeneous equation had a constant term like that a, right? C1 is just a constant, just like the a. If that overlaps the homogeneous solution, then we have to multiply by the extra power of t. Now notice I didn't add an extra constant term. I didn't say at plus b. That's not necessary because the b is still in this set. It's going to cause you to get 0. It's not going to contribute to the 5. So only when it overlaps the homogeneous solutions do you need to put that extra term. Now, ideally what you'll do is you're going to suggest, you're going to first check the homogeneous solutions, because if we're going to get all the possible solutions, we're going to need to do that anyway. So check your homogeneous solutions first. Then when you look at the form for the particular solution, if it overlaps, we need to adjust our particular solution form. Okay, so now let's look at the second problem here. Just based on what the right side is, the f of t, we would guess our particular solution would be of the form just a constant times e to the 3t. Okay, well let's try that. This will be a pretty fast one. Y prime then would be 3a e to the 3t. Y double prime is 9a e to the 3t. Plugging in, we get 9a e to the 3t minus 6 times 3a e to the 3t plus 9 times a e to the 3t, and we want to equal to e to the 3t to satisfy the equation. So we have 9a minus 18a plus another 9a, which is 0 e to the 3t, which can never be equal to e to the 3t. So that's making me think that that e to the 3t was probably part of the homogeneous, included in that solution of the homogeneous equation. The homogeneous equation is y double prime minus 6y prime plus 9y equals 0. It's when you put 0 on the right side for f of t. So let's check that homogeneous solution. So I'm going to use, find the solution to the homogeneous differential equation. Okay. Now, here we could just apply the same principle that we did up here. Let's just multiply by an extra power of t and use the at e to the 3t as the possible solution. But what's going to happen is you're going to end up getting 0 again. So let's go ahead and check this out and see why that's happening. So our auxiliary equation would be r squared minus 6r plus 9 equal to 0, which gives me the two roots, r equal 3 and r equal 3. Okay, so what were my solutions? We know the form of the solutions is this e to the rt. So that gave us that y equal e to the 3t was one solution. We only had the one solution automatically, so we learned the form of the second solution when we had the repeated roots was t e to the 3t. Okay, so that means our solution, the general solution to the homogeneous equation was y equals c1 e to the 3t plus c2 t e to the 3t. Notice any c1 and c2 here will give us a solution that will cause you to get 0 for the right side. So had c1 been 0 and we use c2 equal to 1, we would have t e to the 3t, which is still going to cause you to come up with 0 for this left side. So you're not going to be able to get the e to the 3t. So for this problem, what you need to do is multiply by another power of t. So the form of the particular solution here and that's to avoid overlapping of the solutions of the homogeneous equation will be y equal a t squared e to the 3t. You have to multiply by a high enough power of t to eliminate the overlap in that homogeneous solution. Okay, so now let's see what we get here. If this is our y prime by the product rule will be at squared e to the 3t plus e to the 3t times 2a t. Okay, so we can pull the e to the 3t out. That would be at squared plus 2at e to the 3t. So there's y prime. Y double prime then will be first term times the derivative of the second, which will be 3e to the 3t. I think I forgot that. Yes, I overlooked the 3t up here. So let's just get rid of this part and come back up here. Okay, so at squared, the derivative of e to the 3t is 3e to the 3t plus e to the 3t times 2at. So that gives me 3at squared plus 2at times e to the 3t. Okay, second derivative. Times 3e to the 3t, and then plus 6at plus 2a times the e to the 3t. Okay, let's clean that up a little bit. We have to e to the 3t we have a t squared here, so 3at squared. We have a 2at here, and we'll have a 6at here, so whoops, I didn't multiply through out of that 3. Just through right here. Trying to save space because I'm running out of it here. Okay, so we have 9at squared. We have 6at and another 6at below. And then we have the 2a below. Okay, so now let's plug this into the equation up here. Y double prime minus 6 times the y prime plus 9y and that has to equal to e to the 3t. So let's get rid of all of our e to the 3t's. We're going to have a 9at squared here minus 18at squared plus another 9at squared. So that's 0 t squares e to the 3t. Well, I'm getting rid of the e to the t's. I've got a 12at here. I've got a minus 12at here. And then my constant terms, I've got a 2a here. These are both 0, so we end up with a 2a e to the 3t having to be a 1 e to the 3t. So that means 2a is equal 1, so a is 1/2. Okay, so now go back to the form that we used for that particular solution and fill in what the a value is here, 1/2. Our particular solution then is y equal 1/2 t squared e to the 3t. Now there's a lot of little detail when you're going through and calculating this, so be as neat as you can and try not to take too many shortcuts like I've done to avoid making mistakes. Okay, so now let's look at what the general solutions are going to be for these. To find a particular solution to a differential equation that has a form of a power of t times an exponential power, you're going to multiply by the power of t that's necessary to avoid the roots of the auxiliary equation. Now don't worry about what all that says. It's just saying that if there's a root, if there is a e to a power that overlaps the homogeneous, multiply by t to the first. If there ends up being a t times an e to that power that's already part of the homogeneous solution, multiply by t to the second. You multiply by the smallest power of t possible to avoid duplicating the solutions in the homogeneous. Okay, to find a particular solution where there's sines and cosines for the e of the right side, the f of t, you'll do the same thing. You're going to take the sines and cosines that you were already using, the forms of those, and you're going to multiply by the lowest power of t necessary to avoid duplicating terms. So let's look at a few examples. So let's say that we had an f of t that was one of these forms, a, b, c, d, e, f, there. First thing I want to do to be able to figure out what my particular form is I've got to figure out what my homogeneous solution looks like. So first, find the homogeneous solution. So we're going to look at y double prime plus 2y prime minus 3y equal to 0. Our auxiliary equation is r squared plus 2r minus 3 equal to 0. which means we end up with roots 6r plus 3, r minus 1. So we end up with the roots negative 3 and 1, meaning our solutions will be, remember, they're going to be of the form y equal e to the rt. So our solutions for the homogeneous will be linear combinations of y equal e to the minus 3t and y equal e to the t. So the general solution to the homogeneous equation would be y equal any multiple of e to the minus 3t plus any multiple of e to the t. Meaning any multiple of just e to the t would be a solution, because c1 could be 0, or vice versa, letting c2 be 0. Okay, we've got to avoid overlapping these. Okay, so now if we were looking at the equation with a 7 cosine of 3t on the right side, so this is the equation we're looking at. We know that the only things that are going to cause the left side to be 0 are things that are multiples of those two functions. We don't have to worry about this function overlapping. So our particular solution, we're looking just for the form of the particular solution. You can plug all that stuff in later if you want to practice. The particular solution's form, and sometimes we'll put y of p for particular solution. This other one is our homogeneous solution. The particular solution would be a constant times cosine, and it's going to have to be the same argument, 3t, plus a constant times sine. Okay, so that would be our particular solution. No overlap with the homogeneous. Okay, the second one here, we have t squared cosine of pi t. Again, no overlap with the complement, it's called a complementary solution of the solution to the homogeneous equation. So y of p, now it's a t squared cosine of pi t, but remember when you have that t squared, it could be any power of t times the cosine or sine. So we're going to have a t squared plus bt plus c, so any polynomial t squared or lower degree, times cosine of the same angle, pi t, plus the same type of polynomial times sine of pi t. That's what we're, oops, except I can't use ABC again. I've got to use different letters over here, so we're going to have a lot of things to have to solve for. So d t squared plus et plus f. Okay, so 6 unknowns in that problem. So you'll end up plugging them in and grouping everything that has a t squared cosine, a t squared sine, t sine, t cosine, just a plain cosine, just a plain sine, and setting the coefficients equal to each other. Okay, so now let's look at 3t e to the t. Here we see an overlap with the e to the t. See, now if we were just looking at this and coming up with our particular solution, we would, without paying attention to the homogeneous solution, we would say, okay, we have a 3t, so let's say at plus b e to the t. That's what we would use if we totally ignored the homogeneous solution. But we see that the b e to the t does overlap this. So that portion of it is just going to cause there to be a 0 on the left side when we plug it in. So we need to eliminate that overlap of the e to the t and multiply by an extra power of t. So I'm going to multiply by a t to the first because now my particular solution's form will be yp equal at squared plus bt e to the t. And none of that will be part of the homogeneous solution because the smallest term there, smallest power of t is the bt e to the t, which is not going to give you 0. So this would be my solution, or my form for my particular solution, if this was my f of t up here. Okay, now let's look at the next one. Now we've got an e to the t times a sine. Okay, if we weren't paying any attention to the homogeneous solution, we would say, okay, we have an e to the t times a sine, which could result from an e to the t times a cosine also. We have a 2t, which when you have the polynomials, you would always put the a times the t plus the b. Okay, so we're looking at this e of t, sine of t as a group. And since we have a power of 1 here on the t, we could have an at plus b as the coefficient of the e to the t sine. But it could also be an e to the t cosine. So we'll have to have a ct plus d e to the t cosine of t in our particular solution as well. Okay, now the next one, we have an e to the minus 3t. So we see an e to the minus 3t over here. So if I plug this value in, or something of the form, see how we would have chosen our particular solution before without noticing the homogeneous solution would have been a constant times e to the minus 3t. But we see that that's already included in the homogeneous solution, so that would result in just getting 0 on the left side. So we would never get the 5 e to the minus 3t up here for the f of t. So we're going to need to multiply by a power of t to remove that duplication. So just a simple a t e to the minus 3t will work. You don't go all the way down from the power of t, because if you added just a constant times e to the minus 3t, again, it's going to result in 0. So we can't use this one because of the duplication here. But this would be our particular solution that we would use for if the f of t over here was the 5e to the minus 3t. Okay, so now the last one, we have t squared e to the t. So normally when we have an e to the t times a polynomial, we would have said, okay, our particular solution is going to be at squared plus bt plus c times an e to the t. But we've got a duplication up here with this e to the t. That's the constant times e to the t. This one has the constant times e to the t, which would just result in a 0. So this term would not be contributing to that t squared e to the t. It's going to give us 0 when we plug it in. So multiply by another power of t, just a t to the first, because by distributing that through then, it's going to eliminate just a constant times the e to the t. So the particular solution here then would need to be at cubed plus bt squared plus ct e to the t. So we're just multiplying by this extra power of t to what we would have used had we not noticed the homogeneous. So there's our particular solution. Okay, another example, we're looking at an equation where this f of t could be any of these. But first let's look at the homogeneous solution. So the homogeneous solution, 2y double prime minus 2y prime plus y equals 0, the homogeneous equation, would result in the auxiliary equation of r squared minus 2r plus 1 equal to 0, or just r minus 1 squared equal to 0. So our solutions, knowing what the form of the solutions are to this, they are y equal e to the rt, but we only have one root, r equal 1. So r equal c1 e to the 1t is one possibility, but to get that second solution, when we have a repeated root, we have to multiply it by another power of t. So c2 t e to the t. So these are our two solutions, e to the t and t e to the t, when we have that repeated root of 1, and then just take linear combinations. So this is the homogeneous solution. Anything of this form, or any part of this form, is going to give us a 0 when we plug it in on the left. So now, to get a 7 cosine of 3t, it's not affected by the homogeneous solution at all. So our particular solution will be just a constant times cosine of 3t plus a constant times sine of 3t. Okay, this one, again, it's a sine and cosine. It's not going to be affected by the results of the homogeneous equation. So we're going to have, because of the t squared here though, we do need to have that power and any lower powers times sine or cosine. So the y of p would be at squared plus bt plus c times cosine of pi t. plus dt squared plus et plus f times sine of pi t. So that's what you would plug in and solve for those 6 variables, the 6 unknowns. T e to the t. We do have that up here. So normally we would have said, okay, because it's the power of t times an e to the t, we would have said, okay, we'll take at plus b times e to the t. That's what we would have used had we not considered the homogeneous solution. But we need to avoid the duplication. Notice we would have a duplication with this one and a duplication with this one because of the b times e to the t. So multiplying by a single power of t does not remove the duplication because we would still have the bt e to the t, which overlaps this one. So we must multiply by t squared to remove the overlap. So now we don't have an e to the t or a t e to the t in this particular solution. So our particular solution will actually be at cubed plus bt squared e to the t. You don't need the lower terms because they're going to just generate a 0 on the left side anyway. This one does not overlap because there's no sine and cosine. So we would take the at plus b times e to the t sine t, and then we'd have a ct plus d e to the t cosine of t. No overlap with the homogeneous solution. 5e to the minus 3t. Again, no overlap over here because there's no e to the minus 3t in the homogeneous solution. So we would just say a constant times e to the minus 3t. And then the last one, the t squared e to the 3t, we would normally have said at squared plus bt plus c times e to the t. That's what we would have used without considering our homogeneous solution. But we see an overlap with the bt times e to the t is part of this, is just that term, and the c e to the t is this one. So we have an overlap with both of those. To remove that overlap, we're going to have to multiply by t squared, because then our lowest power of t times the e to the t would be a t squared, which does not generate the 0 with the homogeneous solution. So y of p will be at to the 4th plus bt cubed plus ct squared, all of that times e to the t. Okay, one last example here. First, let's look at the homogeneous equation. The homogeneous equation is y double prime minus 2y prime plus 2y equal to 0. The auxiliary equation would be r squared minus 2r plus 2 equal to 0. Quadratic formula would be 2 plus or minus 4 minus 8 over 2. We get 1 plus or minus I. That's the alpha is 1. Remember, the alpha plus beta I is the standard form of a complex solution. Alpha equal 1 and the beta is equal to 1. So if we're looking for that solution to the homogeneous equation, we were going to have e to the alpha t, which is e to the 1t, times cosine of beta t, so just cosine of t, plus sine of t. Okay, so that's the solution to the homogeneous equation. Some authors use a little c there to refer to it's called the complementary solution. So the solution to the homogeneous equation. Okay, so we got to make sure we don't overlap when we're figuring out the forms for the right side here. Okay, so right now we have an e to the t cosine and we have an e to the t sine. So now let's see, I didn't put the complementary, I just put the two solutions separately, so let me correct that. Okay, so now if we were just considering this for our f of t, the form that we would have used, just using the, not paying any attention to the homogeneous solution, would have been a times t plus b times e to the t cosine of t, okay, plus A, not A again, we can't use A again, ct plus d e to the t sine of t. So that's what we would use for our proposed solution, particular solution, just paying attention to the 5t e to the t cosine of t. You have to use e to the t cosine of t and e to the t sine of t times any power of t, the t to the first and below. Okay, now do we overlap our homogeneous solutions? Notice we have an e to the t cosine of t times just a single constant here, which is here and here, so they do overlap. So we have a constant e to the t sine of t and a constant e to the t cosine of t. So we must multiply both of these by another power of t. If we just multiply by a single t to the first, it will have a p b times t, which will eliminate the overlap. So that should be sufficient for the what we use for the form of the particular solution. Okay, and you can simplify it to be at squared plus bt e to the t cosine of t plus ct squared plus dt e to the t sine t before you start finding derivatives and plugging it in. That's going to be a mess because that's a huge, lots of product rules. Okay, so that's why we're just finding the form and not actually finding the solution. Okay, now the method of undetermined coefficients that we've been talking about in this whole section only works for non-homogeneous equations where the f of t on this side is polynomials, exponentials, sines or cosines or products of those functions. That's really important. You can't just use it for anything on that side because not everything, when you find its derivative and second derivative, will you result in terms that are similar. You're trying to guess, okay, what might give us this answer? Well, you know the solution is going to have e to the t's and sines and cosines in it because that's what their derivatives look like. Had you started with a tangent of x over here, the derivative of tangent is a secant squared, so the form on the left is nothing like the form on the right. So just keep in mind that only use this method of undetermined coefficients when those non-homogeneities, in other words, the f of t, or polynomials, exponentials, sines or cosines, or a product of those. Okay? We'll look at what's called the superposition principle in the next section. It's going to show us how to extend it when you have sums of those same type of terms. Okay? Okay, we started this chapter looking at second order constant coefficient differential equations of the form ay double prime plus by prime plus cy equal to some function f of t. Okay, we first solved this equation by considering only the cases where the f of t was equal to 0. Okay, this was called our homogeneous equation. And we found that the solutions to this homogeneous equation were of the form y equal e to the rt. All we did was we found the auxiliary equation by plugging this particular solution in, and then we found our two values of r. Or if there was just one value of r, we found how to find the second solution to that homogeneous equation. Then in the last section, we extended this to finding a particular solution to the equation ay double prime plus by prime plus cy equal to some f of t, where f of t was a single term. Okay? Now we also only considered terms, f of t, that were either polynomial, exponential, or sine or cosine, or products of those. And the way we did that was we figured out the form for the particular solution based on what the form of f of t was, and we set up a system of equations using the method of undetermined coefficients. So we were able to find the solution to this differential equation when you had a single term f of t. So now, the next thing we want to do is, what if you have more than a single term on the right side? Still the same type of terms, the polynomial, the exponential, and the sine or cosine, or products of those, but we want to be able to have two terms added together, or even multiples of two terms added together. So now we're going to consider differential equations of the form ay double prime plus by prime plus cy equal to some constant h1 times f1 of t plus another constant h2 times f2 of t. And we're trying to find the solutions to this differential equation. Well, the way we can do that, what the superposition principle says, is that we don't have to deal with what the form would be to get this huge function on the right. I mean, it would make a really large form by looking at all possible, functions that could come up with that term on the right, just like what we did in the previous section. So what we're going to do is we're going to solve this as smaller problems. We're going to look at ay double prime plus by prime plus cy equal to just f1 of t. And then we'll look at ay double prime plus by prime plus cy equal to f2 of t. Solve these two problems separately using the method of undetermined coefficients. And then once we get those solutions, let's say that y1 was the solution to the first one and y2 was the solution to the second one. Then our solution to this differential equation would be of the form y equal h1 times y1 plus h2 times y2. So we can form the general solution to a bigger problem when you have all of this on the right by looking at smaller pieces and doing those problems separately. And that's all this superposition principle says, is that if you have a problem where you have this linear combination on the right side of two functions, f1 and f2, let's just solve them separately. Let's find the solution for f1, let's find the solution for f2, and then we'll just take the linear combination using those same coefficients, h1 and h2, to get the solution for this bigger problem. Okay, so let's see how that applies to the problems here. In the last section, we already solved a solution for y double prime plus 3y prime plus 2y equal 3t was y equal 3t over 2 minus 9/4. We also saw that a solution for y double prime plus 3y prime plus 2y equal 10 e to the 3t came out to be y equal e to the 3t over 2. So now once we've worked the same problem using both this f and this f, we can say that the general solution to this whole problem then would be y equal 3t over 2 minus 9/4 plus e to the 3t over 2. We're just summing the two solutions together. Okay, so now let's look at the second problem here. This is just a multiple of 3t. So because we already know, and notice this first part of the equation is identical to the one that we did over here. Because we already know that the solution to this equation is of this form, the solution to the equation where there was just a negative 9t on the right side would be y equal negative 3 times the previous solution. And because we already know that if there was just a single 10t, 10 e to the 3t on the right side, over here we showed that if that were just a single 10 e to the 3t, this would be the solution. Then since this is 20 e to the 3t, which is just 2 times the 10 e to the 3t, we would have a solution of just 2 times e to the 3t over 2. So our general solution for this differential equation, having a minus 9t plus 20 e to the 3t on the right side, would simply be minus 9t over 2 plus 27/4 plus e to the 3t. So work simpler problems instead of having to get just one giant form of a particular solution. Okay, so now we're going to put all this together. We're looking for a general solution for a non-homogeneous differential equation. We're going to first find the general solution to the homogeneous equation. So we're going to just put a 0 on the right side in place of the f of t here and find what that general solution is. And remember, that's going to be something in the form the e to the rt and a linear combination of those two terms. So find the solution to the homogeneous equation first. Then we're going to find a particular solution to the differential equation having an f of t on the right side. Now, the f of t could be a single term or it could be a linear combination of terms as in the previous two examples. But just consider that whatever function is on the right and get the particular solution to that differential equation. So now, we're looking for the general solution, not just one particular solution, but all possible solutions to this differential equation. And those result from adding the general solution to the homogeneous equation to the particular solution. And that gives us that general solution to the non-homogeneous equation. Okay, now this existence and uniqueness theorem for the non-homogeneous case just tells us that if we have a particular solution y of p that's a particular solution to a differential equation on some interval, so here's our differential equation, and we know that y1 and y2 were those linearly independent solutions to that associated homogeneous equation, you know, by putting the 0 on the right side, then there will be a unique solution to the initial value problem given by this. So all we have to do then is to find a particular solution, y of p, find the homogeneous solution, you know, take the associated homogeneous equation by just putting 0 on the right side, get that solution, and then we know that there will be a unique solution to that initial value problem. So we just need to find the C1 and C2 that would make that true. Okay, so let's now assume that we were told that y of p is t squared is a particular solution to this non-homogeneous differential equation. We want to find the general solution. That means not just one particular solution. We want to find all the possible solutions. So the first thing I want to do is solve the associated homogeneous equation. Okay, you get that because you know that y equal e to the rt is the form of the solution to this type of second order constant coefficient equation. When you plug that in, you're going to end up getting the auxiliary equation, r squared minus 1 equal to 0. Two roots for that, r minus 1, r plus 1, end up being r equal 1 and r equal negative 1. So our two solutions are y equal e to the t and y equal e to the minus t. So that means our general solution to the homogeneous equation would be y equals c1 e to the t plus c2 e to the minus t. Okay, so we just solved this equation and found our general solution. Now, anything in that family, you know, of two parameters there, put any C1 and C2 in there, and you'll get a solution that'll make a 0 on the right side. So now, to solve this differential equation so that you get 2 minus t squared on the right side, you have to find that particular solution. Now, the way we did this in the last chapter was we would look at this polynomial over here, and because it's a polynomial of degree 2, we would take the form of the particular solution, was y equal to a t squared plus bt plus c, and we plug that in for y prime and y double prime in the equation and solve for a, b, and c. So they're telling us here that yp equal t squared is a particular solution. So we don't need to take the time to actually solve for that a, b, and c there. Okay, so we've now got a particular solution. We also already know the general solution for the homogeneous equation. So now to find the general solution for this differential equation, we know it's going to be of the form y equal to the t squared, a particular solution, plus the homogeneous equation's general solution. Okay, now some books will call this the particular solution, and they call this the complementary solution, which is the solution to the homogeneous. So the general solution is just the particular solution plus the solution, complementary solution. Okay, so we now know the form of the general solution for the differential equation here. So to solve the initial value problem, given these two conditions, we just need to plug those in and determine the C1 and the C2 in this equation. Okay, so let's plug them in. Let's first use the fact that y of 0 is equal to 1. That means that 1 will be equal to 0 squared plus C1 e to the 0 plus C2 e to the 0. Okay, so that just means that 1 is C1 plus C2. Okay, now let's use the condition that y prime of 0 is equal to 0. Well, we need to find y prime. Y prime would be equal to 2t plus C1 e to the t minus C2 e to the minus t. So now use that and the condition y prime of 0 equal to 0 to get 0 equal to 2 times 0 Okay, that tells me then that C1 minus C2 has to be 0. So I've got these two equations, and I need to solve for C1 and C2. So let's bring those over. C1 plus C2 equal to 1, and C1 minus C2 is equal to 0. Just summing the two equations, you get 2C1 is 1. C1 is equal to 1/2. And so if C1 is 1/2, the C2 is going to have to be, because this one tells me that C1 is equal to C2. So our specific solution solving this initial value problem will be this equation filling in the C1 and the C2. So we've got y equal t squared plus 1/2 e to the t plus 1/2 e to the minus t. And that's our specific solution to this differential equation with those initial conditions. Okay, previously we looked at the mass spring system that gave the differential equation the mass times y double prime plus the dampening times y prime plus the spring stiffness or constant times y equal to the driving force. Okay, so if we have a mass spring system described by, it's driven by the sinusoidal external force 5 sine t plus 5 cosine of t. That would be the F of t. The mass is equal to 1. So we'll put 1 y double prime. The spring constant is 2, so that's your stiffness. So here's our 2y. And then the damping coefficient is 2. And so we would put that in here, which is the 2y prime. So this is the differential equation that describes this particular mass spring system. We're told that the mass initially is located at 1 unit below equilibrium at time 0 and is imparted with a speed of 2, whatever the units are, at time 0. So the velocity that it's let go at is 2 in the downward direction since it's a positive 2 at time 0. We want to find the equation of motion, which just find y, the function y, satisfying this differential equation. Okay, so to solve this, the first step would be to solve the associated homogeneous equation. Which would be y double prime plus 2y prime plus 2y equal to 0. You know the form because of the second order constant coefficient equation. You know the form is going to be, looks like y equal e to the RT. And when you plug that in, you get the auxiliary equation r squared plus 2r plus 2 equal to 0. Solving using the quadratic formula we got previously when we did the same problem. r equal -1 plus or minus I. Okay, so now when you had solutions of the form alpha plus or minus beta, in this case your alpha is -1 and your beta would be +1, we saw that the solutions to this homogeneous equation were of the form y equals C1 e to the alpha t, so e to the minus t cosine of beta t, plus C2 e to the minus t sine of t, sine of the beta t. So that's our solution to the homogeneous equation. That's with the 0 on the right side. Okay, so now the next step after you find the solutions to the homogeneous equation is to look at the particular solution based on what's on the right side here. So those are our functions that we need to come up with by setting a particular solution for y in that. So to do that, we look at each one of these. Now we can do these two parts separately using the superposition principle, or we could do one large particular solution form using the two combined with the sum of those two particular solutions. So let's go ahead and just look at what would we get for the particular solutions form if the equation just had a 5 sine of t on the right side. In this case, the particular solution, the only way you're going to come up with a sine on the right side is if you had sines or cosines on the left for y. So we would have, and you just have a constant in front of the sign. So the form for the particular solution would be some constant times sine of t plus some constant times cosine of t. Okay, because sines and cosines have each other as the derivative, so you have to consider both of those for the particular solution. Then you would plug that into the y double prime and the y prime and the y. Okay, now we could also do the same thing for the equation y double prime plus 2y prime plus 2y equal 5 cosine of t. Okay, the particular solution for this function over here would also be a cosine of t plus b sine of t. So the form is going to be the same. Because the forms of these are the same, we don't need to do two separate problems. We can just simply do it once and then just set this on the right side equal to it. So let me just show you what we'll do. Instead of doing them separately, I'm going to do one problem and have the sum of the two functions on the right side. Okay, so we got our particular solution. Y prime would be equal to a cosine of t minus b sine of t. Y prime double prime would be negative a sine of t minus b cosine of t. Plugging those into the differential equation, you're going to get negative a sine of t minus b cosine of t. Okay, that's my y double prime. Then I want plus 2y prime and then I need a plus 2y Now, because these both had the same form, we're going to do them at once. Okay, let's group all the terms on the left, getting the sines and the cosines collected. So here's a sine, and here's a sine. So we're going to have minus a, so all be times sine. Then this one is a minus 2b, and then this one will be a plus 2a. And then I'm going to look at the cosine terms. I have a minus b cosine, I have a 2a cosine, and I have a 2b cosine. Okay, so now the only way for this to be true is if minus a minus 2b plus 2a is just 5, and then I want minus b plus 2a plus 2b to be 5. So let's solve those two things separately. So this one will combine into 1. This is actually just a minus 2b. And I add the a's together. And then this one comes out to be b plus 2a. So let's say 2a plus b equal to 5. So that's from that one. Okay, now solve this system of equations. So let's multiply the second one through by 2. And add them together. Once we get the a, let's come back over to one of these. So we'll have 3 minus 2b. The second one probably moves faster. But okay, that tells me that minus 2b is equal to 2, so that means b is negative 1. Okay, so we have our a and our b. So now we can come back up here to what the particular solution looked like and come up with what our particular solution is to this differential equation. So y of p is equal to 3 sine of t minus 1 cosine of t. Okay, that's our particular solution. So now if we're trying to find the equation of motion, given an initial condition, we need the general solution for this non-homogeneous equation. Okay, first step was to solve the homogeneous equation. Second step was to find a particular solution for the non-homogeneous equation. So we actually just put the functions over here. Then third step will be to find the general solution of the non-homogeneous equation, which means to take the particular solution with the values filled in plus the solution of the homogeneous. So we're going to have 3 sine that's the particular solution, and now here's our complementary solution, which is the solution of the homogeneous. Okay, now we need to satisfy the initial conditions here. Y of 0 is 1. That means that 1 is equal to, I'm putting 0 for the t's, sine of 0 is 0, minus cosine of 0 is negative 1. I'm putting 0 here, 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 here. So this part will be negative 1. This will be 0. This will be C1, e to the 0, which is just 1, cosine of 0, which is just 1. And then this whole term will be 0 when we plug in 0. Okay, well that tells me that C1 is equal to 2. Okay, so now let's look at the second condition. Y prime of 0 is equal to 2. Okay, so I need to find y prime. Y prime is 3 cosine of t plus sine of t. Ooh, we need the product rule. C1 e to the minus t times negative sine of t plus C1 cosine of t times the derivative of negative e to the minus t. So that's negative e to the minus t. And then product rule one more time. Okay, I'm not going to simplify it. I'm just going to plug in the condition is y prime of 0 equal to 2. So plugging in 0 for all the t's, we'll have a 0 here, 0 here, 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 here. Okay, so this term becomes just a 3. Okay, so y prime is 2. 3 plus 0, this is 0. This will be 0, since sine of 0 is 0. And this one will be plus C2 cosine of 0 is 1. and then e to the 0 is 1. And then, like, that was a C1. Helps to be neat. Okay, now we've got our C2 over here. So we're plugging zeros in here, 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 and here. So we're going to have plus C2, and then the rest of that's 1, and then this part is just simply 0. So we have that C1 plus C2 is equal to negative 1. And we already know that C1 is 2. So that tells me that C2 is negative 3. So our equation of motion is the y value. We're just going to take this solution, the general solution to the non-homogeneous equation, and plug in the 2 and the negative 3 for C1 and C2. But before you say anything, I just realized I skipped a minus sign right here. So that's going to make this a negative. And so when I put in the negative 2 here, we're going to get C2 is equal to positive 1, which is going to make this slight change plus 1 e to the minus t. Okay, we want to find a particular solution to this differential equation. And this is a non-homogeneous equation since we don't have 0. To be able to find the form of the particular solution, we have to know whether it overlaps the homogeneous solution or not. So let's first find the solution to the homogeneous equation associated with that. So we'll look at the equation y double prime minus y equal to 0. We know the form of the solution here is y equal e to the RT. The auxiliary equation is r squared minus 1 equal to 0. So we have that r is equal to 1 or negative 1. So our general solution to the homogeneous equation would be y equal to C1 e to the t plus C2 e to the minus t. Now we're not asked for all solutions here. We're just being asked for a particular solution. So we don't need to use this in the form of the answer other than to make sure it doesn't overlap with the form of the particular solution. So if we were just looking on this right side, we see both of these have an e to the t. One of them's a constant term, one of them's a t term. So the form of the particular solution over here, ignoring the homogeneous solution, would be some constant times t plus a constant e to the t, because both of those are an e to the t, and so we can take care of both of them in this one form. Okay, now look to see, does that particular solution overlap the solutions given down here in the homogeneous form? And we see that we do have a constant times an e to the t here. So that means that this b e to the t isn't going to give us this 2e to the t like we'd like it to, because b e to the t is just going to result in 0 if it's in a part of the homogeneous solution. Because anything, the homogeneous form, has to end up, it'll give you 0. So we can't just use this form for the particular solution. We have to avoid the overlap, and you do that by multiplying by the smallest power of a t that eliminates the overlap. So I'm going to multiply this by a t, because now I'm going to have a t squared here, and I'll have a bt, which neither of those is part of that homogeneous solution. So my particular solution that I'm going to use is going to be at squared plus bt times e to the t. Okay, so now let's plug that into the differential equation. So we've got that y double prime, or y prime would be, I've got to use the product rule here, at squared plus bt, first term times the derivative of the second, plus the second one times the derivative of the first. now y, let's see if I can simplify that a little bit. I can. Yp prime. Now if I'm looking at, let's just pull out the e to the t to everything. I have an at squared here. I have a bt and I'll have a 2at, so that's going to be a b plus 2a times t, and then I've just got this single b term. Okay, so that would be the simplified form of the y prime. Now let's find y double prime. Product rule, e to the t times 2at plus b plus 2a plus the second term times the derivative of the first. So that's our second derivative. Okay, so now let's just plug them into the differential equation. Y double prime would be that big thing. Minus the y, which would be this right here. And that should equal to 8t e to the t plus 2e to the t. Okay, let's go ahead and pull out the e to the t out of everything and just eliminate those. It's never 0, so we can just divide both sides of the equation by it, just to simplify it. And now let's combine some of our terms. This is a t and this is constants. This is a t squared. So here's a t squared and here's a t squared, which just cancel each other out. The t terms, I have a 2at, so I'm going to look at the t times. I have a 2a here. I have a b plus 2a. And here I have a minus b times t. Okay, so that should be all the t terms. I have the 2at, I have the b plus 2a, and I have the minus bt. And then the constant terms would be the b plus 2a. They're the ones I've underlined with 3 things over here. None in that next term. That's our constant term. And that has to be 8t plus 2. Okay, so now equating, the t coefficient on both sides has to be the same. Okay, let's go ahead and add these together. Jumping ahead here. So this ends up being 4a times t. So that means that 4a has to be equal to 8. And this ends up being 2b plus 2a, and that has to be the constant term over here. So a is 2, a plus b is 1, and when you plug in the 2 for the a, that means the b is negative 1. Okay, so now let's go back up to what our form of the particular solution was, which is up here. The particular solution was 8, or right here, simplified, at squared plus bt times e to the t. And we got that a was 2 and b was negative 1. And so here's our particular solution. So then if you wanted the general solution, you would add this solution of the homogeneous equation to it. And that would give you all possible solutions of the original homogeneous equation. Okay, now this is just going to be a table that kind of tells you what to do when you have some of the terms that are very similar. like if you have a differential equation, on one side you have a polynomial times an e to a power, then whatever that degree of that polynomial is, you're going to have that term plus any possible lower degree term times that e to the power. And that's all they're saying here. And then, so you're having to have this form times the e to the power because of what's over here. You just have to match the power of that, the degree of that t polynomial in front of the e to the rt. And then, depending on whether or not you have the roots duplicated in the homogeneous, you need to put another power of t, either a t or a t squared, depending on what the multiplicity of that root would be, whether it's a double root or single root. Same thing as if you were looking at the ones with the complex solutions. So if you had forms where you had an e to the alpha t and cosine of t, or an e to the alpha sine t, remember that when you have an e to the alpha t cosine, you're going to have that e to the alpha t sine of beta t also included. But they're just saying here that if you have both of these two terms on the right side with different polynomials, take whichever polynomial has the highest degree. And so that's what the k is representing here, is the k degree is the highest degree of those two polynomials. And you're going to have the e to the alpha t cosine of beta t and e to the alpha t sine of beta t. So both of these are going to be part of the form. But then you have to add that extra power of t, multiplied by that if you have duplication in the homogeneous solution. So let's just look at a couple quick examples and see if we can get what the particular form would look like. So we're not going to actually solve these. We just want to know what the form of that particular solution would be. Okay, look at the homogeneous equation first. We know that if you were solving this, we got that previously that the r came out to be -1 plus or minus I. So we know that that complementary solution, the general solution, was the c1 e to the negative t times cosine of beta, here's 1, so cosine of t, plus a c2 e to the minus t sine of t. So that was our solution to the homogeneous equation. Now let's look at the form over here. We have an e to the minus t sine of t, and we have an e to the minus t cosine of t. So you see that duplication in these if there's a constant in front. And so this one definitely duplicates it because it's got just a constant in front of the e to the minus t sine of t. But because this one has a higher degree polynomial that is not included, if we weren't paying attention to the homogeneous solution at all, and we just said, okay, our particular solution form, we've got that e to the minus t sine of t and e to the minus t cosine of t. But because we've got a cubed polynomial in front, this is just a polynomial degree 0. So we would have to start with a cube. So we would have at cubed. I'm going to run out of room. Let me see that. At cubed plus bt squared plus ct plus d. We have to have a polynomial of degree 3 because of this right here, times that e to the minus t sine of t and the e to the minus t cosine of t. Oops, can't use the same letters though. We'll start with e. This is going to be big. So that's what we would get just based on the forms right here. And they're both in that form. But because of this duplication of the constant term, see this d e to the minus t sine of t is not going to generate the 5 e to the minus t sine of t, because this term, the d e to the minus t sine, will give us 0 since it's part of the complementary solution, this solution of the homogeneous equation. So since there's just that one duplication, we would multiply this by t and this one by t to avoid that duplication. So then this will be the form that we would use to get our particular solution. Okay, same thing down here. Now we've got a third degree polynomial. It's a little bit different, so let's check that one out. The homogeneous equation is y triple prime plus 2y double prime plus y prime. So we would have r cubed plus 2r squared plus r equal to 0. If you factor it, you get that r is equal to 0 and -1 is a duplicate root. Okay, we know the solution again is y equal e to the RT. Okay, so we need 3 solutions though, since it's a third order differential equation. So we're going to have e to the 0t for one of them. We'll have e to the minus t. And since we can't have another e to the minus t because it would not be linearly independent, what we found was that if you multiply it by t, you're going to get another one that is linearly independent. And I left off my constant term. Okay, so that would be the solution for the homogeneous equation associated with it. Okay, so now let's look at what form would we expect the particular solution to take for what's on this right side. Well, we see different types of forms here. So we see something that's associated with the e to the minus t sine of t, and there's none of that over in the homogeneous equation. But because of this form, we know that we need to have an a e to the minus t sine of t, and we need to have a b e to the minus t cosine of t. Anytime you have the sine or cosine, you've got to have both of those because of the way the derivatives work. Now this 3 is just a single constant term. But look down here. This e to the 0, that's also a constant term. That is just a constant, C1. Okay, so this 3 overlaps that C1. So if I want to avoid the duplication, I can't just have a single constant A here. I have to have A times T. But it can't be A because it's got to be a different letter. So we'll use C times T. So normally if you just had a constant term, you would say the particular solution was some constant, y equal A. But because it overlaps this term here, which is also a constant, we're going to have to multiply it by the t. Okay, and now let's look at this term. A t e to the minus t, which we see as a duplication here. Normally when we see this term, because it has the t to the first, we would have to have, let's see, we're on d now, dt plus e times e to the minus t. So this term alone would require that term to be in the particular solution's form. But because these are both being duplicated, you know, if I just multiply by another t, I still have the e times t here, which is the same term here. So I haven't eliminated the duplication yet without multiplying by t squared. So I'm going to have a dt squared, dt cubed plus et squared e to the minus t in my particular solution. So that's the form of the particular solution for a differential equation with this whole thing here on the right side that will eliminate the duplication with the homogeneous equation. Now, you don't have to do this all at once. You can use the superposition principle and maybe just do it with this one first, and then you could do it with this one. You could do it as 3 separate problems, and then just take the sum of those for your particular solution. But this would be the form. If you're asked for the form, you would need to write that down. Okay, previously we've been solving second order constant coefficient differential equations. We used the method of undetermined coefficients when we were trying to find the particular solution, but the equation had constant coefficients, and that non-homogeneous term on the right side had to be a special type. It had to be either a polynomial, an exponential, like e to the t, sines and cosines, or products of these terms. That's the only time we could guess at what the particular solution's form would look like. Okay, now we're going to look at a more general method. It's called the variation of parameters. This will be a general method for finding a particular solution. Now, we're going to start with just any linear second order differential equation. Now, it could have non-constant coefficients. Put it in standard form, and this f of x, once it's in standard form, is going to be important. Okay, so the first step is going to be to find the solution to the associated homogeneous equation. So find that y1 and the y2 that we've been working with previously. We know that the solution, the general solution to the homogeneous equation, was of this form: some constant times y1 plus a constant times y2. Now, a more general second order equation is going to have a solution of the form a function times y1 plus a function times y2. So that's going to be the idea here between using the variation of parameters, is we're going to find those solutions to the homogeneous equation, but instead of taking just constants times those, we're going to take functions times those and assume that that's going to be the form of our general solution to this differential equation. Okay, so now once you take that form, the u1 y1 plus u2 y2, and plug that into the differential equation, you're going to end up getting a system of equations like this in the variables y1, y2, y1 prime, y2 prime, u1 prime, u2 prime. So now our goal here, we already know the y1 and the y2. Our goal is to find the u1 and the u2. Once we have the u1 and the u2, we know that the solution will be u1 y1 plus u2 y2. Okay, so now both of these equations have u1 prime and u2 prime. So those are the variables that we want to solve for. Now, you can use an elimination method like you did back in algebra. Another method for solving a simple system of equations where you just have the two unknowns like this, the u1 prime, u2 prime, is to use Cramer's rule. Okay, Cramer's rule says that if you take the coefficients, we're going to take this y1, y2, y1 prime, y2 prime, and form a determinant, which we know that's also called the Runge-Kutta. We're going to look at that determinant. Then we're going to form other determinants by taking this 0 and f of x and replacing the first column. Replace this first column with 0 and f of x, and keep the second column here the same. We're going to call that determinant w1. It ends up that u1 prime, this first variable, the first unknown up here, will just be the determinant w1 over the determinant w. Okay, u2 prime. Solving that using our system of equations and using Cramer's rule, we can get u2 prime by taking this w matrix again, this determinant, and replace now column 2 with the 0 and the f of x. Then we're going to have this w2 determinant. u2 prime will be w2's determinant over w's determinant. Okay, and you remember how to solve these 2 by 2 determinants. You're going to take the product down the main diagonal minus the product up the other diagonal. So you end up just getting y1 f of x for that one. For this one, you've got 0 minus y2 f of x, which is what they've got right here. So you don't have to memorize that. It's just going to be the determinant's value. Okay, so once you find u1, u2 prime using these two determinants, we're going to integrate to find u1 and u2, and then we're going to replace them in this equation to get the particular solution. So that's the method of variation of parameters. You can solve equations with variable coefficients and with any type of equation on the right side for that non-homogeneous term. Okay, so let's find a general solution on the interval from minus pi over 2 to pi over 2 for this differential equation. Notice here, we still have constant coefficients of 1 and 1, okay? But the function tangent of t is the reason we must use variation of parameters. We cannot use the method of undetermined coefficients with the non-homogeneous term tangent of t. Okay, first step. We've got to get the differential equation in standard form. So right now we have y double prime plus y equal to tangent of t. It is in standard form because we have just a single 1 in front. So standard form. Step 2. We need to find the solutions to the homogeneous equation, which will be y double prime plus y equal to 0. The solutions, because this is constant coefficients, the solutions will be of the form e to the RT. And we want to find, plug that in, and we get our auxiliary equation, r squared plus 1 equal to 0. Okay. We come up with, you can either use the quadratic formula or r squared is -1. You end up with r equal plus or minus I. So that's 0 plus or minus I, which means our alpha is 0 and our beta is 1. So we know the homogeneous solutions are going to be e to the alpha t, cosine of beta t, and e to the alpha t, sine of beta t. Okay, so this will be e to the 0, cosine of 1t, and then e to the 0, sine of 1t. So just cosine of t, sine of t. That's your y1 and your y2. Okay, so if you wanted the general solution to the homogeneous, it would be c1 cosine of t plus c2 sine of t. Okay, but it's important to note that y1 is cosine of t and y2 is sine of t. Okay, so now we're ready to, we want the general solution, or particular solution. We know our particular solution is going to be of the form y equal u1 y1 plus u2 y2. We just need to find u1 and u2. Okay, so we're going to end up with an equation, and we know from the previous slide that using Cramer's rule, we can find u1 prime by finding the determinant of w1 over w, and u2 prime will be the determinant w2 over w, and that's where w is the determinant you get by putting y1 and y2 and then y1 prime and y2 prime. And then our w1 is the determinants that you get by replacing the first column with 0 and f of x, and the second column stays the same. And then w2, start with w again, and replace column 2 with 0 and f of x. Okay, our f of x here is the tangent of t. Okay, so let's find our determinants first. W, I'm putting cosine and sine in the determinant. Okay, W1, I'm going to replace column 1 with 0 in the f of x, which is tangent of t. Keep column 2 the same. W2, start with w, keep column 1, but replace column 2 with the 0 in the f of x. Okay, now let's evaluate these. This will be cosine squared of t minus a negative sine squared of t. We're 2 by 2 determinants. You multiply this and then minus this product. Well, that just ends up being 1. W1 will have 0 minus tangent of t, sine of t. Now, tangent is sine over cosine, so that's just going to be negative sine squared of t over cosine of t. W2, we're going to have cosine times tangent. Well, cosine times tangent, tangent sine over cosine, so that's just going to end up being sine. Okay, so now let's find u1 prime. u1 prime will be minus sine squared of t over cosine of t, and then over 1. u2 prime will be w2, which is sine of t, over the w, which is just 1. Okay, so we've got u1 prime and u2 prime. We need to next find u1 and u2 by integrating. Okay, u2 is easy enough. This could be minus cosine of t. Okay, the minus sine squared over cosine of t, we can't just do a u substitution with the sine squared on the top, but what we can do is try to use a trig identity. I'm going to pull the minus sign out in front, and then sine squared is 1 minus cosine squared. See if this helps. This ends up being negative 1 in front. I'm going to split this into two fractions. 1 over cosine of t minus cosine squared over cosine of t. So I'm just breaking it into two fractions. This is 1, and then this will be the other one. And then they just reduce. Okay, so this comes out to be a negative, the integral of 1 over cosine is secant of t, and then minus cosine of t. Okay, if you remember from calculus 1, the integral of secant of t was simply the natural log of secant plus tangent. Okay, so we've got, I'm not worried about this minus sign yet, but that's the integral of secant of t, and then the integral of cosine would just be sine. And now let's multiply this negative 1 through, so we're going to have negative here and positive here. Okay, so that's my u1. Okay, now let's form our particular solution. We know the particular solution looks like this. So we're going to have y equal, I'm going to go ahead and put the sign first since it's positive, sine of t minus natural log of secant t plus tangent t. That's important to keep the same one up front. So that was my u1. My y1 was cosine of t. And then plus the u2, which is negative cosine of t, times the y2, which is sine of t. Okay, and let's simplify. So we have a sine times a cosine here, but this is going to be a minus sine times a cosine, so we end up just getting minus cosine of t, natural log of secant t plus tangent of t. Now, had we wanted the general solution, well, we do want a general solution. We want a general solution here. This is the particular solution, right? That's what we were finding here, a particular solution. So our general solution will be y equal, I'm going to go back to my y1 and y2 and just take constants of those. So c1 cosine of t plus c2 sine of t, and then plus my particular solution, and we've got our general solution. Okay, one more. I want a particular solution for this. I've got the same differential equation that I started with. Okay, so we've already found the solutions to the homogeneous equation, this is the same differential equation. So we know that y1 and y2 are just the cosine of t and sine of t. Okay, so we have that general solution of c1 cosine of t plus c2 sine of t of the homogeneous equation. Now, we've already solved the equation where you just had a tangent of t on the other side. We got that particular solution was negative cosine of t times natural log of secant plus tangent. Okay, so the only difference is this 3t minus 1. Now we could start completely over and use the variation of parameters and use this whole function on the right side, but we don't need to. We can use the superposition principle and solve the problem separately. The y double prime plus y equal 3t plus minus 1. If we can get the solution to that one, we've already got the solution to y double prime plus y equal tangent of x, or tangent of t. That's the solution to that one. So let's find a particular solution to this one, and we'll just add them together. So we know what the homogeneous solution looks like. We want the particular solution, the form of it, because of what's on this right side is of the form at plus b, which does not overlap the homogeneous solution. So we're just going to use this. Let's see, y prime would be a and y double prime would be 0. So that means that we'll have 0 plus the y, which is at plus b. I'm just solving this equation right here, equal to 3t minus 1. And that becomes simply that a has to be 3 and b has to be negative 1. So our particular solution, if the right side were just 3t minus 1, would be 3t minus 1. Okay, that's easy enough. Okay, we've got a particular solution for when the right side is just tangent. So the superposition principle says that the particular solution then will just be minus cosine of t times natural log of secant of t plus tangent of t plus 3t minus 1. Okay, but we want the general solution again. The general solution, y, is equal to c1 cosine of t. We're taking the solution of the homogeneous equation, which is called the complementary solution, and then add the particular solution to it. And that's our general solution. So use variation of parameters either when you don't have constant coefficients or you have functions on the right side that aren't your polynomials, exponentials, and sines and cosine products. Okay, previously in this chapter, we've been looking at second-order differential equations where the coefficients were constant. So they were equations of the form a y double prime plus b y prime plus c y equal to either 0 for a homogeneous equation or some f of t for a non-homogeneous equation. So now we're going to look at equations that have variable coefficients. So instead of just a single a, b, c for the coefficients of y double prime, y prime, and y, we're going to look at a function of t for the coefficient of y double prime, a function of t for the coefficient of y prime, and a function of t for the coefficient of y. Okay, so these will be variable coefficient differential equations, second order. Okay, so normally when we're working with these, we're going to divide by that first initial constant so that we always have a 1 in front of the highest order derivative. So the standard form will be this. Okay, so we're still going to have a p of t that's the coefficient of y prime and a q of t that'll be the coefficient of the y. And then g of t will be that resulting function that's on the right side of the equation. Okay, so it ends up that as long as this P, Q, and G are continuous functions on an interval that contains some initial point t. So I'm looking at a specific value of t, so t equal to t naught. So if we have an interval, so t naught is an element of the interval AB. So t naught is just a number that's in that interval, and the P, the Q, and the G are all continuous functions on this interval, then if we have the initial conditions that y of t naught is cap y0 and y prime of t naught is some capital Y of 1, then for any y0 and y1, there will be unique solutions on the interval AB to this initial value problem. Okay, so we can find a unique solution to this differential equation that has these initial conditions as long as the P, the Q, and the G are continuous on an interval that contains that t value for that initial condition. Okay, so let's look at a problem. We want to find the largest interval for which that theorem ensures the existence and uniqueness of a solution to this initial value problem. Okay, so we've got our initial value problem here. The conditions, y of 1 is 3 and y prime of 1 is -5, are occurring at the t value t naught equal to 1. So we need to look for an interval that contains t equal to 1. Okay, the first thing we're going to do with this equation is look at the coefficients. I've got t minus 3y. Okay, as I said that, I realized this is a typo. This y can't be here, or it wouldn't be a second order linear differential equation. So t minus 3, second derivative of y with respect to t, and then plus the coefficient of the dy dt here would just be a single 1, and the coefficient of the y here would be the square root of t. So notice the coefficients here. We've got t minus 3 is the coefficient of the second derivative. We've got 1 is the coefficient of the first derivative. We've got the square root of t is the coefficient of the y, and then here's our function on the other side. Notice those are all functions of t. Okay, so it is a second order linear differential equation with variable coefficients, since these aren't just constants in these two terms. Okay, so the first step would be to put it in standard form. So standard form here would be the second derivative plus 1 over t minus 3 dy dt plus square root of t over t minus 3y equal natural log of t over t minus 3. Okay, so we've got our coefficients now. Here's that p, here's the q, and here's the g on the right side. Now, this differential equation with these initial conditions will have a solution, a unique solution, as long as the functions, the p, the q, and the g, are continuous on an interval containing t equal to 1. So we want to find out what interval would that be true for. So let's look at the three functions and make sure they're continuous. P will be continuous everywhere except for t equal to 3. Q will be continuous as long as t is not 3, so that the denominator won't be 0. And the numerator here, the square root of t, requires that t has to be greater than or equal to 0. G, again, will be continuous as long as the t is not 3. And natural log of t must exist. Well, natural log of t, if you recall the function y equal natural log of t, it only exists if t is greater than 0. So the domain of this function is from 0 to infinity. So t must be greater than 0 for natural log of t to exist. Okay, so what interval will all three of these then be continuous? Well, we know that t must be greater than 0, so we can throw out t equal to 0 here. So t has to be greater than 0, so just look at a number line. We know it has to be from here on, if this is values of t, and we know that t can't be 3. So we're going to have a little hole here as well. So the intervals where all three of these will be continuous would be from 0 to 3, not including 0, and not including 3, and from 3 to infinity. So t greater than 3. Okay, so we've got the intervals in from 0 to 3 and from 3 to infinity. Okay, so now pick the interval that contains the t value where that initial condition occurs. Since we're looking at t equal to 1 and we know that that's in the interval 0 to 3, the largest interval then for which we are guaranteed the existence and uniqueness of a solution to this initial value problem will be the interval from 0 to 3. Okay, now we're going to look at a special case of a linear second order differential equation. If it can be expressed in the form a constant times t squared and then y double prime plus a constant times t y prime plus a constant c times y equal to f of t, then we call that a Cauchy-Euler or equal dimensional equation. So it's a very special case where it has variable coefficients, but the variables that's in front of each of the derivatives actually matches what the order of the derivative is. So when you have the y double prime, the coefficient is just going to be a t squared times a constant, and the y prime will have just a t to the first times the constant, and then just the y term itself is a t to the 0 coefficient, which will just be 1. So the only variables are t powers that match the order of the derivative of that term. Okay, so to solve a homogeneous, remember that means that we have a 0 over on the right side, Cauchy-Euler equation, we know the form of the solutions. We know the solutions will be of the form y equal t to the r, where r is the roots to that auxiliary equation that we're going to get, or the associated characteristic equation. Okay, so let's look at what that associated characteristic equation looks like. Now, I'm not going to memorize this form down here. Don't memorize it. Just know what the form of the answer is. When you see the t squared with the y double prime, the t to the first with the y prime, and then just constants with a c, just know that the solution is of the form t to whatever the roots are of the auxiliary equation, which we get that by just simply plugging this value, this solution in for y into the differential equation. So this is very much like when we were working with the coefficient equations, and we knew the solution was of the form y equal e to the rt. But the Cauchy-Eulers have the form y equal t to the r. Okay, so let's find what that's going to look like. So if y is t to the r, then we know that y prime would be r times t to the r minus 1. And y double prime will be r times r minus 1 times t to the r minus 2. So now let's plug those in for the second derivative, the first derivative, and the y value, and our differential equation then becomes at squared r minus 1 t to the r minus 2 plus bt times r prime, which is rt to the r minus 1, plus c times the y, and then we've got a homogeneous equation, so 0 on the right. Okay, so now simplifying, notice the values of t, the powers. Here we have a t squared and we have a t to the r minus 2. Since the bases are the same, they're both t to powers, add the exponents. The exponents 2 plus r minus 2 will simply be r. And then we'll have a times r minus 1 for the rest of it. In the second term, we have a t to the first, and we have a t to the r minus 1. Add the exponents, and you get t to the r. So we'll have b r t t to the r. Okay, now, notice every term has a t to the r. I'm simply going to factor that out. Okay, we're going to assume that the t is not 0, since we're given that t is positive. So that means we can divide both sides by it and still have an equality. So we'll have AR, r minus 1, plus BR plus C equal to 0. When that's true, we'll have a solution of this form. So we just need to find the values for r that make that true and put those as the exponent on the t for our solutions. Now, simplifying this, that would be AR squared minus AR plus BR plus C equal to 0. Or you could write it as AR squared plus B minus A times R, just factoring out the R of the second and third terms. And that's your characteristic equation that results, it's associated with this differential equation. So that's what I marked out over here. Don't memorize that form. Memorize the fact that this is the solution of an equation that's in the Cauchy-Euler form, with the t squared and the t as those variables that are coefficients of the y double prime and the y prime. Okay, so let's find two linearly independent solutions to this equation. Okay, the first thing I do is when I look at it, I'm going to notice that it's second order. It has variable coefficients, 3t squared, 11t, and minus 3. Okay. But because of exactly what those variables are, it's not just any variables, it's t squared with the y double prime and t to the first with the y prime. That means it's a Cauchy-Euler equation. And notice it's homogeneous. Okay, so because of it being Cauchy-Euler and homogeneous, we know that the solutions are of the form y equal t to the r. We simply need to find the r values. So find r prime, y double prime, plug them into the equation. We'll have 3t squared r minus 1, t to the r minus 2, plus 11t r, t to the r minus 1, minus 3 times y, which is t to the r, equal to 0. I know, being Cauchy-Euler, that the t's will have a t to the r power in each term. So if I divide through by t to the r, right, t squared times t to the r minus 2 is t to the r. I'll go ahead and put one more step down. So that's 3r, r minus 1, plus 11r, t to the r, minus 3t to the r. Now divide everything through by t to the r, and we get our characteristic equation that's associated with the original differential equation. Simplify, 3r squared. We've got minus 3r plus 11r. Okay, now let's find the values for r. Hopefully this factors. We're going to try first before we go to the quadratic formula. I know it's got to be a 3r and an r to give me the 3r squared. And I know the last two numbers here and here have to multiply to be the 3. I want the sum to be positive 8, so I'm going to put the 3 and the 1 here so that I'll get the 9 and the 1 to give me an 8. And I need this one positive and this one negative. So that looks correct. That means that my r values are 1/3. Set this factor to 0 and negative 3. Okay, so that gives me two linearly independent solutions that would be y equal t to the 1/3 and y equal t t to the minus 3. Okay, the previous example of a Cauchy-Euler equation had two distinct roots to that auxiliary or characteristic equation. So what if those roots end up being equal to each other so that we have one unique root? Or what if they end up being complex numbers? We had adjustments for those solutions when we had that situation when we were dealing with the constant coefficients. So if the roots of the associated characteristic equation are equal, then the independent solutions are given by this. y1 will be t to the r, and y2 will be t to the r natural log of t. Okay, we did something very similar when we were doing the constant coefficients. Okay, so that's when you have two equal roots. If the roots are complex, meaning the two roots are of the form alpha plus or minus the beta I, then determine your alpha and your beta, and the independent solutions will be t to the alpha cosine of beta natural log of t. That'll be the argument on cosine. And y2 will be t alpha sine of beta natural log of t. Okay, so let's look at a couple examples. I want to find a pair of linearly independent solutions for the Cauchy or Euler equations. Again, we're assuming that t is positive. In this first example, first off, you do see that it's a second order. You see that it's variable coefficients. I see a t and a t squared, but the powers of t match the order of the derivative. So this is a Cauchy-Euler. So be sure you identify, is it constant coefficients or is it non-constant? And if it is non-constant, is it Cauchy-Euler? Do the powers of t match the order of the derivative? Because only when it's Cauchy-Euler do we know that the solutions are of the form y equal to t to the r. Okay, so plugging that in, and we'll skip a few steps here. We already know what y prime looks like and y double prime. We've done that enough times. So I have t squared times r minus 1, t to the r minus 2. Okay, so that's y double prime, plus 5t, and then y prime we know is r, t to the r minus 1, plus 5 times t to the r. Okay, I know that pairing up the t powers each time come out to be a t to the r, so I'm going to divide everything through by t to the r now. So I'm going to have r minus 1 remaining from the first term, plus 5 times r, plus 5 equal to 0. Okay, now solving, I'll have r squared plus 4r plus 5 when I take the minus r and the 5r here. And now this one's not going to factor. In fact, if you use the quadratic formula, r equal to negative 4 plus or minus the square root of 4 squared is 16 minus 4 times 1 times 5 is 20, you'll see complex roots. Okay, so we have the square root of negative 4, which is just 2i. So that means our roots are negative 2 plus I and negative 2 minus I. Okay, so that means then that I've got alpha is negative 2 and beta is equal to 1. Okay, so my roots, by looking at the forms of the roots for when there's complex solutions to the characteristic equation, would be y1 will be t to the negative 2 cosine of 1 times natural log of t, and the second root solution will be t to the negative 2 sine of 1 times natural log of t. And I'm just stating that these are linearly independent. We can use the Runge-Kutta to confirm that. Okay, let's look at this second example. I'm going to look and I see a second order differential equation, homogeneous since there's 0 on the right side. And I see variable coefficients. So the only type of variable coefficient second order equation that I can solve is the Cauchy-Euler. Those are where the power of the t matches the order of the derivative. So this is indeed Cauchy-Euler. I see t to the second and t to the first matching the order. So we know that the solution is of the form y equal t to the r. And plugging in the derivatives, I get t squared r minus 1, t to the r minus 2, plus t times r t to the r minus 1 equal to 0. I can ignore the t power since they're both t to the r for each term, and I'll divide through by that. So I'll have r times r minus 1 plus r equal to 0. Okay, so r squared is 0, which means r is only going to equal to 0 when I take the plus and minus the square root of 0. So that means I've got a single distinct root. So we have repeated roots. 0 is a root twice. So using the form of the solutions, when we know we have the roots that are equal, we know one of them will be y equal t to the r, which is t to the 0. And we know that the second one here will be, so that's y1, y2 will be t to the r, t to the 0, natural log of t. Well, t to the 0 is just 1. So our two roots then are y1 equal to 1 and y2 equal to natural log of t. Those are our two distinct solutions to the second order differential equation. Remember, we have two solutions since it's second order. Now we're going to go over some of the theorems that we've talked about in the past when we were working with the constant coefficient second order differential equations. They're going to apply also in the cases where we have the variable coefficients, including the Cauchy-Euler, specific case. So a condition for linear independence of solutions. So if we say that y1 and y2 are any two solutions to the homogeneous differential equation, okay, so we found the two solutions. If we want to show that they are indeed linearly independent, meaning that they're not just one of them being a multiple of the other one, then we can use the Runge-Kutta. So the Runge-Kutta is where we set up that determinant that had the two solutions on the first row and then put their derivatives on the second row. Now, if we're trying to find, if we had three different solutions, we could extend this to a 3 by 3 where we would have y1, y2, and y3 on the first row. We'd have the first derivatives on the second row, and we'd have the third derivatives on the third row. And then we just calculate that determinant. So as long as this determinant is not 0 for all values on that interval, then we say that the value, okay, so if the Runge-Kutta is 0 at every point, then we say they're linearly dependent. So if they're not 0, then we would say it was linearly independent. So if y1 and y2 are any two solutions to the homogeneous differential equation that are linearly independent on an interval that contain whatever the initial condition value for t is, then there will be unique C1s and C2s so that we can get a solution by taking a linear combination of those linearly independent solutions. So we found two solutions, y1, y2. We've proved that they're linearly independent using the Runge-Kutta. So show that they're linearly independent. Then the general solution would be y equals C1 y1 plus C2 y2. That's the general solution to the homogeneous differential equation. So if we have an initial condition, y of t naught equal to capital Y0 and y prime of t naught equal to y1, then we can find unique solutions for the C1 and the C2, as long as those y1 and y2 here were linearly independent on an interval containing the T naught. Okay, so now, I just mentioned this, but this will be a general solution to the homogeneous differential equation. Now, this textbook uses y sub h to represent that general solution to the homogeneous differential equation. Some books will use y sub little c to mean it's called the complementary solution when it's a homogeneous equation. So if we have this differential equation, notice it can have variable coefficients. This is the standard form, and it has variable coefficients. Then if y1 and y2 are linearly independent solutions, c1y1 plus c2y2 will be the general solution of the homogeneous differential equation. So now what if it was non-homogeneous, meaning that we've got some function g of t on this other side? Okay, to get the solution, what we have to do is we have to first find the solution to the associated homogeneous equation. So first set it equal to 0 here, find those solutions to that homogeneous equation. That is the y sub h that we found up here, the linear combination of those two solutions. Then we need to find a particular solution. Okay, so to find a particular solution, when we were looking just at the constant coefficients, we used the method of undetermined coefficients by knowing what that form was going to look like. If we had functions of the form polynomials, exponentials, sines, and cosines, we guessed what the form of the solution looked like, and then we solved for those a, b, c, however many variables we had, to find that specific solution. Now, when the g of t was not functions of the form polynomials, exponentials, and sines or cosines, or products of those, we then used a method called the variation of parameters. So that's how we found that the particular solution. And remember that those particular solutions, in that case, where it wasn't those special kinds of functions, was some function u times y1 plus some function, so u1, u2, y2. So this was what we used for the particular solution when it wasn't, the g of t was not the special polynomials, exponentials, sines, cosines, or products. Okay, so we found those by variation of parameters. So once we get that particular solution, we again will know that this is going to be the general solution for that differential equation that's non-homogeneous. Find the particular solution, find the complementary solution or the solution to the homogeneous equation, and just add those together. So if you have the linearly independent solutions to the homogeneous equation, remember we can get y sub p by knowing that the y sub p will be of this form, because we already know the y1 and the y2, and then we just found those coefficient functions u1 and u2 that made that particular solution. So remember the way we did this. We were looking at solutions to this system of equations, and I showed you by setting it up as a determinant. We started with the determinant w, which was determinant of y1, y2, y1 prime, y2 prime. And then we replaced the first column and the second column to get y1. So we used the 0 for the first, and we used the function g for the second, so g of t. And then kept y2 and y2 prime in the second column. And then w2 was the same thing. Start with w, keep the first column the same way as it is, and replace the second column with 0 and g of t. And then I showed you just to calculate this determinant. Remember the product down the main diagonal minus the product here. So it ends up being 0 minus g of t y2. And then this one would be y1 g of t, and then minus 0. So that's what we got for the determinants. And then we found the u1 and u2, or they're calling them g's here. u1 was going to equal to whatever the determinant w1 over w was. See, this was u1 prime was equal to this, so then we had to integrate to find u1. So u1 was equal to the integral of whatever the W1 over the W came out to be. And then U2 prime was the W2, which notice what they've got here. Okay, so here's the W1 they have on the top over the W, W2 over W, and then to get U2, you just simply integrated with respect to T. Okay, so once you find the U1 and the U2 here, you simply put those as coefficients of the Y1 and Y2 functions that were found to be solutions of that homogeneous equation. So all of these are things that we've talked about before. Find the solution to the homogeneous equation, so you'll get your Y sub H. Find your solution, your particular solution to the non-homogeneous equation. And so if it has variable coefficients, we will have to use the variation of parameters to do that. And we use the Y1 and the Y2 that we found getting the general solution of the homogeneous equation. So these same methods work for when the variables are the coefficients of the second order differential equation.